All right, we rebooted the machine and, well, not rebooted the machine, rebooted the application. It seems to be working again. So again, I don't know if that's a problem, but it seems to get locked up in a state. If that happens, just better to restart the application rather than keep in a funny state where it could damage your files. All right, so we were just routing right here, manually routing on the top layer. And so we just did C3, so let's go ahead and do C4. So we're going to go back to route, interactive routing, and we're going to grab, and again, if you zoom in enough, the net names will come up, net C4.1, net C4.1, and we're just going to go in here and go ahead and grab it, double click. You got to double click at the node, and again, we're not hitting, I like to hit these things on center, dead center, so it's coming in perfectly perpendicular to the circle here, to the circumference. But we can't do that with this snap grid. We'd have to go down to 5 mils. So we're not going to do that. We're just going to stay at 10 mils. Okay, so we've got those two traces there on U1, and we can continue. We can see that pin 2 goes to pin 6. Let's do that one. That's an easy one. All right, pin 2 to pin 6. Again, let's get pin 2 here, and we'll come in, and we could come in like this and go tight, or we come through the middle. You know, there's lots of ways to do this. All right, double click, re-pour, and then when we're done, what we're going to do is we're going to go grab things. And again, whenever you select an object where there's multiple layers, you have to select the one you want. There we go. And I'm just dragging it a little bit. And when we're done with routing, we're going to go back and clean everything up. All right, we're going to clean everything up. So this is the process. All right, so now I could sit here and route this entire thing for you. But what I'd prefer that you do is you just use the auto router for now, and then what I'd like you to do is augment the auto router with yourself. So after it auto routes, you kind of take a look at it and you go, oh boy, that's ugly, that part's ugly, and you can rip the traces up. It's called ripping. The traces up and then redo them yourself manually and clean them up, change the size of things and so forth. Okay, so we're going to try and use the auto router. And remember, the auto router is going to be able to route on two different sides, on the top copper and on the bottom copper. Okay, all right. So we'll just put it here on the top, and what we're going to do is we'll zoom out. We're not going to be able to see much here. It's not going to do it visually. It's just going to do it and then pop it all up. Now let's do a Control S here to save. All right, and then now what we're going to do is first we're going to run a design rule check here. All right, so we're going to go here, we'll say reset markers, we'll click design rule check. All right, and then we want to run design rules. All right. Okay, and you can see here we've got all these violations. All right, so 38 of them are unrouted nets. We know about those, okay, because we haven't routed them. 44 are silk to solder screen mask clearance. Don't care about that, right? That's the solder, the silk screen, that's the text. Don't care about that. That's not anything functional. And then these are silk to silk screen. Again, and what is it talking about silk screen? And the reason why it uses the word silk screen is silk screen comes from a printing process, right? Which may not necessarily be the way they do it. It's called silk screening still. And it's a way of printing material or printing on surfaces. It's called silk screening, and it's a layer process with ink and so forth. It's a printing process, so it's called silk screen, and that's where that word comes from. And it's completely confusing and really doesn't have anything to do with anything anymore. But that's just talking about the text. The text. We don't care about that. So we're doing pretty good. So basically, all we have to do is get these nets routed, these unconnected nets. So here's this design rule report. Now, what you can do is you can drag this off to another monitor. I have another monitor over here, another monitor over here, which you can't see. I could drag that off, but I'm just going to close it. So I'm going to right click on it, close design rule verification report. I don't need to see it. I already know. All I really need to do is get these nets routed. So let's use the auto router. So let's find this thing. Where is the auto router? So in home, clipboard, routing. So here's routing. So it should be in routing, right? No, not in routing. So interactive differential, not there. It's not in unroute. It's not in connections. It's not here in place, not in collaboration, not in any of these things. Where is it? It's over here in tools. Total horrible placement. Drives me crazy. Here's the auto router right here under auto route. And it's not route. It is route. It's auto route. It's routing. So we're going to click here. And so if you click the icon itself, In this case, many of these things will go to a dialog, but this one doesn't. It only will drop this down. So again, this tool has weird behaviors. So we can go to setup, we can go to all, we can do all this. So let's just go to a setup. Now, in setup, this is where we start to play with the parameters of the auto router, right? So routing width, routing via styles, all these different things here. Let's take a look at these. And there's strategies for routing. How do you want me to route it? A router is a very complex piece of software. Routing is an NP complete problem in computer science, and so these routers use heuristic algorithms. Some use artificial intelligence, some use all kinds of different methods to route your board. And routers can cost from $200 to $50,000. All right, very expensive pieces of software, especially if you want to route high pin BGA ball grid arrays, 1,000, 2,000 pin FPGAs. On 60 layer boards, crazy stuff. So these routers get really expensive. Many routers do a horrible job, and most electrical engineers just will not use them, including me. I typically won't use them, but they're getting better all the time. And this router is not bad. The router inside of this, and I'm not sure which router it is. I'd have to look it up. But it's not a bad router. But it can have different strategies where it optimizes different things. So it has a priority of, I want to make your buses this, or I want to do your power like that. Again, a gajillion different settings to make that happen. But let's start off simple. Routing widths. So remember this, we set this ourselves. So rule width, the rule, its name is width. Okay, it's not rule width, it's the name is width. So if we were to click on this thing, we could say edit rules, and I believe we can just click on this one. Yeah, and it brings up the rule specifically. And we already set this rule. So on the top and bottom layer, we said minimum is 10, preferred is 12, maximum is 12. We'll just hit cancel. All right, routing via styles. Remember we did this, right? So we could click here. Remember we said we want it to be 10, 10, 10 for the whole size and 20 for the total width, all right? So that's good. And that's the only thing we did. And then there's all these different things here we can play with, but we're not going to play with them. And that's where you do all this right here. Yeah, it's the Citus router, S-I-T-U-S Citus router. Says it right there. And that's a very popular router that's used and licensed by a lot of companies, the Citus router. Okay. So we'll hit cancel on that. Let's go back to auto route. And so we're going to say all. And we go back here, and all we're going to do is just say route all. Now, rip up violations after routing. So what this does is if you click this, anything that's a violation, it'll rip that trace up and just get rid of it so that you can go at it. We don't want to do that. We want to leave everything because I don't care about violations, because I know the only violations I'm probably going to get are clearance violations to text and things like that, which I don't care are not functional. All right, so let's leave that unchecked. Okay, and then like I said, there's these different strategies here. There's this strategy, default two-layer with edge connectors, default multi-board, general orthogonal, via miser. So the via miser, let's look at that. For routing multi-layer boards with aggressive via minimization is what it says. So maybe I don't want to punch a bunch of holes in the board because that's going to cause some kind of a problem with RF or EMI or the integrity or the thermal characteristics of the board, right? So that's just one strategy. Okay, so let's go back to default two-layer board, looks good. And we can create, these are just built-in strategies which are based on a parameterization. So there's a bunch of different parameters that you can change, and then you can say, I want to call this the default two-layer board. See, we can add here and create other strategies. And then when you do that, a big dialog is going to pop up and you're going to fill out a bunch of things which are really complicated. So we're not going to mess with it. Okay, here we go. Ready? We're going to say route all. Cross your fingers. Now this process used to take minutes to hours in the past, but this is an i7 something, i7, I forget the name of the particular version of the processor, but it's a fast one. I think it's running at 3 or maybe 3.5 gigahertz. All right, so during the routing, it's done. Now it wants to repour the fill polygons, the ground fill. So let's say, sure, repour, go ahead. All right, okay, now, not sure if it's done. We'll scroll around in a second. I see the cursor flickering, but here in this window, the output messages, look here. It said up here, routing started, creating topology maps, starting fan to plane. It's just telling you all these different states that it's going into here. 27 of 48 connections, we're 56% done in 2 seconds, really, really fast. 46 of 48, we're 95% done. And then a lot of times it'll get 99% done and get stuck for a little while. It'll have to keep trying different things to, a couple traces it'll get stuck on, and then it'll finish. All right, and that what you might have to do is you might have to move around a couple ICs or just manually route those last signals. So anyway, it was able to finish itself and do everything. And 48 of 48, 105 seconds. So it took it 5 seconds. Crazy, huh? This might have taken like minutes before in the 90s, but now it's very, very quick. Okay, so here is the board. And there it is. I just clicked in there, and once it hit that message box, it popped up. So I'm just going to zoom in and look at this. All right, and now what's interesting is a lot of the routing is on the blue plane, so which is kind of interesting. So on the back plane, it did a lot of the routing instead of the top plane. It made that decision as it was working. All right, and routed there on the bottom plane. Let's put this into single plane mode so we can see a little bit better. So we'll go to Home, View, Single Layer Mode. There we go. All right, and now we can switch between the top layer and the bottom layer with a plus and minus here. Oops. There we go. And now what we're going to do is we're going to go through this manually, and we're going to clean this up for things that I don't like, all right? And I'll tell you why I don't like them, and then we're just going to clean this board up. So let's start with the top layer. So I'm going to zoom out, all right? So what we're going to do now is the thing has been routed. Okay, so there's the top layer, and there's the bottom layer, all right? So it's been routed. So good. Let's go ahead and let's run our design rule verification again. Let's make sure we're okay. So let's go to Tools, which it's not in. Let's go back to Home. There it is. Design rule check. Let's go ahead and reset error markers. Great. Let's click on design rules. I want to do the whole thing. Run design rule check. Okay. There's our report. So let's look. Rule violation 63. Okay. Errors 0. Okay. Violation, don't care about. Errors, I do. So we look here. What do we got? We got width constraint. So a couple traces. We violated the width constraint. We click on that. It'll show us where they are. Don't care right now. Solder, silk to solder, mass clearance a couple times, many times it's violating that, but I'm sure it's okay because we set it, it's set for 10 mil, which is huge. So this can probably go down to 6 mils or even 5 mils. It would be okay. I'm sure it's okay. Silk to silk clearance, again, it's been set for 10, which is huge, and probably got some 9s or 8s in there, and that's why those violations occurred. But the big thing we care about is unrouted nets. All right, but let's go look at these two problems right here. If you just click on it, what it'll do is it'll zoom to it. All right, and here they are right here. So it went to this report of hyperlinks, and now here it is here, and it says exactly where it is. It's saying the coordinates at 12,100 mil, comma 1450 mil x and y coordinates, top layer. So if I click that, all right, then it shows me where that is, and again, it's not easy trying to figure out where exactly it is and what exactly it's talking about. But it's talking about this in this case. And the reason why is because remember we made this track too big. We violated our own rule, but it's okay because I wanted it to be 20. We want all power to be 20. We're going to go back and change all those V sub CCs to 20 ourselves manually, or as large as we can up to 20. Okay? All right, so that's okay. So the board routed safely, and so we're done. All right, so we'll go back to design rule verification. Let's just close that. I don't care to see it anymore. So now let's go ahead and Control S. We've got a routed board, and we could send this to a manufacturer. We could create Gerber files from it and send it. It would probably work, right? It's electrically functional. If the schematic is correct, right? Oh, let's get the schematic back up here. That literally took about, I don't know, 3 minutes, 4 minutes. Like I said, this cloud stuff, until you cache it and bring it in, it's just horrible. All right, so we got our schematic there so we can look at things on that. All right, so back here on the PCB, now what we need to do is we need to start cleaning this up. And you might say, well, Andre, wait a minute, the auto router did it. Doesn't it know what it's doing? Yes and no. The auto router did it, but then there's all kinds of things that the auto router doesn't know to do. And you know, you would need an expert system or an artificial intelligence to finish this thing off mostly. So now what we're going to do is we're going to apply our years and decades of PCB layout and design and building PCBs and seeing what happens and all this and all our rules of thumb that we've compiled over the years, and we're going to fix it, right? And we're just going to make it a little bit better, a little bit more manufacturable, a little bit cleaner. The majority of things that I'm going to do can fall under the category of aesthetically pleasing. And aesthetically pleasing typically also means functionally better, right? So we're talking about equally distributing objects, and if you equally distribute something, then you equally distribute their mass, you equally distribute their current, their this, their that. So a lot of times just making things visually cleaner will have a side effect that has a functional effect that makes things better. So we're not going to go into exactly why we're doing everything. We're just going to do it, and I'm going to kind of say, why we're doing it. What's the reason? All right. So the first thing is, let's start here. We're going to make traces bigger. We know that. But let's start here. Anything wrong with this? No. Trace looks good. And also, we're going to put this in 5mm mode so we can get a little bit more resolution. All right. Trace looks good. I'm happy with that. Trace looks good. I'm happy with that. Good. Looks good. Now, right here. So what's happening here? So see this, we've got a via here, and then we've got this fill. There's no need to not have this be complete, all right? So let's complete that, and that's just going to be much better, and we're going to have a nice ground around this entire via rather than having this little hole here. So I'm just going to grab this. I'm just going to pull it up a couple grid snaps, which I know will be 10 mils because we've got to set at 5 mils, all right? Oh, I see another one here. Don't like this. Oops. Don't like this. Select it. Move it out. All right, again, move it out. And the whole point is here, we want that fill to finish. All right, same thing here. I'm going to pull this up a couple times. All right, and then I'm going to grab this one and just move it a couple times over here to give this fill a little bit more. Thicker is better. The more fill we have around everything, the better. All right, so we're moving around here. This looks good. There we go again. Let's back out. Okay, so we can definitely pull this up. Let's pull it up a couple snaps. And I'm going to do this in real time with you, so you're just going to have to sit here and deal with me talking. I want you to see every single thing that we do. What is this? This is unnecessary, so let's pull this out, pull this in, do something. All right, so we're going to pull that out. There we go. All right, and what happened there was the router did something, and it probably ripped it up and then placed it back, and it didn't do any kind of cleanup on it, so it just kind of left it. All right. Okay, so let's zoom out and constantly zooming in and zooming out. All right, zooming in and zooming out. Okay, now see right here. So we got this ground right here, but I don't know how much is getting through here. This is getting through. This is pretty good, but put a little bit more space through here. Maybe I want to get a signal through there later. Okay, there we go. Always adding space. Equally distribute things. Okay, here we go right here. Let's do this. Let's pull this one out. Okay, good. All right, this looks good here. I'm okay with that. This area right here, I'm not happy with at all. Now, here's some things really functionally that I don't like. So here's a ground. This is grounding signal. We want ground here. So we got 1, 2, 3. Where's the fourth one? It's not there because this is too close. It hugged these pins. So first thing I'm going to do is I'm going to pull this away. Okay, pull that away. Keep repouring your ground. Now I'm going to pull this down. Okay, that's much better. Okay, next. This pin is right on top of all these pins. So the signal is right on top of these. Now, normally that would be fine, but I got all the space here. Why put it on top of it? Also, what can happen is as I'm soldering this, let's say that there's a little bit of exposed copper here. I might short this. I might short this. I might short this. I got all these chances to short it. Plus, let's just get the ground around here, right? So let's just grab this. Let's pull it out. Okay. Make things look nice. Be greedy. Okay, go like that. Okay, getting there. I'll go back to that, and you're probably starting to see things and go, ooh, go there. It's like it's actually fun. Now here, not much we can do here because it's decided to go through here. Now I might be able to center this a little bit more between these two, but if I grab this, I can pull it up a little bit. Let me see, and it's probably going to be the exact same. Yeah, I can put it up or put it down. My only other option is to now route this around here and rip it up and do all that, but I'm not going to do that. Now here, see this? This is centered and then this business is happening. So let's zoom out and it's going here. So you know what? I'm going to grab this. I'm going to pull this down. And there we go. And again, this is grounded right here. So notice we got these two grounds and we got the signal going through here. All right. And we've only got two grounds, and this is our ground for our IC. See, this is pin 8, so I'm not happy about this. I'm not happy about this. I kind of want more ground. So my options are to take this signal right here and pull it down here. I can do that. So why don't we take this, and I'm going to pull, 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 pull. I'm going to pull it right to the edge, a little bit aggressive. Then I'm going to take this right here. Oh, and then also, see, this is not totally aligned. All right. Okay, let's get rid of that. Let me see if I can get this thing to, nope. So what's happening here is you got these two, so we're going to go into a 1 mil. I'm going to go into 1 mil here, and I'm going to take this and I'm going to move this up just a hair. And then I'm going to see what's going on here. See that? This little business right here, and I'm not sure what's even going on there. And I'm just trying to fix it. See, there's two of them here. There's two of them. So what if I delete that? All right, so I just deleted that. Now there's one here, there's two here. Delete that. So see what's happening? All right, let me just try and pull this away. Let me repour. All right, now let me pull this in. Yeah, so what's happening here is we got this little thing here, and I definitely don't like it. All right, so I got this now. Let me see if I can pull this away. I'm trying to just pull this thing away. All right, let's go out of 1 mil and go back to 5. Let me see if I can grab it. And I see I can't grab it. I'm going to delete it. All right. Okay, now let me pull this way. Can't do it. And you're gonna see this problem. You're gonna see this problem. Let's move this way a little bit. When you're doing routing, sometimes the tool gets a little bit confused. All right, so this it's going from this pin over here. So I'm just gonna get rid of this. Oops, I'm gonna get rid of this trace right here. It's just making me mad. Okay, now it was coming all the way through here. So now what I'm gonna do, whoa, let's undo that. I grabbed the power planes. Got to be very careful. All right, so this is coming through here. So what I'm going to do is I am going to try and bring it down here. See, now we've got those 3 grounds that we like. We got 3 of the 4 grounds. So what I'm going to do is this. I'm going to go into interactive routing mode here, and I'm going to see if I can get this thing right there. Okay, now I've got it. All right, now I'm going to click it up into here, double click. All right, now I'll repour. Okay, now we've got it connected. Let's go out of interactive routing mode. And you know what? Be careful. Everything is really slow sometimes with this cloud connected thing. So now what I want to do, the question is, can I get this trace, down here? Now, if you look at, here's the bottom of the board. We don't have a whole lot of room here. So the question is, what if I drag this thing down here? What if I drag it down here? I can do that. And if I drag it a little bit more, do that. And then I've still got, and then I can also drag this right here. All right, I can drag this here. This is, I guess we could leave that there, huh? We could leave that there. All right, and now we've got 3 of the 4 grounds, and then I could, and again, this is where this interactive tool, depending on its settings, may act a little funky. And then I can bring this up like this. Maybe I want to do that. All right. Now I don't like how this has been exposed over here. So see this edge? It's been exposed here. I'm not happy about that. And what's causing the problem is this trace right here. Now I wonder, can I bring this up a little? So this fill is not happening here. Can I bring this up 1 and can I get the fill to fill? There we go. I got it. All right. So that makes me happy. So I've got 3 ground processes or little spars coming off of that, and that makes me happy now. All right, but that's kind of what you got to do. You got to kind of mess with it and pull things around until you're kind of happy with them. I'm just kind of centering that right now, and we want to watch that edge there. Okay. All right, zooming around, so things are looking good. Let's look over here. These are kind of some of the signals we did, right? We did that one. All right, up over here. This is kind of messy. All right, now look over here. So the tool said, hey, I wanna. And if you look at the layers here, we got a lot of funny business going on here. So look at this signal right here. It wants to be connected here. And then on this layer, it's doing this. So let's take this top layer and let's drag this down here. So it goes to the center of this a little bit better. Okay, do that. All right, so that's a little bit better. All right, and then let's come over here and this mess of things here. So let's grab this, move this like about here. Okay, and then what we could do is we could take this and we could just pull it over here a little bit. But if you look at this, this and this are going to the same thing here. So why even do that? Why don't we just take this and directly connect it here? And the tool sometimes will do this, right? It'll do these kind of connections. So let's go ahead and we could just run this straight here and then right click and we'll say repour. All right, and now what it did was it decided, oh, you want me to stop there? No, we don't. So we're going to zoom in a little bit, and we're going to go ahead and click it again, and click it right here because we know we need that to be connected. All right, there we go. So that's not bad. All right, so things are looking good. And let's get out of that interactive mode. All right, now, okay, over here, what's going on here that I don't like? You see how the signal is coming in right at the corner here? There's a lot of things that I don't like about this. So first, you always want to come in perpendicular if possible. So see how this is coming in perpendicular, or you know, here's the tangent plane is right here of this circle, and then so this is coming in perpendicular. Here we're coming in at the sharp corner. This thing's going to be kind of made on top of this, so this is not good. So what I'd rather do is drag it out, and now look, much better. So now it comes in perpendicular. We've got stress and strain is distributed nice and equally. We're not focusing anything on a sharp edge. You never want to put things on sharp edges. Here, right here, also, this right here, this is fine. But you know what? We know, what are we putting in here? I'm not sure. Is this the switch? Not sure what that is. Let's go back to the view mode and let's get out a single layer. Yeah, that's the switch, right? So the switch is there, and you know, we're putting in this big heavy switch here. So you know, why don't we just spread this out a little bit? There we go. Okay, good. All right, and remember, anything with power, we want to make these thicker. So we're going to do that later. Now, over here, not much we can do here because there's this pin here, so we can't get that fourth ground there, right? So that's just, you know, oh well. All right, now let's go over here. There's our 3 connections we made, and then that ground down there, so we're good. Okay, so now everything looks good here. Do a quick zoom in again and pan over it and look around. Anything that looks ugly, anything looks like we could distribute the signal a little bit better, maybe move that up a little bit. And you're always trying to create space so that you can add more signals later, right? And as you're doing this, you could say, well, I could have routed this better if, you know, I did this or do that. And there's a limit to how far you need to do this, right? How much time should you spend doing this before you just say that's enough, it's going to work, it's not bad. Again, that's just something you learn over time and what you're comfortable with. Okay, let's go to the other layer. So we're just going to press, we could just click here on the layers, or we can go plus and minus. All right, so we're going to go to the bottom layer, which is blue. All right. All right, and again, we've got the same situation. We've got all our LEDs here, and we've got this real tight routing, which is exactly what the thing should do. So let's start here and let's zoom in. Okay, so I do not like this happening right here, so I'm going to pull each one of these out, and I'm going to pull them out 1, 2. So let's pull them out 2 as a convention, and what we're trying to do is get that to 3, 4 to fill. All right, so 4 looks like it'll do it. All right, so 1, 2, 3, 4. And as a matter of fact, we're going to make these V sub CCs bigger, so we're going to have to pull these out even more in a moment, right? Because we're going to make V sub CCs bigger. We're going to make all those like 20s if we can. All right, so now I'm just pulling these out quickly, kind of just eyeballing it. I got a feel for it now, and I know that I can just match it to this one right here. They're all going to be roughly on the same level. All right, oops. And careful with that ground plane. It'll go bye-bye sometimes. All right. Depending on the selection logic will grab the wrong thing. Okay, and I think we got one more over here. Okay, so we're just going to leave that for a second. I probably know I'm going to have to give myself some more room here because I'm going to make this thicker. Okay, so now we got this this thing over here. So the first thing, first let's zoom out. What am I messing with? Let's zoom out. This thing, this trace right here is riding on top of all of this. All right, so what I want to do is first, let's get it up here. Let's get it up here. All right, and then let's bring this up a little bit. And then, you know, what just happened over here? All right, we brought it close to this V sub CC. I'm going to bring it down just a hair. All right, that violated something. I'm not sure what it violated. All right, and now let's move this forward like that. Okay, now we're going to move this forward, and I'm going to undo that. Grabbed it wrong somehow. And again, you got to be careful with these things. There we go. You got to kind of figure out where they want to be touched. Okay, now again, we've got these vias here, and going over here, and I like the ground to go all the way around it. All right, so I'm going to move this up. 1. Let me see if 1 will do it. Nope, let's try 2. Okay, 2 looks like it gets it done, but then we lose that fill connection. So let's go up 1 there. All right, now we still have that fill connection there. All right, then here, let's back off this one. Okay, and then you see we got that little nib right there, which I'm not too happy about. So what I'm going to do is I'm going to move this v sub cc up like this. All right, then I'm going to take this, I'm going to move this like this. It's a process, you know, and you get a, you get a feeling for how these things move around. Okay, there we go. Now I can move this up a little bit more. Give myself a little bit more room. Okay, now I can back this one off. And again, grabbed in the wrong place. Press Control Z, be careful. Got to zoom in sometimes to get things right. There we go. All right, now I want to pull this up, 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 up. There we go. All right. Now, okay, now I'm happy. I've got all the tops are all grounded. So let's zoom out. Okay, so that's better. Now we got this line here, and we got all these bottoms that are not finished, right? See that? See all those grounds? That's pretty easy. So first I'm going to start over here. Let's get this ground here. So let's pull this down, pull it down one more. Probably didn't need to go that far. All right, let's grab this here. And another thing, this is a ground fill. So as this thing is filling around, we want to have as thick copper as possible connecting all these regions, all right? Thick as possible connecting all the regions, all right? All right, so now, see now that opens up there, and now what I'm going to do is I'm going to back this out here a little bit. Okay, okay. Now we can just grab this, and this is all the way across the bottom there, all these, and we'll just pull it down a couple, and there we go. All right, so there we go. Now, everything's got a complete ground around it, so that looks good. Let's zoom in here. What do we got going on here? We got ground here, 3. We got 3 processes. Can't get the 4th, just not going to happen. We've got an island here. That's dead copper, right? It's not connected to anything. This is dead copper as well. What if you wanted to connect this to ground? What if you had to? Well, you could put a via through here, and if on the other side of it there's copper, which there is right here, you could ground that if you needed to. All right, but we're just going to leave it. All right, everything looks good. This looks good. Not much we can do here. There's some funny business up there. Let's address that in a second. These look good. I might want to come out and come down a little bit because these are, this is real tight over here. Let's see. Over here, let's oops. And again, you got to be careful what you click. Control S. All right, getting a bad feeling. Bad feeling. All right, Control S, and I'm going to commit this. Yes, which I just clicked save twice and it didn't save. All right. Okay, so this little business over here, I'm not a big fan of what's going on right here. So let's see if we can fix that. And again, you got to be careful what you click. All right, so first what I'm going to do is I'm going to get this piece here, I think, and I'm going to drag it down. There we go. Okay, repour. Now I'm going to take this piece here. I'm going to drag, press Control Z, not doing what I want. Let's try it here. Okay. Okay, this is going to make me work for it. We're going to have to do it in pieces. Now grab it here. There we go. All right, just take your time, be patient. See that? Much better. Now we don't have that little teeny tiny little sliver there. We got a decent piece there, which we could ground if we wanted to. Okay, so that's much better. I'm happy with that now. Got all our grounds where we should have grounds. That's good. We got a 4 ground there. Now, V sub CC in this ground right here. Now let's take a look here. So look what happened. Here's V sub CC, and the router decided to take it up and under and around, right? This to me is kind of messy, right? And then if you look at the other layer, we got a V sub CC here and a V sub C here, and then it's making connection on the top layer, all right? So I'm not a big fan of what's going on right here. Let's pull this around here, and let's even clean this area up because this is just really confused, all right? So I'm going to grab this, and I'm going to grab it and see if I can interactively pull it, and it's not going to have it. So let me try it here. Let me hit spacebar. Okay, not cooperating with me. Okay, fine. We'll just do a repour. So what I'm going to do is I'm going to manually do this. So I'm going to go back into home, and I'm going to go into route. I'm going to go into interactive. And now from this V sub CC here or from this V sub C here, they're both going to be the same. So we can do either one. So I'm going to grab it here. I'm going to come up. I'm going to come out. And I'm going to go like that. And then I'm going to put it right. Got to double click sometimes. Be careful, people. There we go. And sometimes it's smart enough to rip the trace up, and it was good. I'm still in interactive. Whoa, whoa, whoa. I'm still in interactive mode. Be careful. All right, much better. So that's cool, and we still have that up there. Remember, we're going to thicken this trace up. Now, what do we got going on here? I don't like this, so I'm going to pull this trace down a little bit, like that. Repour. All right. I bunched myself up a little bit here, so let's pull this thing down. All right. Let's give ourselves some room here. All right, we've got a lot of room, so let's take advantage of it. Okay, there we go. See that? There we go. Take that. That's okay. All right, and then let's take this one a little bit. There we go. And I'm eyeballing it. See the space here, just making it equal. Now I'm feeling better about this. This looks good. Okay, we've got our V sub C here. All right, now let's see over here. This looks good. Let's flip to the other layer. Looks good. Okay, so nothing going on there. All right. Okay, look at this. We got a 3 ground here. We got V sub CC. Let's just up. Okay, always grabbing the wrong thing. Okay, let's grab the trace. There we go. Let's pull the trace down. All right, good. And we're going to make this a little thicker. So let's pull it a little bit because we know we're going to make it thicker. Okay, that looks good. Now, I'm not a big fan of these direct traces here that kind of cuts across the insides of an IC because then it makes it hard to route anything else. So what I'll typically do is go out, kind of do a bend, go down, do a bend like that. That way I could run a bunch of traces. But since there's only one, the whole thing's routed, we'll leave it. But just realize that this is going to cause a problem. All right, now over here, these are fine. That's cool. Now right here, this is a little bit close to this one. I wonder if I pull this down, can I get it to ground on both of them? Can I get it to fill on both of them? A little bit more here, and I maintain that one, a little bit more symmetrical. I'm going to stick with that, all right? Another thing, I'm going to pull this back a little bit. Maybe I can get a little bit more over here. Okay, so that's good. All right, I'm happy with that. Look at this right here. So we've got, this is not a finished, complete fill. So I'm going to grab this and I'm going to pull it down, just like that. And then what I'm going to do is I'm going to take this and I'm going to pull it out, just like that. All right, and we can bring this up closer if we want to. All right, I just always much rather have that finished ground. Okay. Now over here, if you look, this is not hitting perpendicular. It's not hitting dead on. So I might want to do that to put that back there and just kind of let that piece not fill as much. All right. Okay, again, this is not hitting it here, but again, you can't be OCD about this. You have to stop at some point. Over here, I definitely don't like this, so I'm going to pull this. And I know this is V sub CC, so it's going to be thickened up in a minute. Good. All right. So that looks good. We got 3 ground there. Now we're backing out. We know these are our battery connections. There's nothing on this side. We better have a ground over here on both layers because the ground's got to go on the top layer and on the bottom layer, right? Okay, so let's zoom out. Okay, all right, Control S. Make sure this thing is saved. Okay, let's zoom back in. Let's take another look. All right, this is such a tiny board, and this is taking us a long time, couple hours or hours, right? And but this is the process. All right, and I want you to see this, so you can always fast forward if you want, but I'd rather you stay here and just hear me babble about what we're doing. So I'm just looking for anything that I missed in this pass, okay? And circuit design is an art, layout is an art. Okay, looks good. Let's go ahead and let's add the other layers back. Let's go back to view and let's take it out of single layer mode. Okay, Control S. Now let's put it to the top layer. So there's our nice top layer. And now watch this. We'll go to 3D view. All right. And now you can actually see the layers. All right. That was a bad place to grab it. Let me grab it up here. Okay. There we go. And you saw for a moment, because I rebooted this, there was red boxes showing the bounding box of the 3D objects because they were loading in. All right, now you can actually see the traces. See those traces? You can see the traces now. All right, and in this view right here, since it's a 3D view, you can't, if you press plus and minus, you can't see anything else. I wonder, I haven't tried this. Let me do Shift S. Yeah. So if I do Shift S and go to single layer mode, now I can see what the other layers are. All right. So we can kind of go through all the layers, which is kind of cool. All right. And go back to the top layer. which is the ugly green one. If we can, there's the bottom layer, there's the top layer. All right, so in single layer mode, it looks like this. So there's the top, there's the bottom. So you can see it in 3D, which is kind of cool. All right, so let's press Shift S to go back into the multi-layer mode. Okay, so that looks good. Let's go back to 2D mode. All right, let's save it. Control S, we're going to save it. All right, and let's go ahead and commit this thing again. And go back up here and we'll say commit, let it commit. Okay, good, we got all greens. Let's run a design rule check again. Did we violate, did we mess something up? I don't know. Let's check it, right? I'm not a computer. Reset error markers, design rule check. Let's hit it with run design rules. All right. Now, rule violations, 63, that's okay. How many errors? 0. Warning 0, looks good. And what's everything again? It's just these text to trace the text, kind of clearance issues that we're violating, but we have them set so large at 10 mils that we know that we're okay. Just a few of them. And then if you scroll down, you can click on every single one of them, and it gives you these coordinates, and it goes to them sort of, and sometimes it's hard to figure out. And then you can see all these R1, R2, these are all violating because they're on top of things. But this will be okay because the manufacturer can print right on top of everything. It'll look fine. All right, so let's close that. Okay, we are almost done. So we're almost done. We could be done right now. What's our last problem that we want to do is we want to deal with, what do we want to deal with? We want the power traces to be a little bit thicker. We want to try and push them up to 20 mils. Right now they're 10 or 12 mils, so we're going to push them up to 20 mils. So that's the next thing that we're going to look at. And then when we're all done, normally we would generate Gerber files and manufacturing files, but like I said, that's a whole process unto itself, and I'd rather we get all the boards done, then we'll get into manufacturing mode and generate those files so you can see how to do that. I think that's how we're going to do that because I don't want to stop. We got some momentum here with layout. I don't want to stop and go to manufacturing mode. So we're going to stop the video real quick. We'll start back up, take a break, and we are going to finish with thickening up some of these traces. All right, so I'll see you back in a minute. All right, welcome back, and we're continuing here with the PCB layout. So we're just, the videos are so long and so many of them, we have to keep starting and stopping in this marathon. And this is the first printed circuit board, which is the simple one, and it gets more complex as we go. All right, so we're all done except for, so we've got the board routed, if you recall, and we kind of cleaned everything up. So let me put it in single layer mode. I believe it's a Shift S, and then we'll go up and down and look at the layers here. So there's the bottom layer, and there's the top layer. So we went through and we kind of cleaned everything up and made sure that there was nothing funky. So now what we want to do is we want to go through, and our power rails, we want to kind of thicken those up a little bit. So what we're going to do, okay, so we want to thicken up the power rails in the design, and that's basically the last thing before we generate the Gerber files, which we're not going to do now. We're going to wait until we're all done, and then we're going to generate those all at once for all the different projects. So we can kind of do that as a process. All right, so let's take a look at the design itself here. All right. And let's just see what we need to work with. So by power rails, we mean anything where the power is flowing out of or into. All right, and so that's our V sub CC. And it's also the connections between the batteries, which we already did that. It's the switch, the connection to this bulk capacitor right here, C1. All right, and then V sub CC running to every single one of the ICs, U3, U2, and U1. And then also the bypass capacitors. The bypass capacitors, that's where if there's noise, right, the noise is going to bypass the IC and go through the capacitor because it's a path of less impedance, right? So we want to make sure that that wire is very wide also, so that the wire itself doesn't have a lot of impedance, all right? So we also want to make the track from the V sub CC connection to the bypass capacitor very thick as well. Okay, so that's what we want to kind of work with right now. And then the other thing is the LEDs, right? All of them are going to be fed from the output of this 3 to 8 decoder, all right? And now, so we've got, now technically only one LED is going to be on at once because the 3 to 8 is mutually exclusive, but it's possible maybe in a different design all 8 LEDs could be on at once. And here's a common problem that people don't think about. So say you have 8 lines right here, right? And in this case, these are sinking current, but syncing or sourcing doesn't really matter. You've got 8 lines right here. Then all of these lines go in and power something, source or sync these devices in parallel. And then all of that is funneled into a single, bus into a single line, and then here to V sub CC in this case. So we've got 8 tracks right here. Just say each track was 10 mils thick, right? 10 thousandths of an inch each thick. All right, so if there's 8 of them and they're 10 mils thick, that's 80 mils of copper. But here we might only have, 10 mils of copper for this one little V sub CC line. So you've got this kind of disparate size of copper. So what you want to do is you want to fatten up this bus because all these currents, either leaving or coming in to this common bus, right? They're all coming from all these lines in parallel, so you want to make that V sub CC fat also. Now in this case, because they're mutually exclusive, only one is going to be on at once, so we don't have to worry about that particular use case, but it's something to know when you're doing these kind of designs. For example, when you have a big bus and you've got signals running down the bus, you can have all these signals simultaneously running down the bus. They've got to have a return path, and then you got one little teeny tiny ground return path. That's why on a properly built cable or bus, you'll have signal paths and you'll have return paths right behind them, next to them. So you'll have a signal path, return path, signal path, return path. And so that's how a lot of large bus cables work if they're properly designed. All right, so we know what we want to do. We want to hit the V sub CC lines. All right. Remember, we could have let the auto router do this by creating a net class and saying we want the width thicker, right? But we don't want to do that. We want to kind of learn how to use this thing manually a little bit here. All right. So let's get back to the top layer. All right. So remember plus and minus, or we can just select it over, in this bottom little ribbon here. So let's get to the top layer, and we're in single layer mode. If I press Shift S, it'll turn all the layers on, and then we can see the text here. And that may help you. It helps me so I can see what's what. So the V sub CCs on these TTL chips is in this top right pin always. I won't say always, but most of the time. And in this case right here it is. So if we look here on this first on the timer, V plus is pin 8. Okay, so that's correct. And then V sub CC on U3 is pin 16, as we expect. And then V sub CC is pin 14. So yeah, it's the top right pin in each one of these cases. All right, so let's go through here and we're going to kind of trace the V sub CC line and make sure it's fat. So going back here, remember we did these. Now let's check what these are. So I'm going to click on this, and then over here in our PCB inspector, now right here you got to be very careful. See how it says include all types of objects? If I inadvertently had this display only track or something else, it wouldn't pick up everything. So make sure it says display all objects until you want to turn that filter on. Now we've got this track highlighted, and you can see it says the width is 20 mils. All right, so that's correct, 20 mils, and you remember doing that. All right, so now that one's 20 mils, and we've got the ground there, that's fine. Okay, so this is kind of our V sub C here, running and finally exiting right here. So if we click on this, or zoom in enough, all right, there we go, and we can see this is 12 mil. So let's go ahead and make that 20 mil. So first we got to get all pieces of it here. All right, so we've got this piece selected. So what we're going to do is we're going to hold down Shift, and let's move this over a little bit. We're going to hold down Shift and get the other pieces. So again, it puts up this dialog. Since there's multiple layers, we want to grab that piece, and then here we want to grab that piece, and let's move this over, holding down Shift again, and we're going to grab that piece. Okay, so when I zoom back, you can see we have all these pieces here. And then over here in the object inspector, it says 12 mil. We're going to set that to 20 mil and repour now. All right. So that's good. And it's showing this violation, these little X's, because it's too thick. We violated our own design rule, but we don't care. That's okay. Now, so now as we're moving around, we can kind of start to see, here's another thing. We're looking at the top layer, but the bottom layer, as we kind of hover over things, so as we hover over, see there the bottom layer, it kind of x-rays through and you can see it. So you can kind of see, oh, here's V sub CC also. So this can kind of help us. We know that we want to make this thick, right? Here's V sub CC here, all right? And there we go. So we selected both of them. We'll go over here to the object inspector, thicken that up, repour, all right? And now I can see that there's this bottom V sub CC. So you can actually, I believe you can get it. Yeah. If we click it there, see how we got that, and then if we hold down Shift again, we can get another piece of it. We keep holding down Shift. We can get this long piece of it. So we're actually grabbing through the layer, and then there it is there. And we can keep going. We can grab it here, and there it is. We can grab it here, and there's probably a more efficient way to do this, but we will do it like this, and we will keep going to right here, and we're going to select this piece here. All right, and we need this little guy. And let's not get too greedy and go too far. Okay, now that we have all that, let's go ahead. So if we back out of this, see we've got this whole little trace highlighted, and then over here, since that's what's highlighted, this applies to all of it. I change it, and then there we go. We make it thicker. Repour now. All right, and then these inputs here, these are to the potentiometers, so we don't really care. These are just going to be low current signals, but this is the actual routing path of V sub CC, so we do want this to be thick as it's routed through the circuit. So another place it's routed to the circuit here is C2, so here we have one of our bypass capacitors, right? So we need to thicken this up, so I'm just going to go right here, select it, and I'm going to hit that with a 20 mil. All right, repour now. And you can kind of see the process here. And we've got another V sub CC coming right here to this other pin 4. So we'll go ahead and select that. Again, we'll hit that with a 20 mil. And again, I could just do this with time lapse, but I really do want you to see as I'm doing this some of the commentary that I make, because sometimes I see things I want you to kind of see what's going on. Anyway, here's another one here. And again, we could just go to this layer and we can see here's V sub CC here, right? So I'm just going to select that. And it's a little easier if you're on the layer because we're not going through layers here. All right, and then now this is kind of interesting. So you see this, I can't really see. So, okay, so see what's happening here? This trace, let's get rid of the text. This trace is hitting the via, so it's making contact, but I don't like that it's not hitting it in the dead center here. So that concerns me. So what I'm going to do right now is I'm going to go ahead and make this a 20 wide track. So let's go ahead and do that. All right, so we're going to make that 20. So we fatten that all up. Okay, fine. But now I don't like what I'm seeing here. And so let's see if we can drag this up into here. There we go. All right. And so that's not bad. And we put it a little bit more in the center. All right, there we go. And again, depending on, if we go back home, we're in 5 mil snap grid. Depending on the grid snap that we're in, we can or cannot move this exactly where we want it. But again, this is much better. So that makes me feel a little bit better now. All right, so that's good. Okay, so now if we back out, we can start to see our V sub CC here. All right, going to different places. All right, and let's see. So this is another trace right here that V sub CC is taking. Right, there it is there. Okay, so and that's 20, so that's okay. Okay, then we're going to go over here, And we can see we've got some V sub CCs here. Now, a lot of times, this is the power of V sub CC, and this is just, I believe we're pulling this pin 13 up. So we don't really need to make that thick, but it doesn't hurt. All right, it doesn't hurt to do it. So let's go to this layer here. Let's select that, and we'll make that 12, or excuse me, 20. And remember, the whole idea is you have the V sub C track, which is kind of routing the power, all right? And so this routing is happening, it's happening here, it's happening here, it's happening here. This is not routing power, it's just this is an offshoot of it, but it's not going to hurt to make it thick also. Why not? All right, so let's get this one here. All right, and hold down shift, hold down shift, hold down shift. Looks good. Let's make that 20. Okay, and we're almost done. All right, and so now here's some more V sub CC. It's on the other layer, so we'll go up top. Oh, there it is right there. Okay, I'll click it there, holding down shift. And be careful because these tracks, they're in a lot of little pieces. As you can see, I'm trying to select them. Let me zoom out. So now we're going to hit that with a 20. Okay. All right, looking good. And alrighty. And zoom in here. So there's V sub CC. Now, this is where V sub CC exits, and it goes and snakes to each one of the LEDs. So here it is here. So there's V sub CC right there, right? So if we, now we should be able to, there's of course a way to select a track or a net, and then we could highlight the entire thing. But net actions, show nets, hide nets, there's definitely a way to do that. But anyway, what I'm going to do is I'm going to just piece by piece, I'm going to go and make these all 20 right now. Okay, so I'm going to speed the camera up and do that. All right, so we'll be right back after we do that. Okay, so I've got the entire V sub CC track here highlighted, and then we're just all in one fell swoop. I'm going to change that to 20 mil, and it does it, and we're good with that. Now, let's see. Is there something else? Yeah, oh yeah, I wanted to show you this. Take a look at this. And I showed you this before, this link. So it'll be inside of the notes, the text of it, but it's a little Hackaday post, tips for using Circuit Maker, and I've showed this to you before. But there's a bunch of good little tips here, which have a lot of little things that are real lifesavers on this page. And it's, hackaday.io project 7155 logs, blah, 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 blah. But if you just type in tips for using Circuit Maker Hackaday, I'm sure Google could find it. But anyway, you'll have the link for it. Read through these, and I can't remember these all the time because, again, I don't use this tool all the time. But those have some good tips in there. Okay, so now we have that. So now we are pretty good here. We've got V sub CC all highlighted here, and we're looking at it, and we've thickened it up in all these places. So now what we want to do is let's go back to that bottom layer, and let's just kind of hover on V sub CC, and we can see all these different paths that it takes when we hover over it, right? And it looks like we've got them all thickened up. So that's good. All right. And now we go back to the circuit. Let's go back to the circuit and see, is there any other places? Not really, because we power this IC, we power this IC, we power this IC. We have the source power for all these LEDs. This is one V sub CC. And the only other place maybe we might miss something is SW1 and C1. All right. But if you go to SW1 and C1, let's turn single layer mode off. All right. So that's what, Shift S. All right. And now we can see everything. We can see the text. So SW1 and C1. So if we look at those and zoom in, and you can see that that line has been thickened up, and that switch has been thickened up. And there's only one place that goes into that switch, which is this net right here coming off the batteries, which has been thickened up. All right. So as far as I'm concerned, I think we're done with that. So let's put that top layer back on so we can see. All right, let's zoom out. All right, and again, it's very hard to see the circuit because it's so wide and very narrow. All right, so that's it. Let's go ahead and, if you haven't been hitting Control S constantly like I do, let's go to our Magic Wand Final Design. Let's commit the project. And once it's committed, then we are going to switch it to 3D view here. 3D view, cool. All right, let's bring it up here. Let's zoom in a little bit. And let's swing it around a little bit. Play with this little funky 3D thing. Zoom out, grab it, pan in, pan out. Get it just how we like it. Oops. Okay, so, and again, if you zoom in, you can see the tracks. So if you zoom in, you'll be able to see the actual tracks. And then we can also go through the layers on this. If we we have to go to single layer mode. Now we can do it, and then we can see all the different layers. All right, and our two signal layers, of course, are that one and that one. That's the top and that's the bottom. All right, so let's go out of single layer, Shift S. Okay, so again, why are these parts missing? They're not missing. There's just no 3D models of the parts, right? So we could go make them if we want, but at least these have 3D models. Okay, and this capacitor and switch do. All right, and so that's about it. All right, so good. So let's go back to a 2D view. All right, so now what we're ready to do is, again, we're going to run the design rule check. So we'll go to design rule. Let's first reset error markers. We'll go to design rule check, and we're going to run the check and let it do its thing. Okay, rule violations 120. What we really care about are errors and warnings. There are no errors and warnings. All right, but we've got these rule violations, and the only one I really care about is, where is the one that I really care about? Unrouted nets, right here. All right, and short circuits, obviously. 0. So all these other things, there's two classes, silk to silk clearance, and then silk to solder mask clearance. Who cares? All right, unless you care. If you care, then you care. All right, so let's close this. So now this board is ready for manufacturing. We can generate the Gerber files and all that. So now let's do one last thing here. So I want to do one last thing. Now what I want to do is I want to decorate this a little bit. So if we go look at our working copy, which is the forked copy, which we made a copy of the original. So all I did here was I put the off and on. So I put, and this switch is a little bit different. I put on where the switch direction would be on, and then I put off where the switch direction would be off. And then I just said sequencing Magic Wand version 1.0. Sequencing Magic Wand version 1.0. Okay, so we can call this thing anything we want. And we didn't put any other annotation on that. And then here's the batteries, right? You could put something on there if you want. Okay, so sequencing Magic Wand version 1. All right, so let's just close that. And let's go here, and let's just add some text here. So where do we do that? Again, you got to go kind of go through these things and figure out what's what. And in home here, there's this place, right? And we want, what do we want? We want text. Okay, and where do we want the text? Well, I surely don't want it on the outline layer, so I want it on the top layer, the bottom layer, the outline, the assembly top, assembly bottom, all these different things. Where do we want this? And again, these names of things, depending on what tool you're using, you got to figure them out. We want the top overlay. The top overlay and the bottom overlay are the text layers. Okay, so the top overlay. All right, so let's kind of zoom in here, and we'll zoom out a little bit. Okay, and here we go. Let's go back to text mode. All right, and we can place that text, and let's just grab it, and we will move it, and then we're going to mess with it right now over here. Or we can, let's zoom in so we can see this. If we double click the text, we can get it here. So we can say sequencing Magic Wand version 1.0, top overlay font, and then true type font, stroke font. You can select either one. I'm sure there's a way to get all the fonts. My other tool, you can use any font that's in the system, and these fonts are rasterized, so I'm sure there's a way to get this to do that. And then the stroke font, in this case, there's only a couple of them, default, sans serif, and serif. So not a lot of variability there. Anyway, we'll just leave it the way it is. But the only thing I do want to do is I want to mess with this height right here. So that's 60 mils, 60 thousandths of an inch. Let's do 100 mils. Okay, and that kind of works out. That kind of makes it what we want. And double click it again. And let's see, is there anything we could change the width a little bit if we want, make it a little bit wider. All right, so maybe we can go here and we can say, oh, do that. Okay, all right, and then and then that's that. So now what we can do is we can take this right here. We can control copy and paste, and let's do this. Let's just change this to on. All right, there's on. All right, so now when is the switch going to be on? So the switch is going to be on. Let's look at the design real quick. And this is always a great place to make a mistake. It's just a very easy way to make a mistake. So pin 2 is in common. So the switch has 3 leads coming out of it. So pin 2 is the one in the middle. So that's the common. So we've got the power going to pin 1 and then exiting out of pin 2 here. So when the switch is on top of pin 1, 2, it's going to be on. When it's on top of 2, 3, it's going to be off. So 1, 2 is on. 1, 2 is on. All right. So let's go back here. So 1, 2 is on. All right, there's pin 1, there's pin 2, there's pin 3. All right, so it's to the left. So on is to the left, and we'll just, maybe put it right there. And then let's go ahead, we'll select that again, copy, paste, paste, and we will change that to off. And it's up to you if you want to make them all uppercase and strong like that. And now maybe this is a little bit busy, so maybe let's move this SW1 right here. Okay. And the potentiometer reference designator, why don't we put it there? And the potentiometer reference designator B, why don't we put it there? All right. Okay, and Control S while I look at this. Okay, and so now we can go through this and look at this another time and make sure everything's good. But we'll re-verify this again when we go to manufacture it. So for now, I think we're done. All right, so let's go ahead and let's commit this design one last time. I just pressed Control S to save it. Alrighty, cool. And now let's go press 3 here. Let's get it in 3D mode. So that's it. So there is our magic wand. You turn this thing on and hopefully it should do what it needs to do, adjust the potentiometers for the speed and all that. And then of course the representation is showing all green LEDs. You can put whatever color you want, white at the tip and all that. But there's our complete design. So we came up with the design, came up with an idea, we implemented the schematic, we looked at the schematic, cleaned it all up, we created a printed circuit board, we changed the size of the circuit board, we laid out the components and the parts to make them nice and neat, and then also to have them collected into functional blocks. Then we routed some of it, then we auto-routed the remaining part of it, then we went back through the auto-routed part, and then PCB layout, we cleaned it up, right, knowing what we know about PCB design. Then we went and fixed some of the power rails and made them thicker. So that's it now. We don't know if this is going to work. Why? Because we didn't test it. We're just hoping that it works, looking at the schematic over and over and over and checking the data sheets and just using common sense, and then maybe have another engineer look at it and say, hey, you forgot a capacitor, you got these pins flipped. So that always helps. But at the end of the day, you really want to build a prototype, and check it. Now, a lot of engineers, this is the prototype, So what they do is they have someone else will go build the PCB for them. They'll say, here's some files. Go build this for me and check it. They'll build it, debug it, and tell the engineer. And so, like at a big company, you may be able to get away with that. But if you're like me and you're doing this stuff yourself, you really can't do that. You've got to make sure the thing works, because you're going to waste a lot of time and money manufacturing a PCB. Even if you do 3 or 5 of them, then you got to stuff the thing. So what I like to do is I like to build these on our solderless breadboards or wire wrap boards, or at least simulate, and then make sure we know what we're doing before we build it. But this is simple enough that I think it's going to work. I'm about 95% sure it's correct. So if it's not, we will find out at some point, or you will. All right, so that's it. So this has been the first PCB project, and so hopefully you like this. And I know it was long, seemingly long, but it really wasn't, because I already had done the design. If I had to think of this as I was doing it, obviously it'd be a lot longer. But I want you to see the process, and so we're going to do this again now. We're going to do it again, and the second project we're going to do is let's this mode here is a little bit funky. Let's get back to the main projects window here and go here. All right, and we'll go to My Projects. And which one are we doing next? We are going to do, I think we're going to do, yeah, the 555 timer organ. So this is what we're going to do next. Let's just take a quick look at this, and then the Simon Duino is the last one, which is actually pretty cool. All right, we'll go to Open Design. Okay, so the design is over here, so let's go ahead and open up the schematic. All right, so this design actually is simpler in some ways and more complex in other ways than the previous. And we're going to obviously do a whole video series. I'm just going to give you a minute kind of what's going to go on here. But the difference in this one is we have a voltage regulation. So we've got a battery, a 9-volt battery in this case. We've got voltage regulation, so we're going to put an actual voltage regulator. We're going to have a power good indicator. And then we're just going to use a 555 timer and then precision resistors set up in the RB resistor position of the 555 timer to generate a square wave that's going to be a diatonic scale, which is a 12-note diatonic scale if you're musical, and if not, I'm not musical, so I have to always look these things up. But anyway, and then we're going to take that signal and we're going to put it into a little amplifier, which we've made, right? Single transistor audio amp. This is a current amplifier using a single transistor, and then to a speaker, and then that's that. And then the result of this is going to be a little organ. And these are like, you might see these as kits. You can buy these, and I surely did as a kid. And then here's a layout of it. And you can see the white keys and black keys kind of here. I've kind of drawn here. That's another thing we'll play with is drawing. And then we'll go in 3D. And I think we are we in single layer? Let me see here. Shift S. There we go. Yeah, it's in single layer, so let's go there. I wonder why it's orange like this. Not sure. But anyway, so this is what this thing will look like, which is pretty cool. And then we'll have a bunch of little switches here, momentary switches, put your battery in there. And then this just represents where the speaker will go, so you have to glue it or affix it somehow. And then we've got some mounting holes in the 4 corners. So this will be a little organ, so that'll be pretty cool. So it's simpler in some ways and more complex than the previous design. So this is what we're going to do next. So we're going to go through that same process of making a working copy of it, and then we're going to fork a working copy. So you're going to fork one and I'm going to fork one because I don't want to mess with the original. And then we're going to create a new project where we're going to kind of copy it just like we did. Okay, so that's it. So hopefully you had fun with the magic wand thing. We are done with that at this point. And so now we're going to go in and do the organ. All right, so I will see you in the next video. Bye. All right, everybody, welcome back. And we are continuing with our PCB design lecture series here on our projects that we're doing in Circuit Maker. So we finished up the magic wand. So you can go back and look at that. We just finished that up. We did not generate Gerber files and manufacturing files. We're going to do all that at the same time so we can kind of get good at it rather than just do it once and then go back to design and then do it again, and then go back to design, do it again, we're going to do it all at once 3 times. That way we can kind of get the hang of it. Anyway, so now what we're going to do is we're going to do exactly what we did before. We're going to look at this 555 timer organ, all right, and we're going to fork it, make a copy of it, and then what we're going to do is then we're going to start a new project and kind of make a copy of the copy itself, or work from the copy so we have something to look at, but we don't want to mess with the original. So you should have Circuit Maker launched, and you can do all this project management stuff. You can do it here in the application itself, or you can do it, I believe I have Circuit Maker open, yeah, or you can do it in the website or the web view itself, online. You can do either one, either way works. All right, so since we've got the tool open, let's just do it inside the tool. Okay, so let's go to we've logged in, right? So you should log in under the My Account stuff. Let's go to My Projects. All right. And what we want to open up here is this 555 timer organ. All right. So I've already got a copy of it here, 555 timer organ that I've opened, but we need to fork this because I don't want to touch that original copy. All right, so when we click on it, we get to this view right here. We can open it, which I've already done. Follow, edit, delete, fork. All right, so we want to fork it. All right, and then all we're going to do is, instead of calling it 555 timer organ copy, we're going to call it, and I don't like dashes, we're going to call it work copy. All right, work copy, create. Okay, and now we have this work copy, which is cool. All right, so now what we're going to do is we're going to open this design, and the copy of this will populate all these different things, but it's going to take some time to get through the system. So when you look at this and do it, it may happen faster, slower. So, but right now the cloud is doing the cloud thing. All right, so we open design, and now notice we're still in this view right here. And now we can see work copy, and then here's the original copy, and then here's our magic wand. I can just minimize that right there. So we've got the original 555 timer organ, and then we've got this work copy. All right, so that's good. So now what I'd like to do is let's go ahead and take a look at the documents here. All right, let's open this one up, the schematic and the PCB. Okay, good. And let me zoom. And as a matter of fact, so now we've got a little bit of confusion because we have these same file names here because the 555 timer organ and the 555 timer organ work copy has the exact same file name. So let's just close everything here so we can see what we're doing. All right, now this is the work copy. So now if I double click here and I double click this one, good. Okay, so, and then now what we're going to do is we're going to create a new project totally blank, and then we're going to use this working copy to kind of go back and look at what it is we're designing. So again, let's take a look at what this thing is. So here's what the PCB ultimately is going to roughly look like. We're not going to copy it exactly, just like with the magic wand. We're going to kind of, you know, roughly try and copy it, but we want to do this in real time. So basically there's a battery. There's some power regulation. We're going to use our handy dandy 555 timer. We're going to have an audio amplifier, and then we're going to have a speaker. And then we're going to have 12 buttons, which are the notes on a keyboard or piano. All right, and this is going to be a C4 diatonic keyboard, C4 meaning the fourth octave of C, diatonic keyboard. We'll talk about that. I'm not a musician or music kind of person. I like music, but I don't play anything. But I'll explain this to you if you don't understand or know anything about music theory stuff. So this is kind of what it's going to look like. Let's go in 3D. And I just pressed 3 for 3D. So pretty cool, right? And then you can see I kind of drew the keys, the white keys and the black keys. And my idea was you could run some plastic around this with your 3D printer, or you could go out on a 3D printing hub system with a 3D model and have it printed maybe for $20 or $50, and you could put some plastic around this. So there's some mounting holes in the four corners. There's our switch. And so this will be pretty fun. If you're into electronics, which obviously you are if you're taking this class, and maybe you never learned electronics or you wanted to, you know, refresh your memory here, but maybe as a child you probably, or as a teen, you may have made these kits where you know, made a blinking light or a siren or a little organ. So that's kind of where this idea came from, and it's just a little bit more complex than the magic wand. This is useful. This is something you could actually, you know, do something with and play some music. All right, let's go look at the schematic. So let's take a gross look at the schematic first, meaning the whole thing. All right, so we're going to have our battery here, and then we've got a voltage regulator here, and we've got our power outputs and our power good indicator. Then we have our 555 timer, and then what we're going to do with the 555 timer is we're going to use it as a tone generator to generate a square wave, and then we're going to take that square wave and we're going to amplify it, and we're going to put it through the amplifier and then out to a little speaker. And a speaker meaning this kind of thing, right? One of these speakers, right? So that's what the project is. Now, let's zoom in a little bit here and take a look at some of the things. So we've got our battery, which we're going to use a 9-volt battery. Now, the thing about 9-volt batteries is they don't provide a lot of current. And so they've got a higher voltage and they've got a kind of a lower current. If you open up a 9-volt battery, what's inside of a 9-volt battery typically are six quadruple A batteries. So most people are familiar with double A, triple A, C battery, D battery, but we've talked about there's also a quadruple A battery. And the quadruple A has just got a smaller diameter. So you put 6 in there at 1.5 volts, you get 9 volts. But they're all in series. Because they're in series, you get the voltage, but you don't get any more current. So basically you get the current drive of one quadruple A battery, which is not a lot. You know, couple hundred, few hundred milliamperes, and then very quickly the battery will heat up and then that'll diminish. So the point is, this will work off a 9-volt battery, but it's not going to work forever, right? Because we're going to draw a good amount of current with the amplifier and the speaker. However, if you use a modern lithium-ion 9-volt battery, then it'll last you know a good amount of time. All right, so like Energizer has a lithium-ion 9-volt batteries, which are totally awesome, primary cells. So that's what I recommend. Anyway, so we've got our battery. And then we've got a switch, on-off switch. Always put on-off switches in your designs if you can. I'm sure you're like me, and I hate things that you just have to plug in, and then that's the only way to turn them off is to unplug them. Put a switch on it. It's like the funniest thing you see in all these products, really complex products, and they forget an on-off switch. It's like, are you kidding me? All right, then we're going to go into a voltage regulator. This is not a 7805 linear regulator, which is inefficient. This is an LDO, a low dropout regulator. And remember what LDOs give us. First, they're more efficient because the voltage that you input and the regulation voltage only have to be different by a small amount, or only have to have a differential of a small amount, and the regulation can be maintained with only a couple hundred millivolts over the regulation voltage as the input. So this particular LDO, I think, at 100 or 200 millivolts, it'll maintain regulation. So what that means is, as we drag on this battery, 9 volts, 8 volts, 7 volts, 6 volts, 5.1 volts, we'll still have regulation out here at 5 volts as we really beat this battery up. If we were to use a more primitive 7805, we require, a couple whole volts over our regulation voltage, which means that as this hits 5 volts is our regulation target, we'd have to have at least 7 volts on the input. So anyway, remember, use LDOs, use modern regulators. If you're going to do a linear regulator like this instead of a switching regulator, make sure it's an LDO and make sure it's efficient. Anyway, we'll look this part up. We've got our capacitor on the input. We've got a couple capacitors on the output for storage and for bypass. Then we've got some labels here. We're going to see how to do those things. We've got our power good indicator, so we can see the thing is on. We got a couple little test points here. So all these test points are little pads of copper, so we can put our probes on it and check things, voltages, signals, and whatnot. They're always useful. All right, and then so the power is generated at V sub CC. And we take that and we put that into our U1 here, which is our clock generator, which is our 555. Again, this is our CMOS version. And again, since it's a DIP package, right, you could put anything you want in there. You could put the CMOS version, you can put another version, you can put, whatever, as long as it's a 555 timer. But we want the 555 timer that can operate at lower voltages. As we lose, here's an interesting thing, as we lose power here and we lose regulation, at some point the regulator will stop regulating and the battery will just basically flow directly through the regulator with no regulation as it goes to 4 volts and 3 volts. This project will continue to operate because this clock generator is CMOS. It'll run down to like 3 volts and still run, so which will be kind of cool. All right, so we've got a 555 in normal astable or astable mode, so it's just an oscillator. But what we're taking advantage of is we know that, and remember this is the little, you can put notes and text, right, in your PCB projects. So this kind of explains everything. You need to read that, but I'm not going to read that for you. But if you recall, there's 3 variables we need to mess with, RA, RB, and RC. And those are the resistors. RA is the resistor that goes from 8 to 7, then RB is from 7 to 6, and then 6 goes to ground through a capacitor, and that's called C in the formula. So these are the modeling equations that model the frequency here. And there's T is the period, remember that, and then F is the frequency, 1 over T. The duty cycle is important, and the duty cycle is RA plus RB divided by RA plus 2RB, and what we want is, ideally, we want a 50% duty cycle here so that the signal is high just as much as it's low. And that's going to just give us a better sound. The timbre of the sound will be better. Now remember, we're putting a square wave through here, and a square wave is really an infinite series of sine waves, right? So it's not going to be a pure sine wave. The interesting thing is if you take a sine wave and put it through one of these little speakers, which we did, I believe, it sounds really tinny. But if you put a square wave, it sounds richer because, of course, you've got the primary sine wave, whatever that frequency is, say 440 hertz, then you have harmonics of it because the square wave is built up of a sum of sines, and it just sounds richer, right? And some of these words, it sounds like coffee description words that people use to describe music and tones. Anyway, so we're putting out a square wave. Here's how we model it. So then the question is, well, how are we going to get all these different frequencies? Well, like in the magic wand, what we did was we just put two potentiometers on the RA and RB, and we just let you adjust them, right? That was it. But in this, we obviously don't want to do that, and we want to be very precise. So what we're going to do is we're going to put precision resistors in the circuit for RA and RB. And then what we're going to do is we're going to use switches, and then check this out. So so this is RA, which is R5 here in the design. It's fixed, all right? So RA is fixed, and in this case, it's at 1.4K. And so this is RA in the formula over here, right? So that's that RA right there. Now, all of these, so as we close this switch, each one of these switches, it switches in one resistor into the circuit as RB. And then whatever RA, and then this would be RB, and this would be our C, whatever these values are, that's going to give us our final tone. Okay, and then when we let go of the switch, we can press this one and so forth. Now, no one says you can't press these simultaneously. Then what's going to happen is the resistors are going to add in parallel. You're going to get a different tone. So just press them singularly. You're not going to get multiple tones out ever. And you can't hurt it, so don't worry about it. So now, once we have all these resistors calculated, but we have kind of two things we want to optimize. We want to pick an RA and RB such that the duty cycle kind of stays near 50%, and we hit our target frequency for the note within a very small amount of error, right? So we've got these things we want to optimize. So there's a lot of ways to do this, and one of them is with an Excel spreadsheet, which I've created for you. So I'm going to show you that in a second. And that allows us to kind of play with the values to kind of say, well, if we pick RA as this, then what would our RBs be? Can we get those resistors, and so on? And then, of course, the calculations are going to come up with a resistor value that's a precision resistor, like a 1% or 0.1%. That we'd want to get tolerance. And the question is, can you find that resistor? Can you buy it? If not, you have to kind of make it with a couple resistors. We're not going to go too crazy. We're going to try and hit these targets. So like, 27K, we can definitely find that. 18.7K, maybe we can't find that. Maybe we can find 18.6. That's what we put in there. You get the point. All right, it's a toy. It's not got to be perfect. All right, and now when the signal is finally generated, it comes out of the out pin as usual. And we got another test point here, TP sig for signal. And then that's going to go capacitively coupled into one of our amplifiers. We've seen this, right? This is one of our current amplifiers, right? Based on a NPN transistor. And we've got a big capacitor here, 100 to 220 microfarad. This is going to be our storage capacitors because we're going to draw a lot of current as this thing fires. And then we've got a 10K and a 1K, right? And this is for setting our bias point, right? We want to set our bias point. And then we've got our speaker is right up here from the power into the collector. And then we've got a diode D1, which is our kickback diode because we've got this inductive load here and we don't want to burn out the transistor, right? Remember all that? All right, so we've got our amplifier and that should take care of that. So this is our design, okay? And let me zoom out a little bit. There we go. So that's it right there, okay? So now let's go ahead and let's create another blank project that we're going to start copying this into. And remember, we're not just going to copy it, we're going to kind of go through the whole process, just like we did with the previous Magic Wand design, but a little bit faster now, because now you know what we're doing. All right, so let's do that. So remember, so how do we make a copy here? So first we got this working copy, and let me press Control Save here, and save project, and commit project. Just make sure there's nothing funky going on with the cloud thing. Okay, we've got all little green little icons here, so now we're good. Okay, so now all I want to do is I want to create a new project. So we're going to go up here, and we can go in this project here, and we can say we don't want to do that. We can go to File. Here we go. We want to go to File, and we want to go to New Project. Okay, so right now the project, we can put it in the sandbox, or we can put it public. For now, we'll just put it to public, and we need to change all the licensing and all that later. But what are we going to call it? So we want to call it the exact same thing. So we're going to call it timer organ, and use the same kind of naming convention. We'll call it final. All right, final design, as we did with the Magic Wand. So that's kind of the way we're going to do this. The description and all this stuff you can do later. And this is just my copy of it, right? You're going to do your own, so you can do whatever you want. Okay, and so all this stuff here, right? All these pictures and all these links and all the licensing and all that kind of stuff, right? You can set all that later. We're just going to say save. We're done. Okay, and now this is the 555 timer organ final design. We're going to go to Open Design. And I know I've said this many, many times, I do not like webby programs. This is very webby to me. This is literally a web interface stuffed inside of a window. I am not a big fan. All right, so anyway, 555 timer organ, final design. Now what we're going to do is we're going to right click on this, and we're going to say add new to project, or we can also go up to this project thing here, and we can say add new schematic, add new PCB, whatever you want to do. I like right clicking. So now we're going to say add new to project. So we want a schematic. Now, what are we going to call the schematic? So we're going to call the schematic, let's use the same, as a matter of fact, let me escape off that. Let's use the same convention we did with the Magic Wand. So we just called it Magic Wand Final and then schematic, Magic Wand Final and then the PCB. So let's just do the same thing here. We'll call it 555 timer organ final. We'll just use those kind of naming conventions, all right? All right, so we'll come back here, and we're going to call this 555, and I guess let's concatenate it. 555 timer organ final. I don't like spaces, not a big fan of spaces in file names either, but these days it's kind of like everything is like that. And this time, let's create a PCB right off the bat here. So we're going to say add new, and we'll say PCB. Okay, last time we created it after we were all done, but we'll just create it right now. It'll be blank, there'll be nothing in it. All right, and we're just going to go back to our schematic. Okay, so here's our schematic. And first thing that we notice is the informational block down here in the bottom right is completely occluded. It's like this really big thing. And the question is, we're going to need a little bit more space. So let's look at our working copy here, schematic. And you can see this one's a little bit bigger, right? So let's go ahead and let's make our document size bigger. Okay, so here it is here. Where'd it go? Right there. Let's just close this. Let's close this PCB because it's going to confuse us. Here we go. All right, so here's what we run right here. Now the question is, where do we make this bigger? And it's over in projects. I believe it's in project. And let's see, template. Yeah, so over in project, and then over in this little thing here, content, great name. No idea why that's called that. Go to general templates, and these sizes here, they get larger and smaller. So let's just pick, let's say A2, just this document. All right, and let's see how we like that. And A2 is way too big, right? So let's go here, and let's go A3. Okay. And A3, that's kind of big too. All right, let's go A4. Okay. A4 is good, and we can always make it bigger or smaller. All right, Control S. At least now we can see this information here. We can say circuit maker. Now, one thing that I think I've mentioned to you is there seems to be a bug in the software. If this template is too small, if it clips anywhere here, none of this information prints out. Don't know why, right? It seems to be a bug. I'm not going to mess with it. I don't care. All right, so here we go. So we got our blank. So let's get started. Let's do some of the preliminary things where we're kind of, we're talking about this whole 555 timer and reprogramming its frequency on the fly by using different resistors. Let's get into a little bit of music stuff right now, okay? So let's go ahead and talk about some music theory stuff, okay? Okay, so what we have on our screen right now is a scale, basically musical notes. And the URL is right here. Of course, I'll put this in the information. It's, phi.mtu.edu/tilde suits/notefreaks.html. There's a million pages like this on internet that have frequencies of all the notes. All right, and so what I wanted to do was kind of do something that has some notes that sounds fairly reasonable. So, I have taken a piano lessons in college for like 5 minutes and a class music appreciation. And so one thing that I know is when I usually play the piano, I don't like going down here in the low part or in the high part. I kind of go in the middle. That kind of sounds good. And that's around middle C, it's called, so, or C4. So that's kind of where I wanted to base our notes on. Now, a normal keyboard has a number of keys, right? And the kind of scale that we're going to be talking about is based on what's called the diatonic scale, and you can Wikipedia that if you like. But here's a keyboard, right? Here's a keyboard, and here, just bear with me, here's C4. So if you had a keyboard, and some keyboards have more octaves and less octaves depending if they're full size or whatever. But this is kind of your standard keyboard or piano keyboard. And here's where C4 is, and here's C3. Here's C5. So each one of these is basically a set of notes from C4 all the way up to here. Then another set of notes, C5 all the way up to here. Then C6 all the way up to here. These are the different octaves, right? So C4 is kind of a good middle of the road. If you only could do one little set of keys, C4 is my choice. All right. Now, one thing that you see here is there's some asymmetry. So see, you got the white keys, then you got the black keys. The black keys are called the sharp keys, and then the white keys are the flat keys. And so there's 2 of them here, then there's 3 of them here. So there's this asymmetry going on. It's just the way it is. And then the way that you read this is this would be C4. This is C4 sharp, D4, D4 sharp, E4. Then it just jumps, where there's no sharps, to F4, then F4 sharp, G4, G4 sharp, A4, A4 sharp, and then B4. And then you can see the names of the notes are up here above. Okay, so this is what we want to copy. We want to take this little slice of keyboard and we want to mimic this. So we need to know what are the frequencies of these things, right? What are the frequencies of these things? All right, so that's our next problem. So that comes back to here. So we want C4. So we have this note scale here and we scroll down until we find C4. All right, and then that other link right there, obviously I'm going to give you that link. It's Piano Synth, but you can just type in piano, keyboard, frequencies, graphic, image into Google and get something. Okay, so here's our C4. Here we go. So there's C4 right there. And so C4 is 261.63 hertz. Then C4 sharp is 277 hertz. D4 is 293 hertz. D4 sharp, 311, and so on and so forth, all the way up to C5. So basically we want everything from here to here. All right, so we want to mimic all of these frequencies. Now, how many notes are there here? Okay, it's a diatonic scale, it's called. So let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's diatonic scale, 12 notes. Now here's the interesting thing. Every note, so again, you have to read up on Wikipedia the whys of all this, but every note is the so the next note, say if you have a note C4, 261, the next note in the series is the 12th root of 2 times this frequency, 12th root of 2. So if you don't have a heavy math background, you might not even know what that even means. So let's take a quick look here. So let's get our handy dandy drawing thing here. All right, can everyone see this? Good. Okay, so if I were to say, what's the square root of 100? That's pretty easy. What number times itself equals 100? That's 10, right? Okay, now, so there's this implied 2 here, all right? So this symbol here is, the radical symbol, all right? And this just means you're going to take a root, but it's always implied to be 2. So in school, if you never do any kind of advanced mathematics or whatever, you'll never even know this, but there's an implied 2 there, but you can put anything you want. So we can do, for example, and we'll do this in red, let's do the third root. Make that 3 a little bit bigger. Let's do the third root of, say, 1,000. So what's the third root of 1,000? That would be what number times itself 3 times equals 1,000? Well, it's 10 again, right? Because 10 times 10 times 10 times 10 equals 1,000. Pretty easy. Let's do a harder one. What is the third root of 8? Third root of 8. All right, those that think in binary will realize this is 2, because 2 times 2 times 2 equals 8. All right, let's do one more since we're in the computer, since we're in the mode here. Let's do the third root again, since I like third roots. Let's do let's do something more interesting. Let's do the 8th root of 256. What's that? 8th root of 256. So what number times itself 8 times equals 256? How about 2 again? So, and this, I'm just working in binary, right? 2 times 2 times 2 times 2 times 2 times 2 times 2, 1, 2, 3, 4, 5, 6, 7, 8. Let's check it. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64, times 2 is 128, times 2 is, yes, 256. Okay, so that is how this rooting works. So whatever number you have up here, that is means how many times I want whatever the result is multiplied times itself to equal the number under the radical sign. Okay, so all we need to figure out is what is the 12th root of 2? 12th root of 2. All right, so let's just kind of do it in our heads, right? We can do this iterative process. How about 1? So 1 times 1 times 1 times 1, 12 times is definitely not 12, it's 1. Well, how about 1.1? 1.1, right, times itself 12 times, or I could say 1.1 to the 12th power, right? 1.1 to the 12th power, doing it on my little calculator here, is 3.13. That's no good. Let's try 1.05. 1.05 to the 12th power. All right, that's 1.79. So that's getting closer, right? So you could see we could sit and iterate until we converged on the answer, or we could just use the calculator to do this. So what we want is you have to find the key on your calculator that's going to look something like this. And I'll put it up here on the screen. But what we want is, so you should have on your calculator a little button that looks maybe something like this, right? Or it might look like this. And this means, x to some power, right? Now what we want is kind of the opposite of this. So we want something that looks like this, where we can plug in these two values here, all right? So on my calculator, I have many calculators sitting here, but let me see here. So it's right, and you probably can't see this, but right here, this button, right above my finger, that's the button. All right, so we're going to compute what the 12th root of 2 is. All right, so what I'm going to do is I'm going to get that little function by shifting. All right, and then I'm going to put 2 here, and then I'm going to put 12 here, and this is what it looks like. Can you see that? Let me see. Maybe. All right, and then I'm going to hit equals. Oops, I did it backwards. I wanted the 12th root of 2, dummy. All right, do it again. Try it again. We want 12 there. There we go. And then we want 2 there. All right. Okay. So that's what we want. All right. And we're going to hit equals, and we get 1.059. 1.059. So 1.059, let's write that down. where am I here? 1.059 and a bunch of decimals. So we could call it 1.06 if we wanted to. But as a matter of fact, I'm going to keep it fairly accurate. So I'm going to leave it like that, 1.0594. So check this out. All right, I'm just showing you how this stuff all connects, right? So you know. So 261.63, I say to you that if I take that number and multiply by the 12th root of 2, we will get this number right here, all right? And I think you can just see that's true. So times 261.63, 261.63, and sure enough, there it is, 277.18. So all you need to do is multiply by the 12th root of 2. That's how these scales are generated, right? And there's a bunch of music theory, why that sounds pretty and all that, and so forth. Okay, so now we know that. So now we have these frequencies. And we don't need to generate them because we can just look them up like we did. So we don't need to do that math, but that's how you would do it. If you had an algorithm or a synthesizer that generated these with no lookup table, you could do that. So now, what are we going to do? We need to take this information and we need to figure out the RA and the RB and the C relationship to get this, right? Now, if we go back to our 555 timer data sheet, right? We can run down here and then, you know, we keep going, we find the astable or astable mode of operation, which will be here someplace. Let me scroll through. Okay, there's monostable. And here is astable, all right? So looking at this, it's a very simple circuit. It's RA, RB, and C. So I'm not going to mess with RA. We'll just fix that. I'm not going to mess with C. We'll fix that. But I am going to mess with RB, all right? So that's the resistor we're going to change. And what we're going to do is we're like going to electronically, with switches, just switch in 12 different resistors into this position. Super simple idea, all right? And then here's the equations, which you just saw in the schematic. That models everything. So we're going to use these equations to figure out what the frequency will be and kind of work a tool in Excel so we can say, you know, given this and given that, what is the frequency going to be and so forth. So let's take a look at that tool. All right, where is the tool? Here is the tool. So I wrote this little tool. And so what it's saying right here is the things in this light red, you enter in, and then the tool will calculate everything for you. So we have to put in the frequencies, and here they are. So here's all the notes right here, all right? Here's RA, all right? And as you put different values of RA, so I think I used 1400 ohms. And then basically you can plug in a value of RB here and then a value of C here, and this will then generate a frequency and then a duty cycle. So this is kind of a little work area here so that you can kind of see how things make changes. But what you really want to do is put your values here and then let the whole thing generate. So this is just a little work area. This is the thing that does all the calculations. So the only thing you have to put in are the notes, which I already did. And then the other thing you can change is you can change what the capacitor value is, but you change it here. And then here you can change what the frequency is, excuse me, the resistor value for RA, which we've said is 1400. And I think that's what it is on the schematic, what I ended up with. Let's see here. All right. Yeah, 1.4K, 1.4K. Okay, so let's go back here. And I haven't played with this in a while, so hopefully this keeps working here. So we got to change it here. This right here does not translate down to the bottom. This does not here. We got to put things in here. So we're going to put, and this is already in K, so I've scaled the entries. So you just put 1.4K, hit enter. And then notice how all these things changed. All right, so it puts 1.4K into all these and then does the calculation. So our target was 261 hertz. The actual frequency we'll get is 259 hertz with this value resistor right here. So these are all these values of resistors. Now, the values of resistors, again, let's watch this. If I go in here and I change this to 1.2, notice these values of resistors don't change. All right, I entered these values of these resistors. So you have to actually enter these, and you're trying to find values that exist, right? Find values that exist and that you can purchase and that give you the least amount of error. So the whole point is that's what this tool up here is for, because I've got to kind of hunt and search. I could write code to do this, but this is this only takes a few minutes. So basically we say we're going to use 1.4K for RA. Now, what do we need to get So we've got this 259 hertz here at 27K. If I can buy a 27K, great, but maybe I can only buy a 26.5. If I do that, see how this changes here, right? So let's go back and we'll make that 27K. All right, so this tool just helps you kind of figure out what values, and then basically I had to change all these values, so I minimized the error. This is calculating error, and then I looked up in DigiKey and Mouser, can I buy these things reasonably? And I was able to, I think, buy all of these. Okay, then here's the capacitor value. Notice it's 0.01, right? And this is in microfarads already. So you just put the 0.01, you don't need to put microfarads. All right, and then here it's computing what the error is. So this is in percent. So this is 0.65, 0.86, very small. Here, 1.5% error, 2% error, and then the average error and then the total sum error. So this is not bad. So anyway, that's kind of what I left with, and then here's where I got all the values of the resistors, and I'm done. So this is called Music Scale Computer 555.xlsx, and of course this will be in the files for the lecture. You can just run this on Excel and play with it. But right now the way it is, we've got everything that we need. Let's go back. Okay, so here's all our resistor values, right? They're all plugged in there, so you go buy those from DigiKey, okay? And then that's it. And then the last thing really is this amplifier, which we've seen this. We've done not a billion amplifiers. We've done maybe 500 million amplifiers. So we've done this. We built it on the bench. We looked at it. We already know what we're doing. We don't have to work too much with that. Okay. So now what we're ready to do is we are ready to start building our version of this. Where is it? Right here. From all the parts. So what we're going to do is we're going to look on DigiKey a little bit, and then we're going to just copy and paste things like we did last time, but look at why we made the decisions. Things like resistors and capacitors, just going to copy and paste. We've already found the part numbers. So we're only going to look at things we haven't looked at really on DigiKey to kind of see anything new, like the battery holder, for example. That's something we haven't seen, so we'll take a look at that, all right? So anyway, I'll meet you in the next video. And this one's probably been broken up into a couple pieces too because they're so long. But the next big chunk will be we're going to start putting down the components and building up the schematics. So let's go ahead and stop here, and I will see you in the next video. Bye. All right, welcome back, and we are on the next lecture. We just finished up talking about how we generated the values for the resistors, the RA and RB resistors. This is RA, and then one of these is RB. It's switched in to create the diatonic scale, which we use this Excel spreadsheet to do the computations of the desired frequencies, and then we put in a value for RA, and then the system then computes the frequencies based on these RB values here, which we select ourselves as well, and then we try and find resistors that are as close as possible to real resistors. All right, so now that we've got all those values, now we're going to go ahead and do the design. All right, so let's jump right into it. So this is the reference design here. This is our working copy, and then let me close this, and then our final design is going to be here. And of course it's blank. All right, so the first thing that you notice is in this particular design, we've went along and done a voltage regulator, added a voltage regulator, and the whole point of this is we want to put in use a 9-volt battery, a 9-volt battery, and then we're going to regulate it down to our 5 volts, and we want that regulation to stay nice and stable. So we're using a LDO, a low dropout regulator, right? And you remember what those are, just there's only required a small differential between the regulation output voltage and the input voltage, and it will maintain regulation. These are much better than standard like crude or linear regulators where you need a much higher differential, like 7 volts or 8 volts to maintain the 5 volts. Anyway, there are literally countless thousands of LDOs, and all different manufacturers make them. It's just one of these things that's kind of personal preference and parts that you like to use. Now, in this particular case, I decided to use a microchip part, I believe. This is a microchip part. We'll go in here and type it in. And if we're at all lucky, it'll actually find it. Yeah. So in this case, you can see it's like a transistor package, all right, which is kind of cool, the TO99 package. And this particular part, it's also very cheap. At 100, it's 37 cents, all right. and output is 5 volts. It can take an input maximum of 13.2 and it can output a quarter amp, right, 250 milliamps. And then look at the voltage dropout. It's only 0.65 volts. So as long as there's 5.65 on the input, you'll maintain regulation. All right, so this is just the fun part. And like I said, we could have used anything we want. So we could have put in a 5 volt LDO if we wanted to. And right here under voltage regulators, 40,000 parts. And then we can go through and select, whichever manufacturer we like, and then pick a part. All right, now, since we're doing a through-hole design, again, on this particular project, we won't be using these surface mount ones, but I'll tell you, typically when I do a surface mount design, I'll use these kind of products with this kind of packaging. So this is like an SO23, it's called. Here we go here. SOT, 753. They have different names, but anyway, the whole point is, if you look at it, there's 2 pins and 3 pins, so SOT23, and then it has some other variation names. But these are nice surface mount, and then a little bit bigger with a little bit of a heat sink if you need it, if you're for more current, all right, that kind of thing. But anyway, we're not going to worry about that because we're going to use this part right here. Okay, so let's get that into Circuit Maker. So we've got this part right here. So this is what we're going to use for the voltage regulator. So now what we can do is we can just grab this part with any luck. We'll hit copy, all right, and then we'll go over to our other schematic here, and we'll paste, all right, and we just pasted it in there. And there it is. So that's cool. Of course, we're going to have to change the reference designator at some point, maybe, but it's maintained the same reference designator, which is okay. All right, and let's go back to our design here. All right, so that's a voltage regulator. We'll mess around with the capacitors here in a moment. Now, the other thing is we want to have a switch, all right, and then we want to have a battery holder. We want to be able to switch the power on and off. So let's go take a look at this battery holder here. So now this is a Keystone Electronics. You're going to find that Keystone Electronics has a lot of good battery holders, one of my primary vendors that I like. And again, you can use this tool to do a place. We could do a right click, and we could say place and do component, and we could search for battery holders, but I like doing it on DigiKey or Mouser because it's much quicker to see, and then we kind of see what we want, then we see if it's available on in Circuit Maker. So anyway, this Keystone Electronics 1294, what does it look like? It looks like this right here. Let me push 3. This is the final design. So that's it right there. And zoom in a little bit. So that's what it looks like. Very nice. Whoa. Let's grab us a little bit of, there we go. So very nice, real easy, and it's got 4 mounting holes as well. So we're going to use that part. So let's go back to this right here. Go back to the schematic, and let's get this part. So it's Keystone Electronics 1294. Okay, Keystone Electronics 1294. Let's go back here, and we can say Keystone, and if we're lucky, we might be able to just say 1294. 1294. Let's see if we're lucky. Oh, and good, DigiKey was able to find it. So again, we look at the prices here. So at 1,000, it's $1.15 for this particular part. Let's copy that link right there. Now let's just go and say 9-volt battery. We'll just say, now see how this says holder bat 9-volt universal plastic PC. So a lot of times you can just use some of these kind of search terms here. So we could say bat 9-volt. Because sometimes it's hard to figure out what to search for, what should be the search terms. All right, let's wait for DigiKey to kind of collate what it needs. So see battery holders, clips, and contacts. There we go. All right, and then we've got all these battery holders. Now here's kind of the common one that we could use one of these, but I don't like these unless you have a plastic enclosure that you can solder those leads into and give some strain relief. These typically rip off, right? Now here's another option. You can mount these into the printed circuit board. They're usually very cheap. Now in this case, surprisingly, that's 50 cents. So you need 2 of them. You need one for the positive and negative, right? They're different, the positive and negative. So that's $1 when that other holder was only $1.15. All right, so here's another holder from another company, $1.65. So this obviously at 5,000 units it'll be cheaper. So if we look at this one right here, and down at 1,000 it's $1. So a little bit cheaper, but that's kind of I'm not a big fan of that one. So again, you just go through here and you see what's kind of going to work for you, right? What you kind of want. All right, and scroll through and see what you like and all that. And there's all kinds of battery holders. I think, yep, in fact, that's the one right there, the 1294. And it's a little bit pricey. It's $2 in quantity one, but I like it. It's very robust. It's very industrial. It's got 2 nice solder leads in there, and it's got 4 mounting holes. Our battery's not going to pop out. Okay, so we're going to use that. So again, we can do one of two things. We can go back to here, and we can actually say place, and we can say component, and we can go choose, and then we can, in my favorites, everything that I've used is in my favorites, so we can find it there pretty easily. So we'll just say Keystone 1294. That's one way of doing it here, and it's not finding it for some reason. And this behavior, we'll try 1294. So even though it says Keystone Electronics 1294, should have found it. And then you can see it here, and there I am rotating it. So it's got a beautiful 3D model and the symbol and all that. So we'll go ahead and use that, and we can pop it in here. I'll just put it right here for now. All right, and obviously there's going to be only one battery, so we're going to call that BT1. BT1. And let me, I always forget, let me turn on the little keyboard control here so you can see what is going on. All right, we always forget to do that. All right, so let that do its thing here and go back here. Okay, so so that looks good. Now what else do we need here? Going back to the circuit design. So we need a switch, and we can use any switch we want, but this switch right here I think is the same switch we used in the Magic Wand, right? So the same switch, so this EG1218. So as a matter of fact, I'm just going to grab that and I'm going to copy it, right in here. All right, we're going to put that switch right there. And then just for kicks, let's take a look at this EG1218. So what we can do is we can go and place, and we can say place a component. We can go choose, and then we could say EG1218. And this will let us look for it. And then there it is right there. And then, yeah, there's that switch right there. And you can see in 3D, same switch we used. All right, so that's correct. All right, so we got that switch. Good. All right, looking back to our design here. All right, so now we've got a capacitor on the input. Now, since we're going from a battery, we don't need any high frequency filtering. So you're going to notice there's no small capacitor here. There's no 0.1 or 0.01 microfarad. Typically, if you're coming from another power supply, you're going to want filtering here. And you may want a couple capacitors, one large capacitor for smoothing, another capacitor for filtering, or maybe 2 capacitors. And a lot of times you'll see me throw in an inductor or ferrite bead for very high frequency noise. But in this case, we're going from a battery. So we just put, and we're going to put a big fat capacitor here, 22 to 100 microfarad. And the reason for that is I don't want to have to go back to the battery all the time. If I can pull the charge from the capacitor, that's going to put less strain on the battery. So we'll put a larger capacitor here, and then we're going to put a couple capacitors here. Notice this is electrolytic, or it's polarized, and then this is not. So this would be a ceramic through hole. Again, we can go and look for a bazillion capacitors, but we're just going to take exactly whatever this one was. So we'll take this capacitor. Now watch this. We can actually grab all of this. Let's see. Let me see if I can do this. Let me grab that, and I think I can do what? Shift? Yeah. And then let's grab these grounds. Let's see what happens there. Control copy, just for fun. Let's see what this does. And then paste. Yeah, great. So then we just grab that right there, okay? So now we got those parts. Good, we got our capacitors. And we can always double click and see exactly what these things were, what their part number was on DigiKey and so forth, right? But we're looking, and here's the 3D model. Let me rotate it around. So that's a standard polarized capacitor. Okay, and we're not going to start wiring this yet. In just a moment we will. Let's go back. Oh, I keep pressing the wrong one there. Okay, and then what else do we have here for our power supply? Not much. We've just got some test points, and I think that's about it, yeah? And then we've got our power good indicator. So again, it's just an LED and a resistor. So now's where I'm going to start, we're going to do this grown-up style, all right? So we don't need to go find another resistor and find another LED. We're just going to literally copy this. This is the point. You're a software engineer, copy and paste your code. You've got code that's already working. You've got electronics that are already working. Why make it again? Since it's through hole, it's doing what we need, we're going to copy it. So we're going to just take that, we're going to copy it. All right, we're going to put it down over here. Good. The only thing we're going to mess with maybe is reference designators. We want to be a little bit careful of those, right? These values, but so far so good. All right, so now let's do a little bit of wiring here. So let's now remember how to wire. You go up here and place wire, right? Or you can hit W. So we're going to hit W, and then notice there's a little crosshair. All right, so here we go. All right, so we're going to go there, and then I'm going to go here. Paying a little bit of attention to the pins, so when 1 and 2 are connected, the switch will be on. I could have put it to 3, could do that. All right, here's our capacitor. Good. All right, let's move this. I'm right clicking to kind of move this. Here's our output. So I'm going to make a little right angle turn. I'm going to put this right there. And then I'm going to put this right here. All right, here's our ground. I'm going to copy a ground, copy, paste. Remember, keep things neat. Press W again. Go out, go down. Now we got all these nice grounds here. All right, we got our power good indicator. Looks good. We'll put that right there. 330 ohm, and you know, these values are not written in stone. I might change this, make it bigger, make it smaller, so it's a little bit brighter or not. It's now the LED again. We don't really care what color we say it is here. We can change it to red to blue to green. We just want the style of LED to be consistent with what we're going to do, which this this particular LED is a normal 5 millimeter LED upright kind of LED. So we're going to stick with that. We know we need this V sub CC. All right, so now if we go back here to our schematic, we're using the bar kind of power supply indicators here. Now let me copy this test point here. I'm going to copy this test point. I'm going to copy that. All right, because we're going to have to look for that. All right, so we're using this bar here. If we didn't want to, we could go to power port here, and then we could just grab one right here, right? And where's V sub CC? We could grab that, or we could grab this and rename it. All right, but again, we've already got it here, so let's just grab it, Control, paste, and I'm going to put it right here, and then with a W, I'm going to connect it. There we go. All right, so there's V sub CC. All right, and then let's go ahead and paste it again over here. But right here, I'm going to call this something a little bit different. So right here, and we can go look at this design here to see what I did. So see, I call this VBAT, and this is a convention I do, and I change it a little bit here and there, but a lot of times I may want to sense directly the battery voltage disconnected from the whole system. So I call that VBAT, right? And maybe if I've got 5 different batteries, this would be VBAT 9 volt, VBAT 3 volt, VBAT 1.5 volt, whatever. Then after the switch, this means it's been switched, and I may want to know that. I may want to know something about this because this is this switched on? So I have a sensor here, I might have a sensor here. So again, we have all these different names of things so that we can kind of track what's going on electronically at some point later. So right here, we're going to put VBAT, we're going to go W, so that's VBAT, right? And then I'm going to rename this one, I'm going to call this VBAT switched. So that means it's the switched on version, which I might want to connect a sensor up to at some point and tell this is always going to be on, but this will only be on when the switch is closed, right? So, all right, then here's our battery right here. And let's see here. Okay, so we've got a little bit of a problem here. See this battery? This is the plus side, long side. Now look at our battery here. See that? It's backwards, polarized incorrectly. So we'll select this little wire right here. All right, now there's a little mode here, which if we select this and go right click, we go break wire. And then, yeah, so we can just break a little piece of the wire, so we don't have to do everything. So now I'm going to click on this, and I'm going to hit space bar. Remember that rotates things? Okay, there we go. Now I'm going to press W for wire, and I'm going to connect this all back up. Okay, there we go. All right, so now we got that correctly polarized. Let's get a ground here, copy, paste. And again, I prefer to keep everything at the same level, just being neat. There's a W, get our wire going there, good. Okay, let's back out, looking really nice. Okay, here's this test point. Let's talk about this for a second. So all this test point does is it creates a little 2x2 millimeter surface, just a pad on the surface of the printed circuit board. If we go look at the final design here, where is it here? We can see this. Let's see, where is our regulator? Our regulator is right here. And let's go into 3D. So see right here? and see right here, these are actually these pads. So these are these exposed pads. Those are those test points right there, test points. And so that's what that'll look like. They're just a little pad, and that's how we refer to them so that we can put them into our design. So it's just a test point. Now, if we didn't, we could just make that up, all right? We just make a pad up, but also if you go to component, all right, we could say choose, and then we go here, forget favorites, just go to octopart, which this isn't really a part, but let's just call it test point. And test point probably is 2 words. One thing came up if we use the concatenated word, if we split it up into 2 words. Yeah, so test point orange, so you see all these little different symbols for them. And some of these test points are actually, you can buy components, like this one right here. Oh, yeah. So take a look at this. So watch this. So what this is, it's like a little protrusion with a little eye through it, and that would be so you can grab it with one of your probes from your oscilloscope or your logic analyzer. So take a look at this. Watch this. See that? So it's got that little eyeball there, little eyelet. And so that's really nice. Those are a bit expensive though. So we're doing this really cheap. So for our test point, we just want a solder pad. That's it. We can solder something on or just touch our probes on it. All right, so we're not getting all complicated. So we're just going to use this pad, and if we double click on it, we can see it's just a pad. That's it. It's free. Okay, just a free pad. All right, so that's test point ground. That's test point ground. All right, and then up here, we can copy this, and we can go like this, and we can say this is a test point V sub CC. Now we have a test point V sub CC, and if we want, we could just put those right next to each other. And what we could do is we could grab them both. We just put them right here if we like. Okay. All right. So there's those test points. Maybe we'll put them up here. Okay. All right. And then we need a label for this. Let's just go copy whatever I called this up here. And we got some text. So this says low dropout regulator. Okay. And then let's copy this text right here. And then let's copy this text right here. Again, we're learning to copy things because it just makes everything a lot faster. There we go. Grab those. Now just put this. This is the title of our whole little project. Here's our battery. All right, I recommend a lithium ion. Let's go take a look at that really quick. Oh, we already got this one. Oh no, this is it right here. But since I put this here, it's kind of in the way. So maybe I got to put these right here. All right, now let's put this here, the text. Looks good, Control Save, constantly saving. So there's our entire power supply. Not a bad power supply, you could always add more features to it, but that's good enough for now. All right, now, one thing I just was talking about is this lithium ion recommended. Now, if you don't buy a lot of batteries, you might not even know what I'm talking about. So let's go here and we'll type in 9-volt battery lithium ion. Okay, watch this. So come up here and we see this these industrial batteries and this Ultralast. This is the one that I like using a lot. I end up using these, and this just came up some random site. But these, so it's a lithium battery. It's a primary cell non-rechargeable lithium ion. All right, and then in the stores you can find Energizer 9-volt lithium right there. All right, and there's these, and they're not cheap. They're not cheap. Energizer, we can go to Energizer's website and see their propaganda. All right, but Energizer makes good batteries. So, and let's see if it has the 9 volts here. What I wanted to show you were the specs of it, and let's see here. Okay, let's do this. Let's go back. I actually want to show you this lithium data sheet. Oh, we had it right there. Data sheet. This is it, I think. Yep. So here's the data sheet for the lithium ion battery. Now you can take a look at this. These things are pretty crazy. So maximum discharge is 1,000 milliamps continuous. That's an amp continuous. This thing is no joke, right? This thing is serious. Now look at this. Continuous discharge to 5.4 volts here. All right. So these different graphs here are showing, as you discharge this, what the current is and the performance and all these different things here, how many hours, right? So here's the voltage as it changes. So, you know, at 1.2 hours, it'll drop down to, you know, 7 volts at 500 milliamps. We are not going to pull 500 milliamps. This is an awesome battery. These are actually awesome batteries. Now, if we just look at their plain 9-volt battery, so now take a look at this, Energizer 9 volts alkaline battery specs or data sheet. Okay, take a look at this now. Look at the contrast here. I think this is it, yeah. So we'll zoom in, all right. And now, yeah, and in this one right here, now notice these tests now, instead of showing this huge current at 500 milliamps, what it's showing is a toy. And it's saying 200 ohm, right? So 270 ohm toy. So now we'd have to compute what the current is, and the current is much, much, much less, right? So if you look right here, and at this, say where it's at 10 hours at 8 volts, if we get our calculator, it's always trying to trick us. Everyone's always trying to trick us. 9 divided by 270, all right, is 30 milliamps. So basically, it'll last at 30 milliamps for 10 hours. Where that other one, we were pulling half an amp. So lithium-ion Energizer, awesome. So that's what I want you to use. All right. Let's get back to here. Okay, let's get back to here. Okay, so we've got our power supply. So we got our power in, we got VBAT, we got a switch, we got VBAT switched, and then we have our low dropout regulator. Okay, let's go, we didn't even look at the data sheet, we just picked the part. Let's go get the data sheet up on this and take a quick perusal. All right, so as a matter of fact, well, I guess we can do it right here and we'll pop up the PDF, right? So data sheet, MCP 1702. All right, so so there it is, microchip part, input 2.7 to 13. I like that. It's a 1/4 amp output. That should get the job done. If it doesn't, you can always use a bigger one. It comes in different packages. So it comes in this SOT 2.3 package, this 8.9, and then of course the TO92, which we're using because we're trying to maintain through hole. All right, and then stable with a 1 microfarad or 22 microfarad output capacitor, which we're putting on there. So of course you can just, you know, go through and look at the reference design, very simple and all that. All right, in the data sheet. So always take a look at your data sheets for stuff. All right. Okay, so now we're done with this, and so now let's move on to, what are we going to move on to? We are going to move on to this big part here, all right? So we're going to build this big part here and kind of get this done, all right? So why don't we stop here and we'll start up and work on this big part, all right? See you in the next video. All right, welcome back. We just did a quick pause. We finished the voltage regulator circuit, the power circuit up here. All right, and now that we have power, so we have our stable 5 volts V sub CC, and this is going to be a 5-volt system. We don't have any other voltages. And now we're going to use that power to drive our only IC in the circuit, really, our only other IC other than the voltage regulator, which is the 555 timer. So in a sense, the magic wand that we built, which had multiple ICs, is actually more complicated than this project in some ways. However, this project, because this is something I think that's more useful, it's an actual organ, you can play it, it's something interesting. We had to have the Excel spreadsheet, we had to understand how to generate the tones, then we had to make decisions on the design of the product as far as how many notes to have, how many octaves, and so we have this 12-note diatonic scale. And then, of course, we have an analog section, an amplifier. So more complex in a different way. We're still doing all through hole. All right, so at this point, you should be very familiar with a 555 timer, and you know, we shouldn't have to go over that again. As usual, just get the data sheet for it, wherever it's hidden here, someplace. I think it is right. Where did the data sheet go? There it is. So here's the 555 timer data sheet, and then showing the A-stable calculations and formulas, and then the design, how you hook it up. Very simple. We have that RA, we have that RB, and then there's a 1-line trigger back to the threshold. That's pin 2 to pin 6 if I have them memorized. And then we have a capacitor. So we have 2 resistors and a capacitor. Then we have a bypass capacitor up here. All right, so all we need to do here is design this so we have a fixed RA. That's the thing that we are fixing in our design here. So RA in this case is 1.4K. You can make it whatever and play around with the numbers, right? So we have that fixed RA, And then what we want to do is we want to switch in these RBs. So basically each time you close one of these switches, it switches in this RB into the circuit and then terminates through the capacitor, just like in the design right here. So we're just switching in this RB. Nothing wrong with being able to do that. We're doing mechanical switching. All right, so when you have any kind of mechanical switching, if this was a circuit where we cared about noise and things like that, obviously when you close this switch, it's going to vibrate and bounce and debounce, you know, maybe 2, 3, 4 times in most cases, and then it would stabilize, and there might be arcing and all that. So if we're talking about a very complex circuit, you would want to electronically debounce this and maybe do this all electronically, meaning gating in these resistors via a switching system that is, debounced. But for something like this, we don't need to do all that. All right, so again, we've got our 555. We're going to be using through hole, so we're going to use the DIP8 package. We're going to use this monolithic bypass capacitor right here, another monolithic capacitor right here. So that's just the simple 0.1 or 0.2 inch pitch between the leads through hole, right? We've already selected these. All right, and then these resistors are all going to be through hole resistors. And let's just take a look at the design real quick again here. All right, so we're going to do most of our work when we're mimicking this, because this is, we can copy and paste this if we want, but we're going to actually lay these things down. But if we go into 3D, we want these kind of resistors right here, right? These guys. And, right, so that's what we're looking at right there. Okay, and then you can notice there's no 3D models for the monolithic capacitors, right? So that they're just blank because there's no 3D models in this case. All right, so let's go back to 2. All right, let's go back to our design here. All right, so what we're going to do here is we are literally going to take this whole section and we're just going to copy and paste this into our design. All right, and again, the whole idea is here. What I want to show you is how we can take from other designs. We can open up many, many different projects and copy and paste things. All right, so we're not going to copy and paste the amplifier yet. We're going to do that later. So we're going to grab this whole thing here. We're going to try to. And we might get a little bit more. That's okay. So I grab that, Control C. All right. So I've got all that, everything except this text right here. And we're going to go into our design here. We'll back out of it, and then we'll paste it. And you can see as we paste it, now we can see that we need this thing to be larger, this document to be larger. So we got to go and use a larger size. And then you see how we got a bit extra here. We'll just delete that for now. All right, so let's go and fix that. All right, so where was that? View, project, templates. So under templates, general template, and let's see, I think if we pick A3, all right, and we do A3, and that gets us a little bit bigger, right? That's more what we want. So I grab it, there we go. And we'll just put it right there. Good enough. Let's zoom back in. Okay. All right, so we're happy with that, and maybe let's pull this down just a little bit. I don't like to put things too close. Now, again, remember we talked about when you do larger designs, you might want to have multiple pages so that just on one page, we would have the power supply here, and another page would have another power supply, another page we might have this. Then you're going page to page. It's the same idea in a program, having multiple source files, for different libraries. Maybe one is a serial library, one is a graphics library, one is an SD card library, whatever. But when you're learning, these designs are simple enough. It's just easier to keep it all on one page. It's the same thing when you're doing embedded programming. Typically, instead of blowing everything up into many, many, many files and just causing confusion, you just kind of put everything in one file and just keep it clean, and then you can always separate it later, right? So we're going to kind of take that point of view. Okay, so here's the design right here. And this is the clock generator. We've got grounds, we've got our capacitor C1 and C2 here, and then C4, C5, C6, so that's okay, we don't have any collisions. We got switch 1, we got LED 1, and then we have all these resistors right here, R6, R7, etc. So all the reference designators copied over, and their values, which we'll have to deal with. Now, these switches right here, if I can get it to cooperate. Here we go. So here's the switch right here, and let me rotate this in 3D. So this is just a momentary switch, a very common one, and this is it's 2 pins, it's square, all right? So if we go and this is the part number right there, and we will go in back into DigiKey here if we can find DigiKey, and we'll type that. Don't need to put that Panasonic. So we'll put that part number inside of there. Now the thing about switches, there are so many bazillions of switches, and we've seen them before when we talked about it. And what I suggest that you do is literally just buy lots of switches. Just buy switches. Every time you get a chance, buy some switches. If you go to a electronics store or a kind of a warehouse store where they have, extra electronics or refuse or this or that, just buy as many switches as you can so you can just get a feel for them and see what you like and all that. There's no correct switch for this. It's just kind of whatever you wanted. And so these switches, what's nice about this particular manufacturer, these switches, they're tactile switches, means they're kind of soft. And then if you look in this design right here, they have a few things. The height of this cylinder right here, which is the switch itself that you press down. This plunger has a height, so that's one thing. It has a diameter, that's another thing, another variable. So they have longer and shorter and wider and thinner diameters. And then the other thing is some of them, they also vary what the hardness is of this plastic or rubber, right? The durometer of it. And then another thing is what is the force needed, the gram force to push the switch down. And those are all different parameters. So there's just, you can go all over the place with these things. Not a big deal. You don't need to make anything complicated here. You just want to pick something you want. So again, if we just put momentary, momentary switch, and we put SP, ST, single pole, single throw, that's all we need. We're going to get many, many thousands, at least hundreds. Give DigiKey here a moment. All right, so tactile switches, yeah, 6,800 switches, 200 something new switches. So you can see there's just a plethora of switches. And I mean, I'm a big switch person. I like switches. Here's some dimple switches. And just you can do worse things than scroll through every single switch and look at these things. But again, like I said, you get some extra money, take $50, $100, $200, and they aren't cheap, right? These things are not cheap, right? Take some money and buy 100 switches, buy a couple hundred switches, buy a few of each, because it just helps you think about things and kind of get a feel for what it's going to feel like. Here's look at all these cool colored switches. I mean, you could just look at this stuff all day long. Now, another thing you can do is you can sample switches. If you want to go through the trouble, you can contact every single one of these companies, Omron, eSwitch, C&K, you name it, and a lot of them will do samples on their site, but they're only going to sample the cheaper switches a lot of times because they're so expensive. But if you find a local representative of the company for sales, distributor, local rep, or a field application engineer, a lot of times you can get samples, but it's a lot of work. I just pay the $5 and be done with it. So you do what you want to do. All right, and again, we can do lower profile switches or micro switches. So you can see some of these switches like this, that's very low profile compared to the switch we have. Nevertheless, I just picked a switch. You can pick whatever you want. All right, so now we've got our 555 clock generator in here. This is going to generate our signal, and then so we have this out here, and we got to do something with this. This is where the rubber meets the concrete. All right, and we just put that right there. So now we want to get this signal, and we want to amplify it. We talked about simple amplifiers. We made a few amplifiers with transistors, and then I told you that in the end, what you really want to do with an amplifier is use an operational amplifier or a specific amplifier, whatever you're trying to amplify. Is it audio amplify? Is it a power amplification? And you can get ICs that do that instead of you doing it discreetly. Typically, we won't, amplifiers, you just won't make them anymore. You'll get an IC to do it, a simple IC that's specifically designed for that application. So there's lots of audio amps, but in this case, we're trying to do things ourselves because we're learning. So we use one of our simple designs here, the single transistor amplifier. So I decided to use a NPN. You can put a 3904 or a 2222A or anything that's similar, right? You just want a couple hundred gain on that. So you just want the gain to be, a couple hundred. And then what we care about is how much current it could take, right? So if you look at a 2N 3904 and a 2N 2222, let's go take a look here. Let me get these things in here. And we've done this all before. We've looked at all this before, but hey, it doesn't hurt to look at it again, right? I forget all kinds of things because when you're doing design, you get so much on your mind. So let's just take a look here. And all right, so look at active, apply filters, and we want the TO92 package because we're doing a through hole. So here they all are here, and then we pick our favorite vendor. You know, me personally, I like Fairchild a lot. Fairchild doesn't seem to have any. We'll try Fairchild on. Okay, there it is right there. Okay, great. And it's 21 cents, and at 100, it's 10. At 1,000, it's 4 cents. These things are super cheap. So this one can handle 200 milliamperes of collector current. That's going to take care of what we need. So we could use that one right there and be done with it. So any 3904, any 2222 will get the job done, or any similar transistor. All right, in this case, we just picked, we just marked that we're going to use one of these, but the package is the same. It's the TO92. Now, very, very important. What did we learn about these transistors? Sometimes it's emitter base collector. Other times it's base emitter, excuse me, I'm sorry. So emitter base collector, or it's collector base emitter. Sometimes the pins are switched around, even though the orientation of the flat side of the transistor it has not changed. So don't always assume. Let's go to our drawing program. Don't always assume. So say you have a transistor and you're looking at it, on its end here. All right, and let's kind of do this poor man's 3D thing here. Okay, all right, and then say we got our pins coming out here, right? Now one transistor, I'm not going to be able to draw that with the mouse, I'll tell you that right now. So let's get this color here. One transistor from one vendor might be emitter base collector. But the other vendor might be, the base is always in the middle. I can say that for more or less all eternity. It might be switched where the collector and the emitter are reversed. So you might get a 2222 from one vendor and a 2222 from another vendor, or a 3904 from another vendor, or whatever. Any kind of NPN or PNP, doesn't matter. And these outer pins might be swapped. So whatever you do, be very careful. In our case, since it's through hole, it's just going to have 3 holes like this, and it's expecting, something like this: collector base emitter. All right. If yours is emitter base collector, just rotate the transistor around 180 degrees and solder it in. But be careful. If it doesn't work, that's why it didn't work. All right. So be careful of that. That's a gotcha. It'll always get you. It's got me a billion times. All right. So now what we want here is we want to just copy this, and then the only other thing really here is these capacitors. Again, we're just using electrolytic. We're going to use the same footprint as the other electrolytics in the power supply. Up here, right here, and right here. All right. Again, once we have the footprint, we can kind of just put whatever we want in there, so we don't have to pick an actual part number, right? Now, one other little detail is the D1, this flyback inductive kick diode. You can just use a 1N4001 in here, that's fine, or you can use other diodes. If we double click on this and we can see what the actual part was right here, we go back here, 1N4001 series diode. That's it. Here's a 3D model, which looks like exactly like what you would expect. And there it is right there. All right, so that's what we're using right there. All right, and then the final element here is the speaker connector. So, there's a lot of different ways to do this. We can do this with a very simple 2-pin connector. We could have just put solder pads or solder holes and then took the speaker, where's speaker? And we could just solder, there's the wires. We could just solder the speaker in there. But what I'd rather do is put a connector on there and then connect it in, and then I could change speakers. So I put a female or a male on the PCB, and then I could put a female or male, whatever the opposite sex is, and then I could plug these things in and try different speakers, or if I blow a speaker out. So we're going to put some connector on there. We could use, really cool JST connectors that you see for batteries and whatnot. Those are real nice, a little bit expensive. Or we could use just very simple 2-pin connector, male and female. Just get it done. So let's double click on this. And here's a 3D model, and it's just this little connector right here. Very, very simple. And as long as you've got 2 holes in the circuit board, right? So that's our 2 holes. Let me zoom in here a little bit. What's the zoom? What's the zoom? Let me see here. There we go. All right. So these are the two holes, these are the two pins that go into the circuit board. So I can put any connector I want on there that fits in these two holes. So this is a 0.1 inch pitch, a distance between them. So, you know, this is a right angle connector. It just looks right angle, but if I took a straight connector and bent it, it'd be right angle. If I took a right angle and bent it back, it'd be straight. You put whatever you want. So in my case, I'm actually showing in the design a right angle connector, so everything's flat. So then we would just slide the connector, the other connector, which would be soldered to the speaker. Okay, so that's what we're using there. Right, and that actually does have a specific part number. In this case, I went and looked it up and found an octopart part, and we can come here, and it may not even say it. Yeah, here it is right here, TSW. Can't remember what that company is. Put the part in here, and there it is. So that's exactly what we're looking at right there. All right, a billion vendors make this exact same thing, and I like to exaggerate with millions and billions, and so you can always find this from all kinds of different vendors and very cheap, no big deal. And you could get a bigger one and just cut it into pieces, right? All right, so let's go back here, and we're just going to copy this amplifier. All right, so I'm just going to copy the entire thing, copy, and then I'm going to bring it into our final design here, and I'm going to paste it. We'll just paste it right about there. All right, and then here is our signal we need to connect here, right? So I'll take this, connect it right there, and then let's go ahead and straighten this out. And this wire system works pretty good. It pretty much does what you would expect. You drag things and move them. All right, so that's good. So now let's look at a little bit of what's going on here. So we've got the power that's generating our power. We got our 5 volts. 5 volts powers our clock generator, which is just sitting there. It's not even running right now. The second we close one of these, so this is an interesting point. It's not running because this other resistor is not closed, right? So as long as these switches are open, nothing's going to be happening. That's okay. Now, when we press this clock generator is going to start up, and during the startup, that first clock may not be exactly what you expect. Because we're not using the enable here, we're just kind of hijacking the circuit. So it's going to kind of do something weird a little bit, but that's going to happen in microseconds, right? It's going to happen very, very quickly, or milliseconds. Then it's going to start putting out our square wave, and then that's that. So we're going to get our square wave out of the pin 3 here, right? And then now we're going to take that, and what we want to do is we want to capacitively couple this into this transistor amplifier here. So we want to remove the DC component, and we just want the AC component of this. So that square wave, instead of riding on top of ground, is going to end up going plus and minus 2.5 volts in both directions. We're going to stuff that into the base of this transistor amplifier, which we've biased someplace above ground. And then we're just going to do this a straight current amplifier, and then we're putting the speaker right inside of the collector circuit, so it's just going to get hammered with current every time this transistor turns on and saturates. All right, so we're not using this as a linear amplifier, we're just using this as an on-off amplifier with a lot of current, because I would just want to drive that speaker really hard so that we can hear the square wave, because we're putting out square waves, not Lady Gaga or something, right? Just simple square wave. All right, so that's it. That's all there is to it. So now, if we look at this, we have the entire circuit is done. We've copied all these elements here and put them down. Of course, this time instead of on the magic wand, we just kind of copy and pasted things, which saves us a lot of time. So let's do a Control S on that. Let's save it. Let's go here and let's commit the project. Make sure we've got a committed project here up to the cloud and all that. Let's go back here and let me see here what this thing. Let me just do a Control save on that, this working copy, even though I'm never going to use it really, but since we selected things and moved things around. All right, and then the last thing, this text right here, the 555 timer notes, this is just my personal notes, right? So I can remember how this thing works, right? It talks about RA and RB and C and all the formulas. We just copy that, might as well, right? And we'll just put it over here someplace, do Control V, and we can put it right down here. All right, and then why don't we grab this whole piece here again, and we'll just move it a little bit over here, give ourselves a little bit of breathing room. Grab that again, we'll just put that right there. All right, and another thing we could put is we could put some notes about the low dropout regulator. We could put whatever we want. inside of that. And that's really nice because you go back here and there's no comments in electrical designs and schematics, right? There's none usually. Electrical engineers are definitely not commenters. Coders are not commenters, right? A lot of coders don't comment at all. So you can imagine electrical engineers are way worse. They don't write anything down. So this is kind of being a hybrid where it's like you're writing comments in your code, because this is code. It's electrical code, right? So put those comments in there. Don't be afraid of explaining yourself, what your thoughts are at that time. All right. Is there anything else? Maybe we need a test point on this output right here. That would be helpful. Was there one in the original design? Let's take a look. Yeah, there is. So in the original design, I've got a test point on this output. So let's just steal that. So that makes a lot of sense. So we can see that output. Let me zoom in. And remember, right when I see that little, how it turns red, it's making a connection. I have to drop it right there. Test point signal. Okay. Okay. There we go. And you can go in here and you can modify these strings and all that inside of the document properties up here and put all that information in there. And I'm not going to do it. It's a pain, so you can do it if you like. All right. So that looks good. Okay. So now what's the next thing that we need to do here? So let's go ahead and let's see if there's any conflicts with the reference designators, things like that. Remember, the schematic editor is not an expert electrical engineering system. There's no AI. It doesn't know how things are connected, right? So if you have done the circuit wrong, it has no idea. The only thing it kind of knows is that the ICs have pins. Are all the pins connected? Are reference designators being doubled up on, things like that, all right? So how we check that is we go over to the schematic here on the project. The schematic, here's the PCB, which there is no PCB. Go to the schematic right now, and we're going to say compile. And I believe if you do that and it doesn't do anything, everything is okay. So let's just do something to confirm that. So let's make this R7. All right, so we'll make that R7. So R7 has been copied twice here. So let's go compile. Yeah, so we've got that double up there. So let's turn this back to R6. Sometimes you got to make sure things are working, right? All right, let's do it again. Compile. Okay, that's it. No problems, no warnings. I mean, it's flawless, which it should be. It's a copy of something that we already know worked. Okay, now let's go ahead and let's go into the project here. Let's commit this again. Remember, constantly Control S, constantly saving, committing your project. All right. Okay, so that looks good. So now, what's the next thing? Let's do one more thing, and then we'll stop here, and then we'll start back up. So now we've got our schematic done. All right, now let's go into our circuit board here. So here is our circuit board. Remember, we just created a blank document, so we've got the circuit board there. So now what we want to do is we want to get all the parts copied into the PCB layout document. All right, so how do we do that again? So we go back over here. I believe it's in Home. There's a few different ways to do it. So if we go up to Home and we go to Project, all right, we can say import changes from 555 timer or update schematic. We don't want to update the schematic. That would be going from the PCB to the schematic. We want to go from the schematic to the PCB. This is the one we want, import changes, which is also Shift F5. So I'm just going to click that, all right, and continue to create, yes, all right, and then validate changes. Remember this. Give it a second. We're just bringing everything in here. Execute changes. It's going to go through. It's just grabbing all the different connections and nets. We'll close it, and there we go. And remember, it does this thing that I don't like, where, and then also this, that we can't recenter this. This is, I don't like that, but all right. So there's all the parts all laid out. I don't like the way that this tool does this. Maybe there's a way to get all these not to do this and lay out in a panel over here. Maybe, I'm not sure, but I don't know how to, and I'm not going to figure it out. All right, so now what I want to do is we want to kind of take all these components here and we want to move them in blocks over above this so we can kind of work with this so we're not in this big long thing here, okay? So what we're going to do is we're going to save this right now. We're going to commit this. Give it a second to save. We're going to commit this. Good. Okay, and this is a good place. Let's stop right here real quick, and then we'll start back up, and then we will start moving these components down where our ultimate goal is to get something that looks something like this. Right, this is what we want to do. So we want to get this layout to look something like this. We're going to put everything, put the audio amp, the 555 timer, the regulator circuit, the battery, and all that, and then we'll kind of look at how big this is. All right, so that's the next one. Let's just go through that when we start on the next video. So I'll see you then. Bye. All right, welcome back. And where we last left off, if you recall, was we had all of these parts sitting next to our printed circuit board, and it's very hard to deal with a big row of parts. If there were hundreds or thousands of parts, I don't know what we would do. So what I've done here is briefly, I've collected the parts into their different functional blocks. So here's the amplifier parts. Up here is the voltage regulation and battery parts. Here is the LEDs, their resistors, and the timing circuit. So just so we can kind of grab these things and place them a little bit better. Now, a problem that I just had, which I didn't record, was this. When I looked at the components in the printed circuit board, one of them did not make its way, and that was Q1. And this happens sometimes. Somehow a component gets messed up, something like that. Its nets get messed up. So normally you can kind of come back in here, disconnect it, reconnect it, and then recompile. So you go on to the schematic, you say compile, and then you would go up to project, and then you would say update PCB, and then it would pull the part in. But it just wasn't doing that. So what I did was I deleted Q1, and then went and searched for another 2N3904 transistor, made sure it had a model and a footprint, added it back to the schematic, and then it worked. I was able to recompile and then import it into the printed circuit board. So anyway, I can't recreate it so I could show you, but sometimes that happens. So just recompile and then re-import all the parts back into the printed circuit board if you have anything funky happen like that. So anyway, so we've got all the parts from the schematic now are inside of our work area here in our printed circuit board. So now our goal is to lay this thing out. All right, so the first thing that we want to do is we want to kind of make it semi-similar to what we did here. So this is the original. So what I'm going to do is I'm going to measure this. All right, so let's go to Tools, and let's go to Distance, and let's just measure this from this corner to this corner. All right, and we look down there at the bottom, and it's approximately 9 inches. So 9 inches, 9,000 mils, so that's 9 inches. All right, and let's go from here to here. So it's 9, I think it's like 9 by 4 if I recall. 9 by 4 roughly. Okay, so let's make our board 9 by 4. So we'll go back to our board here. All right, so now if you remember how we do that, we kind of zoom in here, we select this object here, or we don't need to select it, it's just this selected. We go to Home, and then we go to, I believe, Board Shape over here, and we're not going to redefine it. We're going to not move it, but we're going to edit it, okay? So we're going to edit it, and then just make it whatever size we want here, all right? And I'm sure there's something that can tell us what the size of the board is, but I don't see it right here. So if you grab one of these handles, be careful because it'll do that. So you want to make sure you get it so that just showing the icon for horizontal movement. So just kind of work with this, all right? And let's put our grid snap here into like 100 mil, so we can kind of see what's going on. So if each one of these is 100 mil, then each one of these should be an inch, right? There's 5 per inch, so this should be 1 inch, 2 inch, 3 inch, 4 inch, and so on, if I'm right here. So 1 inch, 2 inch, 3 inch, 4 inch, 5 inch, 6 inch, 7 inch, 8 inch, and a little bit bigger. So that should be 9 inches. So there should be 18 of these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. One more. 18. All right, so there's 18 of those, so that should be our 9 inches. All right, and then we want it by 4 inches. So first, let's get this up here aligned better. All right, so we want 4 inches, so each one of these is 100 mils. So 2 of these is 1 inch, right? 2 big blocks. All right, so there's 1 inch, 2 inch, 3 inch. It's too hard to do. 1 inch, 2 inch, 3 inch, 4 inch. So we can make this one a little bit bigger. All right. And nope, that's wrong. Should be right on this major line. There we go. Okay, so that should be correct. Now let's go ahead and let's measure it. And you know, all this stuff is tedious. There's just no way around it. And you know, I can just skip past all this, or you can skip it. But you know, you got to go through it. And a lot of these tools, you got to figure out the best way to do things. All right, so that's 9. That's good. Hit escape. Let's go here, and this should be by 4. Perfect. Okay. All right, so we've got our little circuit board here. All right, let's go back to home. And let's change our positioning to 10 mil for now. All right, 10 mil for now. Okay, and we can press F3 if we want, and we can see everything in 3D now, right? So there we go. So, you know, I don't believe, yeah, we're not allowed to grab anything or do anything. That would be nice though, huh, to be able to move around in 3D, but we can't. Okay, so let's just start placing these objects here. So let's take our battery, and we're going to put our battery here someplace. That's going to go over there. All right, and then we know that we want our amplifier circuit. This is our amplifier right here. We're going to put our amplifier like here someplace. And then we're going to put our voltage regulation. If you look at our other design here, so we've got our audio amp up here, then we've got our 555 timer, which generates the signal, and then we've got our voltage regulator down here. And up here in this version, we've got the battery leads up top here, and we got the switch down here. So that if we look at this in 3D, I like placing batteries in this direction, right? So the battery's kind of up, right? But we could flip that around if we wanted to. All right, but so anyway, we're going to put the voltage regulator down here. We're going to kind of stick to this rough design here. I don't know what's going to turn out when we do this one. All right, and so let's see, where is our little amplifier? Here's our amplifier circuit. Excuse me, here's our timer circuit here. Okay, move this over just a little bit. All right, and then here is our voltage regulator circuit. So we'll put that right there, and let's move this up here. Let's go to 3D. Notice this has got to be flipped around, right? So take this and hit spacebar. All right, let's zoom in and kind of put that in the corner pretty good. Don't want to get too close to the corner. All right, that's good enough. Now we can grab all this stuff here and move it over a little bit. Okay. All right. So, and then we've got all our LEDs here, and the, excuse me, the, not LEDs, these are all our switches. I don't know why I keep saying LEDs, because I guess we're doing the magic wand thing. This is going to be tricky placing these components, because we have to put them in that kind of format of the diatonic keyboard, or the normal keyboard layout, right? So it's like whites and black keys. And they have this kind of shape here. So we'll see what we're going to copy and do there. But for right now, let's just go ahead and let's just place these components manually. So let's do the 5-volt regulator. So if we look at the schematic of the 5-volt, all right, regulator. So we've got the regulator in the middle, we've got the switch, we put that wherever we want, and then we've got C4, C5, and C6. C4, C5, C6. Okay, so we'll come down over here. Let's kind of deal with this. So here is our regulator, all right, and here's the C4, here's, you know, C5, and here's C6, all right. Now, you know, our question is, where do we want to put these, you know, other components? So like the switch, for now, let's just turn it a little bit, turn it, maybe put it right there. We'll put the switch right there, maybe. Right, or we could put it up top. And then here's our power LED. Now in this design, we decided to put the LED, where's the LED? It's right here next to the switch, and we decided to put the switch in the corner. So we're gonna kind of stick to that same kind of thing. So we'll put the switch down here, and then we'll put our LED here, and then we'll put this resistor here. All right, these test points, don't really care about them right now. Now, the rat's nest may be annoying you. It's definitely annoying me right now. I don't need it. So again, if we go to, I believe it's under connections, then we're going to say hide all. All right, there. All right, so that's better. Okay, so now that looks pretty good. So let's go ahead and kind of position this up here a little bit, give ourselves some room down here. All right, we don't know exactly where all these things are going to go. Right now we're just kind of, remember, we just roughly place, let's get rid of this designator comment situation. So let's go there and we'll delete, and that's just some extra text on top of these things. All right, and we know we're going to have an on-off here, so we can kind of put this SW1 here, and or maybe we can put it here for now. Could mess with that later. Okay, and then these test points, like I said, they can really go anywhere. They're just copper pads, so we'll leave them there. All right, so now we've got our regulator kind of set. Control S, we'll save that. Okay, we'll hit 3 there. All right, so that's not bad. Nothing's getting crunched or anything. All right, so let's go back 2. Okay, so now we have our timing circuit here, which consists of U1, C1, C2, C3, and then also R5 is going to be close to us. So let's find R5 here. Let's get all the switches. And if we go back to the design here, and we look here, so R5 is kind of fixed, C1 is fixed, C2, C3, these are all kind of can be close to the chip. Then these all these resistors here, they're going to get switched in and switched out by the switches. Okay, so we have to decide how we want to do that. So if you look at this design, what I did was I put each one of the resistors right above each one of the switches and then just basically let it switch in. But over here in the timer, it's C1, C3, C2, R5 are real tight. So we're going to do that, and we're going to do something similar down here. All right. Okay, so let's go ahead and do this, and let's grab R5 here. All right, so let's go, and we'll zoom in here. Okay, so again, what I'm looking for is you want to kind of remember what things look like. And this is why it's nice to have 2 screens. You know, I have multiple screens here, but I can only show you one. So normally I would put the schematic over here, drag it over to another screen so I can see this, so I don't have to keep going back and forth. But C3 is the bypass capacitor, C1 goes on pin 5, and then C2 is down here on this pin 6. All right, so C3 is the bypass. All right, so let's see here. So C3 is the bypass capacitor, and let's zoom in. All right, let's zoom in more. There's V sub CC. Okay, so I could put this right here. I can also do this. I can put it right here above. Remember how we kind of do this? All right, that gives us some room for routing. All right, and then C2, let's zoom in here. All right, C2. Okay, this is this. So for now, let's just stuff it right there. We'll put it right there for a minute. And then C1, okay, C1 is this net C1, and I'm just turning it around, hitting the space bar. And so maybe I kind of like this. What about, let's turn it like this, and we'll put, both of these have grounds right to the right, and then there's signals. All right, how about this? This is kind of nice. We'll do, what about this? Put this here and put this here. All right. Okay. All right, and there's our bypass, and we want that pretty close. So we're gonna, keep it here. But you know what? We've got these 3 capacitors here, right? Now, no one said that we can't, do this. This would be kind of cool. We could do that. And that looks kind of pretty, right? And again, it's very close to the V sub CC pin. This is the bypass. C3 is a bypass. So that would work, right? And that should give enough room for routing. So we could do that. All right. And then the only thing left is R5. And let's flip this thing around. So R5 wants to go across V sub CC, and it wants to hit this net R5 here, right? If you look at the wires coming from it, so V sub CC. So we could put it there. Another thing we could do is we could put it here, and we could move these a little bit out. I don't want to get that C3 too far from everything. All right, but we could do this kind of thing. Could do that. Uh, Another thing we could do is if we want to, if we really like the bypass close, we could put it up here, do that kind of thing, make this R5. There's a lot of ways that you can do this. And when you have lots and lots and lots of components, it's going to make it harder and harder for things to route. We have a lot of space here, so we don't have to keep things totally completely on top of each other. All right, we can do that kind of thing if we want. Or again, we could say, hey, no, I want the capacitors close. Let's just move this like this, and we'll put this right about here. We kind of like that. And then we like the idea of just having the capacitor, all three capacitors neatly and nicely like that, right? That's fine. If you want to do that, go up there maybe a little bit. Okay, move that down, and then we can just put this right here, and then this is going to have to be routed. Now, no one said that we don't have to, we could put this right here too, right? And then if we zoom in, we've got our V sub CC, and then the only thing that has to be routed is this, is this net right here coming out of here, this net R5, which ends up right here, all right? So that's another possibility, right? So, just for kicks, I'm just going to leave it like that. I'm going to flip this R5 like that and leave it like that, okay? And we can move and clean things up later, so we'll just leave it like that. Okay, so now we have our entire timer. There's our timer. Let's make sure we save that. Okay, good. All right, that looks good. We've got our voltage regulator over here. We're going to move this stuff around a little bit more, obviously. Now we have our amplifier. Now, let's talk about signal flow. The signal is going to basically be generated here. Then we've got our resistors under here, which is going to be selecting our note. Then the output of this, which is here on pin 3, here, that is going to go into this amplifier and be amplified. All right, so we're going to get that amplification. So we want to basically, this amplifier, if you look at the design of it, over here, it has this input on the left side, and then it's got this capacitor, these two resistors, the diode up here, and the transistor. It's kind of going from left to right. So when we design it, we're going to kind of flip it around and make it right to left. That's all. So again, we have to look at this because we don't have it on the screen. So our big bypass is C8. We've got R2 and R3, our setting bias. We've got Q1, D1. All right, so C7 is where we want to enter in the signal in. All right, so let's go ahead. And where is C7? So here's C7. All right, and if I kind of bring this over here closely, and so here's net C7, here's net C7 plus and net C7 minus. So which one is this? This is net C7, should be, all right. Okay, so something is backwards right there. Something is backwards. Okay, so this right here is backwards. So C7 is actually backwards. So that's a mistake. So C7 is backwards. Now the nice thing about this is all this would have done. So this is good. So we made a mistake. All this would have done is in the design, the plus would have been on the silk screen, and you could just turn the capacitor around. We need the plus side to be over here. All right. So what we're going to do is by the time you get this, let's see, I will have updated this, and it probably will be okay because the forked version you'll fork will be okay. But this is how it would have happened back in time. So anyway, let me go to the working copy. So here's the working copy here. All right. And all I'm going to do here in the working copy is I'm going to take this right here, and we're going to delete that. And then we're going to take this right here, and this probably is going to go all the way up. So I don't want to make that much of a mess of things. So just put a little trace right there for a second, and then I'll select this little piece. And then if we press this, we press break wire. Yeah, we can just break little pieces of wire. All right, and good. Now let me take this, oops, and let me flip that around. There we go. Flip that around. And now we'll go W. There we go. So, not a big deal, but you definitely want to have the polarity in your design showing showing the correct direction. All right, so we want this to be the plus side, and we would just turn the capacitor around. It would have been okay, but we want to show the polarity right because we are using a big electrolytic here to AC couple this. Okay, so this is correct right here. So the C7 is correct. So now what this is going to result in is over here. We've already got this whole thing routed. Where is C7? C7 should be over here. So we've already got this whole thing routed. So what's going to happen is this is going to flip around, and like I said, we could have just flipped the capacitor around. But when I make an engineering change order, this is going to flip this around, and then it's going to break these two leads right here. Okay, so let's see what happens. And I'm just doing this I'm just doing this in the work copy right now. Right. So what I'll do is in the work copy, I'll recompile it, and then now if we go over to the work copy, and we'll say compile, and then I'm not committing anything yet. We'll say go over here and we'll say update to the PCB. Okay, right. Okay, so that net goes to that net, so unmatched reference net, plus and minus. This, okay, so we'll just say continue. All right. And so a bunch of things are happening here. So we're just going to say validate changes. We'll say execute changes. We'll close. All right. So now we've lost a couple nets. And what's going to happen is what it does is it shows you this by these lines, right? So now these lines are here. And these nets are now incorrect because it's flipped this. So the first thing that we're going to do, and we're just doing this in the work copy. Okay, so this is just, so we're going to delete that. We're going to delete that, and we're going to delete that, and we're going to delete this piece right here. Okay, so everyone is confused. All right, and we'll delete this little dot right here. Okay, now, and this test point technically should be okay. I'm not sure why it's giving me a problem here, but I'll just delete that, and I'm going to grab this test point, and oops. Let's grab this test signal. All right, let's leave that for a second. I don't know why it's freaking out. But now you can see that the capacitor, the way it's placed, it was flipped around now. So now it's got the correct polarity because we switched it in the schematic in the working copy. So we flipped it. So now in the PCB, it's kind of still sitting here. So now what we got to do is we got to take this, all right, and then we're going to just spin it around one more time. Come on. All right, there we go. We're going to spin it around, and now we're going to re-pour. Now the ground has all got to be re-poured. Okay. Now the C7 here, this is messed up, so it's got to spin this around, and it's not cooperating. Okay, C7. All right. There we go. Again, you know, you're seeing in real time these tools do weird things. All right, so now let's look at the layers here. So there's the bottom layer and there's the top layer. All right, and we need to get this signal here, and it's on the top layer right here. So we're just going to go lay down a track. So we are going to go to route. We're going to go to interactive routing, and we're just going to manually do this. So we got this track right here. Okay. And we will double click. There it is. Okay, do a re-pour. Okay, now that's happy. Okay, and now we need this track right here to replace this. Now we'll re-pour. Okay, and now going through the two layers here, everything should be okay. So now what we basically switched this capacitor around. We really didn't need to, but we want the polarity to be correct, so if someone stuffs the capacitor, it looks right. And we noticed that. And like I said, when you don't build these things, since we're just doing this completely design only and not doing any prototyping, you make mistakes like this. Luckily, that was a simple mistake, and we could have just turned the capacitor around, but we fixed the capacitor in the design. here, and then went and updated our printed circuit board. Now, the question is, are we missing any nets? Okay, so let's go ahead and let's run the tool and make sure that we don't have any missing nets. So the first thing that I want to do is I see a bunch of uncommitted files here. Let's just commit everything. It actually makes a little picture of a cloud. Cute. All right, and right here, go here now, and we will commit all this. We've only been working with the work copy here. All right, so we've been working with the work copy. We haven't gone to our final design, but that's good because we haven't finished it all. Okay, so now this is good, and now what I want to do is I want to go to, we want to go back to here, all right, and then we want to go to rules and violations. That's not it. Tools, that's not it. It's under home, I believe. Under home, yeah, design rule check. Again, always trying to figure out where things are. Okay, so now we've reset the error markers. Let's run the design rule check here. Okay, run design rules. All we're looking for is unrouted nets. All right, so error 0, warning 0. We got some rule violations. We know that those things are just short circuit, constraint, rule violations. What's this? Clearance constraint. Where's unrouted nets? Unpoured. Go down here. I'm going to look at that one short circuit, rule violations, unrouted nets right there, 0. That's all I really care about. Now, short circuit constraint allowed equals no. I'm not sure what this is talking about, but it looks like it's this TP signal, which it's giving us some trouble. It seems to be confused about. All right, so this TP signal, all right, so this TP signal is right here, and all this is, if we go back to the design, TP signal just goes on this signal coming out of pin 3 here. It's just the pad connected to it, all right? So I am not sure why this thing is not liking this, but let's try, if I grab this, can I pull, and it's not letting me move this away, which is actually irritating me quite a bit. So I'm not sure why I can't move this away. All right, and then, let me see, can I move this in here a little bit better? Let me try this. Let me move this. Yeah, it's not letting me. I can't delete it either. All right, so that's something for another day to figure out what is going on here. But obviously, this is fine. We want this test point right here, and we want to be able to access that. So I'm going to leave that. Now we press, put it in 3 mode. All right, we get our 3D view, and this is all fine now again. All right, so everything's okay. The capacitor is now in the right polarity visually as well as in the schematic. Okay, all right, so that was just the working copy. So now what I will go do at some point is I'll go back and as a matter of fact, I'm not going to, because what's going to happen is if I go back and fix it, when you fork the original, you're going to fork a copy that's already been fixed. So I'm going to leave it broken, and you're going to know when we talk about this that this has to be done. So anyway, we'll just leave it like that, and there is a mistake, because otherwise we have to kind of go back in time, and we don't want to do that. All right. Okay, so now, here we go. Good. All right, so and you know, and this is why when you design something by building it, you find these little mistakes. You look at your schematic and you're building a prototype and like, oh, I have the capacitor wrong in the schematic, and you fix it. But we didn't do any of that, so this is why we are coming up with these kinds of things. And now luckily we've only found one here. All right, so let's go back to our schematic. So we have this thing backwards. Good news is it's not all routed and everything. So all I'm going to do is delete this and fix this right here. So I'm going to delete this wire. That's real easy. Now when I select this wire, it grabs the whole thing. I don't want to delete the whole thing. So if I right click on here and I hit this break wire, see it has this little little doohickey, little selector. If I grab here, I can just like break a little piece of the wire. All right, so that's kind of cool. Now I'm going to select it, switch it around. There we go. Press W, go back to wire mode. Press W. All right, and then grab it, make sure it's actually connected. Good. Okay, so that's good. Now what I'm going to do is I'm going to go recompile. Whoa. I'm going to go recompile this. Okay, so we're going to go recompile, and let's make sure we're not messing with the work copy here. All right, so we want the schematic. We're going to compile it. Okay, schematic is compiled. Now I want to go over here, and I want to import changes. All right, import changes. All right, and we're just going to hit continue, and we're going to say validate. We're going to say execute. We're going to say close. All right, and now the C7, what I'm looking for is the output here should go into the positive input of the capacitor. That's what it should be. All right, and sure enough, it does. So there's the positive input going into the positive, so it's C7 plus, and it goes into C7 plus. Okay, that's better. That's what I want. All right, so now, all right, so this is the, so this whole, that whole thing was just because we were just trying to get the amplifier designed. Okay, so there's the input. Now we know that after that comes the transistor, right? And this is going to go into the base of the transistor, which is definitely right here. All right, so that's the base of the transistor. Now we also know that we've got R2 and R3 doing some kind of bias setting here, right? So we zoom out and we can flip that around like this. All right, now if we go look at this other design, let's close this rule verification. If we go look at the other PCB, we see that the way that I did it was I have C7, then I have R2, and I have R3 right next to each other right here, all right? So if we look at ours, we've got C7, then we've got R2 here, and then here's R3, all right? And again, let's zoom in. So this is a ground, so we can turn the ground all the way around. There we go. All right. And now, just because in the schematic we have kind of R2 and R3, right, like that, doesn't mean we have to do it like that. All right. So what we can do is we can pull this back, and maybe I'm going to drag R3 around here like this, and I'm going to probably end up with exactly what I did with the other thing. So here's our C7, and I'm just going to put that right there. And we'll grab R2 here, grab R3. All right, now we got this. This looks pretty good. Pretty happy about this. Now, this output right here, again, we look at that output. The output is going right to this node here and right into the base of the transistor, which is pin 2. All right, so this is pin 2 right here, and then pin 1 is ground. So what I'm going to do is I'm going to line this up. I'm going to just line this up right here, just like that. So there's just a straight shot right there. All right, so that should give me some room. Just move these. Let's move this Q1 here. And now I might want to rotate the transistor. I'm not sure, right? But right now this net D11, so that's where that diode is connected. All right, so let's back out here. C8 is our big bypass for the power to the whole system. So we're going to want that fairly close here to the transistor. So this is ground here. So this is V sub CC here, right? So we're going to want this fairly close. So just for now, we're going to place it right there. All right, and now where is our diode? Here's our diode. All right, so our diode is, and our speaker, the speaker is the output. So I'm going to turn it like this. And then the diode is kind of in parallel over the speaker. So I can put it like this maybe. All right, and then what I can do is I maybe can move this whole thing kind of maybe here, something like this we could do if we want. All right, and now we look here. So here's net D11, that's going to connect there. There's V sub CC, that's good. All right, and then here's the base, and this net, this other net right here is going to have to connect through here. So I think that'll do. All right, and then we've got C8 right here, and we can put this. So this is where the power is going to be connected to the whole little amplifier. All right, and we can put this capacitor right above here, All right, so here's V sub CC, and we can put it right there if we like. So there's V sub CC. So all this is going to be V sub CC. All right, so that looks good. You know, and that's one way to do it. All right, and you know we've got so much room it doesn't really matter. And then here's TP sig. So that signal we're going to put between here. All right, we'll move this over here a little bit, and this is just so we can see that signal. All right, and now we're going to kind of place that. Let's back out a little bit. Look what's going on here. Okay, now we know that we're going to have this big speaker here. Let's take a look at this schematic here. All right, and to give you an idea, so speaker 4 to 8 ohm, this size right here, it's a couple inches. It's kind of a standard speaker size. So I'm gonna copy that because I already measured it. All right, and we're gonna place it, and we of course copied the wrong thing. Never fails. Nothing works right. Let's try this again. All right. So we don't want this. We want this right here. All right. That should be it. Okay. So I'm going to copy that, and now we're going to go hit escape there. All right. Now we want to make sure that we are on the top overlay. Top overlay is where we want to place this. Okay. On top overlay. Now if I just come here and I press Control, yeah, that's not what I want. So let's find the top overlay. Okay, let's take the top overlay and now Control V, and still not getting me the object. All right, so that's fine. It's going to fight us. I'm not quite sure what's going on there, but you know, we're just going to move on. So let's do a full circle right here. All right, we're in the top overlay, supposedly. All right, there we go. And then now what we're going to do is we're going to select this object, and we'll go over here, and you see the radius is 1.5, so 1500 mils, radius would be 3 inches. All right, so that looks like it's about the same. So let's go take a look at this one. And if we click this object right here, 1500 mil. All right, so that's what we want. So that's good. Okay, so we're just going to take this thing and kind of place it right about here. Just kind of eyeball it for right now. All right, and now we see we've got this speaker port here. So now, you know, maybe we want to move this right here to give ourselves a little bit of room. Then the speaker connects there through a pair of wires, right? All right, and then we've got a lot of room here, so we can move this thing up. This is annoying, so let's move that. Okay, and we can go just like this. Zoom in a little bit. We can line up this output right here to this capacitor if we want. That's not going to hurt, right? That's nice. We'll do that. Okay, and then again, we've got a lot of space, so you know we can back this out a little bit if we want. And this is the whole thing. There's no correct way to do things. There's just, you know, what you want to do, right? And then over here, maybe we can just move this over a little bit. Okay, and then we've got these test points here, and maybe we move these test points over a little bit. All right, and now let's work on this right here. Okay, so we go to our design again, and basically it's C4, C5, and C6. So C4 is on the input, C5 and C6 are on the output. Okay, so again, what I'm looking for is always just making things. We know we have to get the power coming in on one of these sides here. So here's the ground. So here's VBAT. So this is going to, you know, come down on the top layer, the bottom layer, and run in here. So now the orientation of the regulator I don't like. I want it to be rotated. So let's zoom in. So I like to think of V sub CC coming in on the left side. So I'm just going to grab this and rotate it. So in this case right here, the way that this particular part is pinned out, right? If we look at the pin out of this, oops, go to this particular part, V in is actually on pin 2, and then V out is on pin 3, and ground is on P1. A lot of times it's oriented in a different way. So here's the actual input. That's that VBAT. So there's our input right there. All right, and here's our output, V sub CC. So this is good. So we could turn it like this, and then the output's here. That doesn't really make sense, right? We could turn it like this, but this right here to me it makes the most sense. So we're just going to turn it like this, all right? And we're you know, basically always spreading things out, making them nice. And then we have these two capacitors. So what we're going to do is this is kind of a bulk capacitor, and which is larger. And then we've got this C6 capacitor here. So what we're going to do is we're going to put the C6 closer because that's kind of for high frequency noise. And again, we're going to space this out a little bit. All right, and then each one of these little demarcations, grids, is 10 mil. So we know these are like 20 mil. So, you know, we're putting in some space, but not too much space. All right. And again, there's no correct way to do things. There's definitely better or worse ways to do things, but the whole idea is we just want this to be neat. We want it to be easy, and we want it to be nicely spaced. All right. Now here's our output here, V sub CC. And now look at our capacitor. Here's the output here, V sub CC, and here's V sub CC. So let's spin this around. All right, so spin that around, make that nice. Okay, there we go. So now we got nice V sub CC, and then V sub CC is going to come down. This is going to get, this is our main feed right now. All right, now this VBAT switch, where is this going to come from? It's actually coming from the switch. So see it right here. So here's VBAT. So this is going to come directly from the battery. Here's the switch. So when we put the switch to the left, it's going to be on, and then this lead right here, this one, is going to feed the input of the regulator. So from the battery itself, all the way up top, here's VBAT. That's going to run down all the way to the center pin, and then the switch pin is here, which is going to run over here. So that's fine. All right, now we have some ugliness here. So, and we can put ground anywhere. Okay, these things are not easy to grab. I'm going to tell you that right now. They don't want to grab. Okay, they don't want to select. All right, and then here's C6. Let's fix this. Grab it and rotate it around. We'll put it up here. Okay, Control S. And again, I could just speed this all up, and you can too. You can skip through it, but you're never ever going to see someone just sit here and design a circuit board unless you sit and watch it. And it's what I'm not sure that I'm going to talk about that's important that I want you to hear. All right, here's some more text here. See this little purple whatever. We want the K. There should be an A. That's the cathode, but I don't want this designator. That's just mucking things up. Okay, K means cathode. That's the flat side of the LED. And I know C is cathode. Why is it K? Okay, here's our LED, which now this is going to get powered. This LED right here, this net LED LED, is getting powered over here. So now if you look at this, here's V sub CC. And the LEDs right here. So what we can do is, since V sub CC is kind of being generated over here, and we've got the LED here, why don't we move the resistor on the side that it should be? All right, we'll move it on this side. And then what we can do also is, you know, we could rotate this around like this. We could put it right here if we wanted to, or we could put it right here. You know, so again, you know, you just got to kind of decide what you know, what you like, how you like things. And then I'm going to turn this around like that. And there we go. And now what I'm doing is I'm looking at the vertical height here and the vertical height here, and I'm just trying to center it a little bit. So if I were to snap a line, see this line right there? It kind of hits right about here. And then if I go here, it hits there. So maybe I'll move this up a little bit. All right, and then we got this resistor here. Maybe I'm going to move that reference designator there. Maybe I'm going to move this reference designator there. Maybe I'm going to move this up a little bit here. All right, and then again, we got these test points, these annoying test points, which are, you know, very important. So now maybe I'm going to move all this up a little bit, and then maybe I'll move these test points here. And then let's get these test points at the same level here. And then maybe, you know what? Let's do this. These test points, why don't we just put these right next to each other? And then we'll put a ground right here. Okay, and then we'll put the V sub C right there, which is backwards. Put this one up here. Put that one there. Okay. And then now we can kind of get these things out of our way a little here. Yeah, the selection logic in these tools is always a lot of fun. All right. Now again, these can really be anywhere. These can really be anywhere, so we don't have to put it right here, right? But you know, it's hidden. This is just for testing. All right. Okay. So that's kind of cool. So now we got our resistor here, we got our LED here, we got our switch here. That's good. We'll do annotation later where we put on and off and put all the cool labels. If you look at this, I got a bitmap font, bitmap font, and then put these little different labels on here, regulator, on, off, and all that kind of stuff. So we'll do that later in ours. Okay. Okay, so this looks good. I'm happy with this. And now zoom in and make sure that the actual signals are fairly close. This helps the router. So V sub CC is right here. Ground, we know we get those for free with the ground fill. There's ground, there's battery, and the battery is going to come from the switch down here, right? So we probably, you know what, we could probably rotate this around, but over here you see the plus, the orientation, here's plus here, and I kind of like the plus here. It keeps the capacitors in the same orientation, right? This one right here, there's V sub CC, so that's going to fit good. The switch is in the correct position. You know, so, you know, I like switches that turn on to the left, not turn on to the right. So this will turn on to the left, so on will be here and then off will be there, but you could flip it around if you want. All right, we have our timing circuit, that's all there is to it, R5, and then now R6 through R17 or whatever, those are, what is it, R6 through R17 and all the switches, those are the actual diatonic scale keys, which we have to position. We've got our amplifier here. A lot of ways to move this amplifier away, tighten it up and all that, but we're just going to leave it like that. That looks pretty good right now. Another thing is I'm going to want to place this thing kind of perfectly centered at some point, right, and kind of measure up and down. I can eyeball and see. If we look here, we got 1, 2, 3, 4, 5, 6, 7, 8, 9. And down here we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's pretty good, actually. That's pretty good. So, I mean, if I wanted to, I could grab this and just move it a little teeny tiny bit, but that's pretty good. Okay, this is a big mechanical object, right? So it's a big speaker, right, like this. Right, so we know that the speaker is going to be sitting there now, so I don't want it too close to the edge. Now another thing, the speaker itself, we can do one of two things. We can face the speaker towards us, right, in the design, so it would be facing us, or we could place it on the board, you know, flat like that, and then put a bunch of holes in the board and let the sound go out of the back. I'm going to leave that to you. You can do whatever you want. So if we place the speaker towards us, it's going to sit on this. So you could even put a small hole in here, right? And then that could, the speaker could go through there and kind of, you know, set it in there. We might do that just for fun. But for now, we're here. Now, so now the next thing that we have to do is set down these keys. And this is actually fairly tedious, setting down these keys. So what I'm going to do is I'm going to stop here real quick, and then when we come back, what we're going to do is we're going to, this is not easy to draw. So I basically had to draw these, and you can see these are the white keys and the black keys. So I had to kind of draw this, and they're spaced in a very specific way. There's ratios of heights if you look at kind of piano keys. So what I did was I went over here. Where is it? I think this is it. No, this is it. One of these images is what we want. This one. So I went over here and looked, and here's our C4. So it's white, 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 and you got the 2 black keys, then another white key, then the 3 black keys, and then you're done. So I wanted to kind of mimic this, and what I also wanted was to place the switches in such a place that they have a good position as far as leverage. So say you wanted to like 3D model the keys. What if you wanted to actually build keys onto this thing, maybe in a 3D modeled case that's 3D printed? Then what you might do is you might have these long keys, and then as the key presses down, this is probably the best place to put the switch. Same place, you know, best place to put the switch. So that's kind of what I did. So it's very simple. It's going to be R6, switch 6, R7, switch 7, and so on. And that's the way the keys go with all these labels. So that's all we're going to do in the next video. We're just going to pause here for a second. Is we're going to drag these things down. So I'm going to basically take this. I'm going to take this. I'm going to take these, and we're going to put them right down here, and we're just going to build this keyboard right down here in the bottom. But the first thing that I want to do is Let me see if I can grab it. Of course not. Of course I can't grab it like that. That would make too much sense. Let's put it back up here a little bit. Let's move this super annoying test signal, and we'll stuff it right there. And stuff it right there. Okay, there we go. And then back out, and then let's move these down here. We'll do them maybe one at a time. Okay, so what we're going to try and do is we're going to try and copy this graphic, all this line stuff, which I painstakingly drew with lines and rectangles. It was a huge pain. So we're going to try and copy that. And before we do that, let's grab this text. I'm going to copy that text. I'm going to go back into RPCB, and I'm going to paste it. And there it is. That gets me that font. And I'm going to paste it if it allows me. And if I double click on this, you can see it's text, whatever, and then its font name is Bitmap, just called a Bitmap font. There's, all these different fonts in here, and it's just a very retro looking font, Bitmap. All right, so we'll take that and then we'll copy that into a bunch of positions for all the text annotation. All right, so we got a lot of work to do. We're getting there. All right, so let's stop here and I'll meet you in the next video and we'll start doing the buttons. Okay, all right, bye for now. All right, welcome back. We are continuing with the 555 organ, or the organator. So this is the work copy, of course, the finished version of it. So now if we look at our version, what do we have here? So we placed everything except for the buttons and then the resistors that go along with each button. So we're mostly happy with where everything is. And of course, this is up to you, and this is, it's a learning process. You have to figure out where you like putting things and all that and how you like doing it. It's just something that you get the hang of over time and just decide where you want to put things. Just like right now, I said, I don't really like that there. And, maybe I want that centered and stuff. And you can do this for hours, really. You can just sit and kind of play around. All right, the next big thing is the whole diatonic keyboard and what it looks like. So if we go here back to this page, this pianosynth.com image that I found, we see that we want to copy from C4 to B4 here. So we've got basically 3 white keys, we've got the 2 sharp keys, then we have another white key, and then we've got 3 sharp keys. So we want to make sure that we have this kind of pattern. So I drew all this, and it was fairly complicated to draw on a pane to draw this stuff. And here it is here. So the philosophy I took was wherever there's, this is a white key, a white key, a white key, a white key. Wherever there's no white key, this is obviously a black key. So you could draw something and you could fill this in and all that. I mean, it's gonna show up on the silk screen, but this is really just a placeholder so you kind of know. So if you just have the printed circuit board and you put the 4 mounting holes and maybe put it up on standoffs, you can sit and play with it and know where the keys are. But ideally what you might want to do is put some stickers on here. You could do that. You could print some stickers out with your inkjet or laser printer and stick those on there to make them look like a keyboard. That would be cool. Or more ideally, you could 3D model some plastic and make a keyboard and actually make all these keys. Then you might have to drill some holes in here or place some holes in here. So you should think of that beforehand if you want to do it. All right. So all we have to do is place these resistors and these switches. But first what we need to do is copy these graphics, all right? So this is going to be a painstaking process, and so what I'm going to do is I'll kind of start doing one, and then I'll just kind of speed the camera up because I'm just kind of be doing the same thing until I get all of it down over there. All right, so the first thing is let's try and copy the text. All right, so I want to just copy the text. So there we go. I think I have it. So now if I press Control, and you know what? This tool, I still don't understand its whole copy and paste mechanism, the way that things are selected. So if I press Control C, that should be copy. All right, I've copy. I've copied this. So now I would expect that if I come over here and press Control V, I would get that whole thing. All right, so I did. All right, so that seems reasonable. Now we'll go over to our other R version, and we'll make sure we're in the top overlay, and then we'll press Paste. All right, so there we go right there. And what I'm going to do is I'm going to leave these little bars here, these little bars, because these bars represent, if you go back here, these bars represent the keys. So that'll help us place the keys. Okay, now let's go ahead and let's try and grab one of these keys. All right, so if I do that, I get everything. I get all the traces and I get all kinds of stuff. So what we need to do is go into single layer mode, right? So we'll press Shift S. Okay, so Shift S, and then now we're in single layer mode, and if we press plus and minus, we would go through all the different layers, as you see, but we just want to get the top graphic layer. There it is. All right, so now I'm going to select this key here, and you can see I've just got the key selected. Now, because these are graphic elements, this copy and paste doesn't seem to do what I would expect. A Control C, all right, and then now if I press Control V, nothing happens because I've got that crosshair. If I press Control V, nothing happens. Control V, nothing happens. All right, so now let's try this. And I'm sure if I read, I could figure out how to do this easier. So I'm going to select it again. This time I'm going to go up here to copy. And then now I've got these crosshairs. So it's almost like it's in copy mode. All right. And now I'll try paste. And okay, I've got it this time. All right. So now it's in the cut buffer. Whatever. All right. So now let's do Control V. Does that seem to work? Yeah. So Control V works. All right. So the first thing we can see is this needs to be up much higher. Right, this needs to be up much higher. So right now, we'll put the key right here and let it sit there. And then what we're going to do is we've got to move this whole diatonic scale thing up here. And then we want to kind of center it. So maybe over here a little bit, and let's go up, 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 up. All right, maybe right there. All right, now let's grab this piece again. And let's see if we can get this to cooperate with us. Oops, redo that. All right, and I want to move this, and what it's doing is it's, yeah, okay, so that's, let's do a copy again. All right, and we've got this cursor doing its thing. Let's see if I delete that, and now let's see if we paste it. Let's see if we paste it. Not doing what we want. All right, so as I said, this is, it's a pain, and I'm not quite sure the dynamics here. Let's try this. Let's click, see, we can't click copy because we have nothing selected. So what's interesting is you select this, and now we hit copy, hit it again. All right, great. And now if we hit paste, we get it right there. All right, so now I wonder if I go, can I delete this? And do I still have the paste buffer? Okay, that's good. All right, so there's the paste buffer. So let's zoom in. All right, and let's move this up a little bit. So I'm going to put this key just right under here. All right, right under the line, and we'll delete those lines later. All right, but they're just going to be used for reference right now. Okay, so that's good. So we got the first one in there. All right, and I'll go do one more in real time here, and then I will just kind of speed up the camera so you don't have to watch this painful copying. And yeah, it looks like you can grab multiple things, but again, the copy paste just does not work correctly as far as I'm concerned. I'm not sure what the problem is, and I've read on the forums for Circuit Maker that there are problems with this, so I'm not sure what I'm doing wrong. Copy, and then yeah, and then paste doesn't work. Yeah, now let's try paste again. Okay, there we go. And we'll come back here, and we'll go Control V this time. And then we're off center here clearly, so that's real helpful. Everything to make everything as hard as possible always, right? Isn't that how computers have to be? All right, and then the other problem is as we place these things, they're very hard to grab again. All right, so I'm gonna zoom in a little bit here. All right, and that needs to move up a little bit there. Okay. All right, so that's the process. So I'm going to just sit here and copy the rest of these things. So you can just watch in this speeded up version. Okay, so I've copied all the graphics here and everything looks pretty aligned. So we've got C4, C4 sharp, D4, D4 sharp. And if we kind of strike a line here, imaginary line, we can see that everything is mostly lined up. And we could probably adjust these things a little bit. So if we want to bring this down one little click, one little space, that's good. And then another thing, let's go and we'll strike a line here. And then we'll see if all the letters are hitting. So you can see C4, D4, E4, F4 is okay, but G4, G4, A4, let's move those up a little bit. And this is just, again, just to make things look nice, right? And it's just, it's a process, and you notice these things, and you're like, I could fix that, I could make that a little bit better. Centering things and all that. You just make it neat. But like anything, you get carried away. We're trying to, get this stuff done. Okay, so now let's look at this keyboard and make sure everything's cool. So we got 12 keys, we should. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's good. And then the key that goes to C4, if we look at the design, so the C4 is R6. So R6, R7, R8, and switch 6, switch 7, switch 8, and so on. So we just need R6 and switch 6. That's how we're going to start this off. And again, we can do this how we want. All right, so we can put the resistor here, for example. There's R6. Now, if you look here, what I did is we have the switch here, and then we've got the resistor here. Now what we could do is we could move the resistor up here so the resistors are all in a consistent place instead of the resistor being by the switch. Maybe let's try that. Let's try that. Maybe that's a little better idea. All right, so there's R6. Okay, so let's get all our switches here. We're just going to drag them down. All right, and then we're just going to kind of scoot them into place. All right, so let's zoom all these down. Let's get them all at the same Y height. And that looks pretty good right there, and we might as well center R7. All right, here we go. So grab all these, and we're just going to move them into position here, one by one. Grab all of them at once so we don't have to keep shifting everything. And just keep trying to roughly center everything. I'm just eyeballing it right now, all right, because I've got a lot of stuff in my way here visually. Oops. Oops. Okay, you know how it is. You click on something and the end of the universe occurs. So be careful clicking on things. Make sure you don't have something selected you don't want selected. These CAD tools are, they're difficult to develop, and especially the selection logic is never easy to get correct. If you've ever written one of these tools back in the 80s and 90s, I used to write paint programs, CAD programs, 2D, 3D stuff, just because there were none, and also just for the experience of it. One of the hardest problems is selection. When you click on an object in a multi-layer system, what are you trying to grab? Now, based on context, you can figure that out pretty well, and then there's lots of picking algorithms and stuff, so you can pick things intelligently. And sometimes I wonder if people who write these programs have read any basic computer graphics books. So sometimes they just seem like they don't know how to do things. I'm not saying this one, but in general, sometimes it's pretty bad, the selection logic in some of the programs, as I'm sure you're aware. All right, so we're more or less done here. Okay, looks good. Okay, and now another thing is the reference designators. I think I made them smaller. Maybe they're, I think they are. So for now, we'll just center them. For now, we'll just center them here. So we got R6, we got R7, we got R8. Just kind of scoot that over just a little bit. Now looking at this, I can see that this is not centered. And again, we can be accurate to 10,000ths of an inch here. And so again, it's like, how much time do you want to spend on all this stuff, right? How much time do you want to spend? How much time do you have? And then the reference designators, they matter for us as we're putting the thing together. But when when there's machine assembly, of course, it doesn't really matter, because the machine is not going to care about the reference designators. It knows the coordinates of every component. Now this one's a little bit off. Let's center this one. We don't have a lot of room in the black key areas. Okay, R14, center that a little bit. R15, these two digits are getting a little bit big. All right, that's close enough. And then R16 here, that's good. And R17, and let's do this. Oops, one up, one too high. And again, you know, it's a slow process. Just last night, I was watching some BGA routing videos to see if anyone had some clever ideas for some big BGAs I have to route. And you know, they're 2-3 hours each, and it's just a very slow process, signal by signal, you know, routing 1,000 pins. And the only way to figure it out is to watch it. All right, so you just got to watch these things if you want to get the hang of them. So that looks good to me. Now, we may have made a mistake. We may have to rotate these around so that the nets, so whatever the nets are at the top and bottom, wire easily to the switches. We'll figure that out in a second. All right, so let's Control S. Okay, let's go get all our switches now. And remember, you can pick any switch you want. I just happen to like these switches. So I'm going to start off like this. All right, and so we've got switch 6 here, and now we're going to keep these vertically oriented, I think, right? We could rotate it 90 degrees. Now, one thing I want to do, though, is as I grab this, let's grab this one, and I move it up here, and I know you can't see anything. It's very hard to see what's going on. Two things I want to bring your attention to. Since these are kind of like virtual keys, and imagine there'd be a key here, and imagine I want it to be able to press, and I want to have a little plunger, you know, in 3D, plunge down on that. We want to make sure the position, see this difference right here? The position of these keys is roughly the same. So these plungers would have roughly the same throw or depth. So if you look at this, so the white boundary right here, I'm going to put it two grid marks away. So see, this one's about 2 grid marks away. And that's just, you know, I just made it up. That's it, 2 grid marks, good enough. I'm not sure what the other one is. Let's take a look. And if we put the other layers back on this one, and if we zoom in, and if we go like this, okay, let's get rid of the other layers, and let's go like this. And why am I not seeing the grid? Yeah, lots of little things you got to figure out with this software. I'm not sure why we're not seeing the grid, so I'm not going to care. We're going to go back to ours. But anyway, the point is, I want the buttons to feel consistent as I press them down. Okay, now, one thing I want to bring your attention to, so let's really zoom in here. So you see this net C2 and this net R7. Okay, so the C, that goes back to the capacitor, probably. And then this net, see this net R51? All right, so if I grab this, yeah, see, this probably we want to switch this around. And if we put it around like this, it kind of fits a little bit better. All right, so we'll zoom it out and we'll put it up right here like that. All right, so, okay, all right, there we go. So now, if you look here, we've got this net R71 here pointing up, and then we've got this net R71 here. So really it seems like what we want to do is we want to turn these things around, right, so that they line up. So if I flip it around like that, now I've got net R71 there and net R71, and then we have these two, this net here and then this top net here. Those are going to escape. So it looks like probably what we want to do is these 6-1, see how this is 5-1, 6-1. We've got net 5-1 here. We would just want to make these, so wherever the capacitor connects, that C2, we want to face that down. All right, so we're going to take this and we're going to face that capacitor down. And then this net 6-1, right, we want it here, so I'm going to flip that around. And then see all these are net 5-1s? Those are all the common net. That is going to connect back up to our 555 timer, someplace over here, net 5.1, where is it? Net 5, right there, right? So those are all there. So we're going to face all those up. So first, why don't we do that? So let's make sure we get the 5.1 net everywhere pointing up. All right, and then this just makes routing easy. So there's the net 5.1, that one's good. This one's bad, so let's flip that around. Now we got that one good. Now we got that one good. There we go. And we're just making routing just a little bit easier on us, that's all. Just making it a little bit easier. And back out, and over here, and one thing you can see is the text now is all messed up. So we're going to have to fix that. We're going to have to flip that around, no big deal. Okay, so now we've got all the 5.1s on top. 5.1, 5.1, 5.1, 5.1, 5.1, 5.1, 5.1, 5.1, 5.1, 5.1. Okay, and if you look here real close, these are a little bit misaligned vertically, but we're not going to be that crazy. Okay, the text is okay on there and there. I'm not sure why those flipped and these didn't flip properly. All right, so I got the text right there. So now if you hold the text, and I'm going to flip it, and then I'm going to just place it right back up here. Okay, and then R9, that one's okay. Maybe we'll bring that R8 down a little bit, and maybe we'll bring R9 up a little bit. Okay, and then we got to take this one, this R10. Okay, let's move that, and we'll put that right about there. Again, we're just trying to keep these things aligned. That looks good. Got a R11, select it, and got to hold it. There's some logic about holding things and then just selecting them and rotating them. I think normally you have to kind of hold it with a mouse, and then you can rotate it with a space bar. Okay. You know, and again, I'm no expert in this tool, and I don't profess to be, but the whole idea is that every tool that you get, they're all going to have similar kind of features. So you just, you know, you figure it out and you use it, and you say, hey, do I want to use this tool? You know, maybe you want to buy a serious CAD tool like Altium, which is the parent to this, and pay 6-9K, whatever it is, plus everything else. Maybe you want to use Proteus. Maybe you want to use EagleCAD. I don't know. But they're all going to work the same. So the whole idea is you can learn this tool really well, and this one's free and it works fine. But don't put too much energy into something until you decide you really like it, because you know the learning curve is non-trivial for these things, and you got to figure out all the little tricks, like that web page that had all the tips on it, right? Which is useful. All right, and this last one, and I've got it there, and I'm just gonna kind of pop it right here. Okay, and now in this lower resolution grid, we can see we're about just a little hair above this line right here, all the text. All right, and I'm pretty happy with that. Okay, now we're going to go do the same thing with all the switches. All right, so I'll speed the camera up a little bit there so you don't have to watch. But the whole idea is I want the net C2 to be at the bottom. All right, and then I also want these switches to be aligned with about, let's zoom out here, with about 2 of these major blocks. All right, so I want C2. So I want to align this way. I want about 2 major blocks here, and I want C2 at the bottom of each one of these switches, and that's the way we're going to do that. All right, so let's speed the camera up, and let's do that. Okay, so I've done all the movement here, so let's just go ahead and do a double check together in real time. So what we're looking for is we're looking for C2 on the bottom of each one of these. C2, so this is SW6, C2, we've got C2, we've got C2, C2, and that's SW9, C2, all right, C2 looks good, C2, 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 and C2. And then if we zoom out, let's check the reference designators. Let's make sure we got everything mapped to everything correctly. R6 and switch 6, R7, switch 7, R8, 8, 9, 9, 10, 10, 11, 11, 12, 12, 13, 13, 14, 14, 15, 15, 16, 16, 17, 17. And again, double, triple, quadruple, you need to check this many, 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 many times. And also, when you're done and it's all done, then check it all again. Because what happens is as you're doing your design, you accidentally click something, delete something. I've done it a million times where I've deleted a track or moved a component or changed a component or inverted a component, who knows. Just be careful and just check, 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 constantly be checking everything. All right, because remember, we're going to build this stuff and they're not cheap. Okay, so now, before we start into our routing and so forth, let's kind of move these reference designators a little bit and get some of the ones that, off the other design here. So let's go here. So we got, and let's see if I can do this. Let's see if I hold down Shift. All right, that seems to be cooperating with me. And okay, who knows? Let's try copy. And then I'll click in the middle. All right, and then let's come here, and then we'll say paste, paste, paste. Where's paste? All right, so that actually worked. I was able to grab all that text. So move this over. Let's back it out just a little bit. Okay, so kind of like right about there, roughly. I'm gonna have to move things, obviously. Okay, just leave things there for a second. Looks good. Now we'll zoom in. We just wanted the text. Just wanted the text, right? So we didn't have to do it again. Okay, so that looks good. Now you can see this the C8 here. This is a little bit more vertically oriented, so it's a little bit taking up a little bit of space. This 555 timer, maybe we wanna, now this pin goes right here, so kind of leave it like that, but let's put this text up here and strike a line, and let's see where the text is. You're always trying to, again, make things neat, make things neat, make things neat, make things neat. All right, so that's good. Now this 9-volt battery, this definitely, we're gonna move down a little bit. So let's move this down, move this down, move this down. All right, and now let's give ourselves some room here. I want the text of the 9-volt battery. All right, we're gonna put that up there. And then we've got this V plus and V minus text here. All right, so zoom in, make sure. So there's ground, there's V plus. Okay, that's good. Now, oh, don't want to grab that. That's it. You got to be careful. Got to be careful what you grab, because everything is always selecting the wrong thing. All right, so I'm going to put this V minus right here, and then I'll grab this one, and then I'll put this V plus right here. Okay. All right, zoom out, and now let's give the cloud a second here to do whatever it's doing. I just selected this. I wanted to get, all right, it's not going to do it, so it doesn't matter. We'll go here and text height. See that 300 mil? Let's make that 250. 250 mil, just a little bit smaller. Okay, now it wants to let me do it here. And all right, so that's, there we go. And again, selection logic is always a little bit tricky. Things don't select the way you want. All right, and now again, I'm a little bit, let me move this over here a little bit, this text here, lithium ion recommended. I don't like, so one thing is when you're doing circuit boards, each one of these circuit boards is going to be cut by either a laser or a saw, something like that. And if you're real close to the edge, typically they'll tell you, depending on the company, the manufacturing company, they'll say, stay an 1/8 or a 1/16 of an inch away from the edge. Don't put anything there because as it's cut. Now, of course, these days things can be much more accurate. So you can probably get within, 20 thousandths of the edge or 30 thousandths and still be okay, especially with text because it's non-functional. But you can see, like, we've got one block here we're trying to stay away. So let's just keep just one little block, all right? One of these little blocks away, all right, and that'll kind of be our little internal rule to ourselves. So that means that we're going to take this and we've got to move this down. We've got to move this down. We're going to move it down right there and maybe center it a little bit more. All right, just trying to keep it a block away, which then means that we probably have to move this down a little bit more, which means we have to move all this down a little bit more. All right, so that's okay. So let's take this whole thing here and we'll just move it down a little bit, maybe move it this way a little bit, move it here. And we want to keep that this resistor, we won't get too close, okay? All right, and then let's go ahead and move this down just a bit also. Now we can move this down a little bit, okay? And it's all this give and take thing. All right, so now we got our 9-volt battery. Let's grab these battery indicators here, and maybe we can put them real close now to the battery leads. All right, that's cool. All right, I'm happy with that. Okay, now we've got, there's this 5-volt regulator right here. So now, depending where I want to put this, I could put it under here, or I could put it above. So if I want to put it under, we got to move these reference designators, all right, because they're going to be on top of each other. And then we've got our test points here again, which, didn't grab them both. There's that selection, that fun selection logic doesn't do what it's supposed to do. All right, so let's try it again. Let me see if I can grab the whole things this time. There we go. There we go. Thanks a lot for that. Put those right there. We'll put C6 right there. And many times you got to zoom in to get the resolution you want. So you got to zoom in if you want to get things accurate. All right, we'll put that C5 there. All right, good enough. Okay, and then we'll grab our 5-volt regulator text here. And this is just text telling us, hey, that's the 5-volt regulator. Okay, there's our on and off. Again, this is just helpful text so we know where on and off is. Okay, got our LED here, and the less text I have by the word on and off, it's going to make me less confused. So I'm going to do that, and then frankly, I'm going to move this over here if it'll allow me, and we'll just put the test points. We'll put the test points right there. You know what? We're putting them right there, right? And let's move this on and off just up a little bit, Okay, now. Okay, we got a little bit of tightness right here, right? So again, I could grab this whole thing, and why don't we just, move it over here, move it down a couple clicks. There we go. All right. Again, this is up to you. You do what you want and just make things and place things where you want. All right. So now we're getting there. Okay, so we're getting there. So we have everything placed. Now we're going to, obviously we got to do the routing, but we have some mechanical stuff we were talking about. So first things first here. Mechanically, so this looks good. Now we could go into the shape editor and we could round things off and make it all cool and crazy. You can do that, and if your PCB manufacturer isn't going to charge you extra for doing funky shapes, you can make this look like anything, some kind of musical instrument. I don't know. But for now, we'll just keep a rectangle because it's simple. Okay, so let's go ahead and let's commit this. All right, and then now what we're going to do is I want to add, so there's some things that we need is some mounting holes, all right, because I'm figuring maybe we're going to put this in a box. So let's go take a look at the mounting holes, and let's take this off of single layer mode. So all these mounting holes these are just through hole pads. So you go up here to pad, right, and then you just create a through hole pad, all right. And then what I did was, so when you're doing, and there it goes to the cloud. I press the right button and who knows what that's doing. So when you want mounting holes in your boards, okay, you have to make a decision what you're going to put through the mounting hole. All right. So if you don't ever do anything mechanical, let me show you this. All right. So M2 screw. All right, so these are machine screws. So see this, M2 screws, M2 machine screws, images. Let's look at images. So they have different kinds of heads, all right? So M2 and 12 millimeter, that means the length of it. So these are machine screws, and the 2 means its diameter roughly, so it's 2 millimeter diameter. So if we say M3 screw, right, we'll get the same thing, and and here's a little chart of it, so you can see this, if I can zoom in. All right. So these are all M3, but they're showing the different lengths. So that's an M3.4, M3.5. So these are hardier, right? So these are like 3 millimeter. And then here's all the different lengths, right? So what we care about is the diameter. So how big of a diameter do we want to make these little mounting holes, all right? So again, you can go here and look at different pictures. All right, how can we serve you better? Internet is just a complete mishmash these days. So let's say M2 screw dimensions. All right, and here we go right here, and some of these charts. Let's see if we can find a big one. Yeah, so this one's not bad. So, all right, so if you look at this, and it's for some reason having trouble zooming in, but this is showing M1, M12, M14, all these different M2, M3. These are kind of the popular ones for electronics, M2, M3, because they're kind of small. Of course, if you have really small stuff, you'd use the M1. Automotive stuff, you're using like these bigger components right here to bolt things together. Anyway, so it shows up here kind of what these dimensions are. D2 is the head size, and then this looks like D0 here, or just D. I can't tell in this image because it's horrible. Maybe we can go to a different one. And let's see here. M3, how about, that actually wasn't bad. It's just such a bad, these are, zoom back out. Hold on a second here. And bear with me. We'll say machine screw size chart. All right, let's see if we can find one of these that's a little bit better. This Grainger is and of course we can't make that bigger. Boy. All right, sorry guys. Okay, so what I found here is metric. So the M means metric. The machine screw meaning it's a machine type threading, so it's not for wood. All right, so we can have different kinds of heads. So this is a Phillips head. You could have a flat head. You could have something where you use an Allen wrench, a hex wrench. So I don't really care about the head. So what we care about is the diameter here of the screw. So nominal size M2, the thread pitch is 0.4, the head diameter, forget about that. And then this is what we care about right here, this M recess diameter. So this is how big you want to make the hole kind of, so 2.5 millimeter. So the bottom line is with an M2 you want 2.5 millimeter, with M3 you want 3.1 millimeters so that it would fit inside. So if we want to use, so M2 is big enough, I think. So we just want to make the size of the hole maybe 2.5 millimeter, right? So this is the whole point I'm showing you right here. You have to pick what kind of size screw you want to put through these little mounting holes, all right? So all that giant exhaustion was for that because you can't find anything on the internet. Now if I grab this right here, I already kind of made this. So if you look here, this hole size is 125 mil, all right? And this 125 mil, of course, is in thousandths of an inch. And if we convert that, that'll end up being around the 2 millimeters. All right, so what we're going to do is we could go and we could just create a pad here. So what I'm going to do is let's go to our other one. Let's go to our other one. All right, and so we're going to go to pad. And right now we'll just kind of do this. So we'll put our pad right there. All right, so now we've selected this pad and see the hole size. So now let's put 2.5 millimeter. All right, so that's the whole size, 2.5 millimeter. All right, and then we need, so see this edge around it right here? So see this X size and Y size? So watch this. If I put 80 mil, and then if I put 80 mil, all right, so see what that's doing? It's kind of widening that out. So what we're going to do is so this is 90, this says that it's 98 mil. So that was that 2.5 millimeter is about 100 mil. So depending on what reference you use for those machine screws, so the other one was 125, so we'll stick to the 125 mil for the hole size. All right, and then down here on these two sizes, let's go and look at what I had here. 150 mil for the overall size, all right, because these holes are going to be plated. The holes are going to be plated, so there's the actual hole, and then we need to make the plating size around the hole. So that's 150 and 150. Okay, so now if we click back, so there's our hole, and you can see it's very small. So this will allow us to have some decent sized screws in there. All right, so now we got that. Now another thing, when we click this, see it's connected to no net. All right, so let me do this. If I just select it over here, see there's no net it's connected to. Now what if I wanted to connect it to ground? So I actually wanted the screws to be grounded to the ground planes, right? So we could do that. So we can actually connect it to the ground, right? So we can connect it to the ground, and now it's connected to the ground. All right, so when we draw a ground, it will be connected. Okay, so now let's go place these things. All right, so right now we're on this 10 mil grid. So first, let's just go over here and let's zoom in here. All right, so this is really close to the edge. So what I'm going to do is I'm going to back out 2 and 2. 2 and 2. All right, so 2 and 2, and if we go to our tools here and we measure from here to here, all right, the distance is about 100 mils, all right, 110 mils, all right, because we're a little bit over here. So each one of these right now is 50 mils, all right, so this is about 0.1 inch of spacing on each side. So let's come here and maybe I want to bring it in a little bit, just like that. Okay, so the rule is we're going to put about 100 mils away from the edge, all right? 100 mils away from the edge. Okay, so let me copy that. And now we have to play with the wonderful copy tool. And then paste. Drives me crazy. I got to figure out what I'm doing wrong with this whole stupid copy thing. Let's try this. There. Okay, copy, paste. Okay. I think you have to keep the crosshairs active. All right, so just 2 and 2. All right, that looks good. And then these things need to be perfect, all right? So what I'm going to do is I'm going to strike a line here and look at it, all right, and then look at it like that. So that's good enough. Now what I'm going to do is I'm going to take both of these, all right, and I'm going to copy and I'm going to paste. There we go. So I copied and pasted. Now we're going to have a little bit of a problem because we're not sure what we've got colliding over here. So I'm going to zoom in. All right, and we want to put these 2 from the edge here and 2 from the edge here. So see that and that. Okay. Now we got the batteries in the way here clearly, so I'm gonna have to scoot that over. No way around that. And now I want to make sure. So if I zoom in at this level, this little edge here is over the top, and this one is over the right side. I really care about all this alignment, so we got to make sure. So let's zoom over here. Just scroll over. All right, and you can see this one's perfectly inside. It's perfectly inside. All right, so we got to make this one the same. Got to make this one the same. All right, so let's back it out right to here. And can I go one more? No. All right, so I'm going to grab this down. I'm going to grab this over. Okay, so that one's good. Now let's go down here. All right, this one's, back it out. Okay, this one's going to go here, and this one's going to go here. So now we've got our nice alignment. Now, if I look at the bottom here, let's go over here. All right, that looks good. Okay, so now this says 2, and this says to ground. So apparently it didn't copy that. So I'll go here, see it says no net. Let's make this say ground. All right, so these are going to be grounded, so be careful, right? Which is good because maybe you want to ground the electronics to the chassis or something. All right, so let's go here and we're going to set ground. Okay, and we're going to scroll up top here and we're going to set this one to ground. All right, good. Okay, cool. All right, so now let's see, what have we done here? So we've created some mechanical holes in the system so that we can mount this thing. And now because the board is big, you might want to put one more hole in the middle just to kind of set it off. But I'm not going to because you'd have to route around it. But just to let you know, when you have a big board like this, here's the side of the board. It's going to flex, right? It's going to flex. So put another hole in the middle, or you don't have to use a hole. In your plastic enclosure, you can just have some standoffs, some plastic, and then it can rest on the plastic. It's mounted through the 4 holes, but rests on the plastic. That's fine, and then the board won't flex. We don't want the board flexing, especially because you're going to be pressing on it, right? Okay, now what's the problem we see here? Well, this is okay. This is not going to collide with anything. There's no mechanical collision. But now look, we've got this right on top of our on-off switch here. So we got to do something. We got to move this over, right? No big deal. No big deal. Let's just move it over. So let's grab these components right here, this LED. So what? I'm going to move it over here. And then let's get this out of the way. I don't want to select everything here, unfortunately, so I'm just going to have to grab this, and I'm going to move it over. All right, and then remember the screw might have a washer and a couple other things here, so give yourself a little bit of space. All right, and from experience you realize this. You're like, oops, there's not enough room for a washer or whatever. So okay, so that's better. And no one said we have to put the LED here. We could put it up here if we want, or you can put it over here, wherever you want. Put it by the speaker, but I'm just leaving it there. Okay, so that looks good. Save. Let's make sure we're updating, constantly committing to the cloud or whatever it does to the cloud. Not quite sure. It's something magical with fairies and gremlins, I would imagine. All right, so we got our speaker, 4 to 8 ohm. We've got our 555 organator here. One thing here, yeah, so this kind of helps. So see this speaker right here? You might want to know what's plus and minus, even though there's only one speaker, so it doesn't really matter. But let's assume we had some magical speaker that actually needs plus and minus correctly, like it assumes that current's flowing in a certain direction or how it's powered, who knows. Let's put plus and minus here, all right? So let's go here to the audio amp, and we'll copy that, and we'll take this text right here, and all I'm going to do is I'm just going to say plus. So there's my plus. So this is kind of the plus symbol, and then I'm going to select that. I'm going to copy that, and I'm going to paste that, and I'm going to make this one the minus because it is the minus. All right, there we go. And let's center those because they're ugly. Okay, there. Okay, so that's about it. All right, so now we'll stop the video here and we'll come back. And so now what we're going to do is we're going to add the ground planes, the ground fill planes for the top and bottom, copper, and then we're going to fire up the auto router again and let it route this thing. Again, we're not going to worry too much about setting up the auto router with all the different classes we could have for power rails and all that. We'll just go back manually. There's not much here. We'll go back manually and fix, thicken up any rails we want, okay? All right, so let's stop here and I'll meet you in the next video. Bye. All right, welcome back. We are on the final lecture. Maybe we'll do one. Maybe we'll do one more. We'll see. Of the 555 timer organ, and we're going to do the layout right now. We may finish with this video. If not, we'll have to do another one. Now, of course, I may split this video up into pieces, but anyway, we'll see what happens. All right. So where we left off, we had everything positioned. All right. And we like where everything is. The design is good to go. We had that little problem with the capacitor was the wrong way, if you recall, so we swapped that around. No big deal. All right. We placed all the keys here. We placed the buttons and we placed the resistors for each one of the keys, which of course are these momentary switches. And then we kind of looked around and made sure that routing would be easy. If we zoom in enough here, we can see this net R7 is right there, and then on the bottom of each one of these is this net C21, and that's consistent. So we just kind of came up with a convention for routing to make things easier. All right. Now, again, we're going to use the auto router because routing this would take a long time, and I would have to do a time lapse, and it may take many hours. Something like this probably wouldn't take maybe but 4 to 8 hours, something like that, maybe shorter. But I would only be able to make a few comments in the time lapse. So anyway, the way to do this is at first, if the board is simple enough, try routing it yourself if you like. If not, try the auto router. But the hybrid approach that we're using, where we use the auto router and then kind of go back and fix it, clean it up, is kind of the way that you should start, so you can get things done. Otherwise, you could just spend forever routing things. And again, like I say, look at other examples, look at PCBs, good PCBs, look at it, look at the routing, actually visually look at the boards. And then there's, countless examples online on YouTube. But you can always tell a really good designer from a bad designer if someone is designing something very simple and you see them using point-to-point traces like that, that's obviously very bad and amateur. So you want to look for someone that's like designing something with a 1,000-pin BGA and a big processor and a big FPGA, and listen to him or her discuss what they're doing and show how they're doing things. So you can never get too many tips and tricks about routing. It's an art form and it takes a long time to get really good at. All right, so again, this tool is fairly complicated. There's a lot of little places that we have to set things up. So just to refresh your memory now, right now we have the nets off, so we can't see the rat's nest. Remember, it's called the rat's nest. So we can turn the rat's nest on if we can find that, and I believe it's here at home under routing connections. If we say show all, and then we can see the rat's nest here. And in this view, it's kind of disconcerting because of the grid, which you can probably turn that grid off, I'm sure, but I'm not going to try and figure it out. But we can see the rat's nest here. And with this and with the design itself, for example, this regulator, we can see that, we've got this capacitor here, we've got these two capacitors here, we've got this LED. So, we can route these things, all right? So what we can do is, let's, for fun, let's not mess around with all this. All right, but why don't we see what we can do with the LDO? All right, so let's just kind of manually route that a little bit and see how that goes and see how long that takes in real time. All right, so I'm not going to speed it up, I don't think. I want to just do this as we sit here. All right, so let's kind of zoom in here. All right, okay, and one thing is we're going to go route here and we're going to say interactive routing. Okay, and then we want to set our the size of our traces, right, to a thick size. But first, we're just going to route with the default size here, and then we'll thicken them up later. But first, we just want to kind of route things. All right, so here we go. So if I click here, all right, now we're on the wrong layer. Let's make sure we get on the top layer here. And remember, we can go down here and click, or we can press the plus and minus key here to get on different layers. So you can see right here, this is the current layer here. All right, so let's get back here, and we will start the routing again. All right, so we're going to go C4 here. All right, that's good. And okay, so now one thing is, let me show you something. So this is ground. We don't want to route any ground. And we forgot to do something, right? What did we forget to do? We forgot to do the ground fill, right? So we got to ground fill the top and the bottom before we go ahead and route the board, because we don't want to be routing grounds, all right? So let's go ahead and do that. So we'll save that. And remember, where we do that, we go to polygon pour, all right? We click that. All right, so we're going to start off with the top layer. So we're going to call it top layer, and it's not no net, it's ground. And you can put any name here you want. Remember that. Net options, connect net to what? Ground. All right, and then there's some options in here for the kind of fill. All right, so and then how big of islands before things get removed, things like that. The kind of ground connections, solid, hatched, none, and so forth. All right, so you can control all these things. We're just going to leave them how they are. All right, and the second we hit OK here, we should. All right, so now we're good to go. It's all ready. So you see this little X here, and we're just going to grab the vertices here, and we can zoom out and we can zoom in. Just be careful not to lose the polygon. Get kind of messed up, and I find that this is the weirdest kind of selection vector polygon select. I get what it's trying to do, I just don't like it. All right, it's just very odd. All right, let's move over here, zoom out, and you see that there's like this delay when I'm grabbing things. It's not sure if you've grabbed it or who knows. All right, zoom in here. Make sure we get these things correctly. Zoom out. I'm trying to be very careful. If it acts, see right there, it's like doing something. So I don't want it to do that. All right, now see it's stuck. So I'm not actually doing anything and it's stuck. So if I press escape, I'm going to lose this whole polygon. Let me see. So it closed the polygon. So actually all right, so we're okay that time, but that's a bug. That's clearly a bug. I couldn't move. The mouse was grabbing the entire object even though I didn't have down the right mouse button. And it's these kind of things that are really annoying, you know? All right, so let's go to Polygon Pour again and double click it up top here. Now we want to do bottom layer. So we're going to say bottom layer and not no net. It's ground we're going to call it. And we're going to say ground here. Same thing. Click OK. All right, and now, again, we got to select this. We'll zoom in, and you can see the ground protrusions right there, because remember we grounded this, and the pin even says ground. So, all right, so that's good. That's good news. And a lot of things in this tool that have to do with selection are wonky, and so you just got to bear with them. Don't get frustrated and angry. Don't throw your computer, even though I know you want to. And you know, right now it's doing something weird too. See, it's trying to track over that corner thinking that's where I want to end things. That's not where I want to end things. I want to end things down here. All right, let me see if I zoom out, if I can. Yeah, so now, yeah, so that, all right, let's try this. So I'm not sure what's going on there. That's clearly a bug. Let's try it again. Bottom layer, bottom layer, bottom layer, ground. Bottom layer ground, and of course these bugs have to show up right as I'm doing this. So let's see, if we do that, all right, do that. And me personally, I like to be zoomed in so I can see what I'm doing, but as we zoom in, this thing is having problems all of a sudden. All right, so there we go, and then last one, and then right click, okay. So now we've got that ground fill there. So both are grounded. Let's zoom in and see if things are grounded. So on our IC, we see a ground here, and we see the four grounds around it. We change layers with the plus and minus. We see the four grounds around it. So that looks good. Let's go over to the power stuff. That's the most important. So here's V minus. We can see it's grounded. See the four protrusions, and it's grounded on the other plane also. So that's good. Let's zoom back. Now that we can see what's grounded, we have a little better idea of what's going on here. And we can now route things. Okay, so this comes from battery switch right here. Battery VBAT switch, all right, and then the battery itself gets powered here, VBAT, all right. So let's start on the top layer, and let's just see how far we can get on the top layer. So we'll go into route mode, all right, and we're just going to start routing here. So this goes here into both of these positions here. So I could bring this up above, or I could bring it below, doesn't really matter. So for now, I will, and then it's got to go down here, so let's do it below. So zoom out, and these are the kind of things you got to kind of see where things are going. All right, go like that, go like this, and let that hit center there. Okay, repour. Okay, so we've got our trace there, so that looks good. All right, and now that was VBAT switch, right? So now we're going to take this right here and we're going to do it again. We're going to put this route in here, all right? And I'm going to just do it just like that. Okay, repour now. Okay, so that's what that's going to look like. And now that I see that I've done this, what I'm going to do here is I'm going to pull this, if it'll let me. And again, this is why you got to sit here and grab this. All right, so you see what's happened here. It pulled down like that. That's okay. We'll fix it. We'll grab it right here, and we'll drag this down, make contact. There. And that's a little bit cleaner. Now, the overlay might be bothering you. It's bothering me a little bit, so a lot of times I'll turn that off and go to single layer mode. So let's, now, in this tool, I'm sure there's a way where you can just enable specific layers, but it looks like it's either all or none. So Shift-S, and we'll leave it in the top layer here. All right, so now that we're in this top layer mode, we can route. All right, so let's go here. Now let's see what else we have here. Route, and let's get a little bit more so we can see. Okay, so here's V sub CC. That goes right there. We know that. That's an easy one. Repour, that's one of our capacitors. Here's another one of our capacitors. So we'll go here. And you need to, as you're routing, you know, drag the route out and then you double click to terminate it. Otherwise, it'll keep going. All right, we got that ground there. We got that ground. So everything's lots of grounds. So that's easy. Now, let's see here. Okay, so now I see. Let's see. Let's turn that. All right, so we've got a mistake right here. So see this test point v sub cc? It's connected to ground, and I'm not sure why it should be connected not to ground. So let's see. Oh, look at that mistake right there. So everyone let me get this far without even seeing that. So what we're going to do here is going to do this. We're going to delete this, and this should just be right here. And let's press W for wire. All right. Let's save that. And I think that's why we were having some trouble with the other design. Okay, so now that we've got that, now what we're going to do is we're going to compile that. We're going to compile that change. All right, good. And then what we're going to do is we're going to go over here to project. And you know, and this is good. I did these designs beforehand, right? But report now. But the problem is they were almost perfect, right? And so I didn't really notice any of these things. So I'm glad we found a couple mistakes so that we have something to fix, right? It's nice to have something to fix. Okay, so now that's better. So you can see this one's ground and this one's not. And again, we would have never noticed that if we weren't, you know, paying attention here. Okay, so now what else do we have here? We've got the LED a little bit. Let's hook this up a little bit. We can hook this up, so we can hook up this, and this is probably going to go down here. So again, now you might ask, well, should I go like this? Should I go like this? There's really, at this stage in the game, there's not enough information. So, you know, you could just go point to point and route it like this, right? The question is when things need to start going around things, you need to start creating room. So at this point, it really doesn't matter. And then if you press spacebar, it kind of picks these different routing scenario, which way it goes. So for now, we'll just leave it like that. Okay. All right, and that's already got a ground there. Now, this right here goes to V sub CC. So that goes there, but that's a test point, so I don't really want to mess with that. Now, all right, so now here is, so this is, this LED is being fed off of the main power, and this is the main power. So this main power has got to get routed out here from one of these points to the entire system. All right, so for now, what I can do is, I can swing this around, go around this. All right, I can do that. I can go around it this way. So if I go around it this way, so if I were to go around it that way, what happens is I block everything with that trace. But if I go under it, right, I don't block everything. So all I want is I just want the power line here. All right, so what I'm going to do is I'm just going to go under these things, okay? So I'm going to go something like this, all right? No big deal. And I'm just going to put this thing up here. This is V sub CC. Okay. All right. And there we go. And so now we've got that that powered up, so that's fine. And now the last thing we have to deal with is this VBAT. That's it. So the entire regulator is hooked up. So the entire regulator is hooked up. The output, the power out, of course, is V sub CC, which any of these nodes would do. So we're going to fatten this up in a second here, but any of these nodes would do, right? So you could take it right here at this node right here and let that be V sub CC, or you could take it in the center here on the capacitor, or you could take it here. Now there's some little bit of differences depending on where you grab it, the path back to the regulator, right, and noise. So if you were to take power from here and then have the capacitors out here, right, or if you were to take the power out from here. So we're gonna let the router do that and see what it does. But there are a little bit of differences in this design. In this, it's not going to make a difference. But be aware where you snatch the power from. Right, makes a bit of a difference if you've got the output and these capacitors, these devices. You know, either inductors or capacitors. These are reactive devices. Okay, can have a little bit of a effect. Okay, so the last thing here is VBAT. So let's back out of this. So all we need to do is route this VBAT. So what I'm going to do is I'm just going to get this trace going, all right? And I'm just going to kind of put it through the middle here, All right, put it through the middle here, and then you can see I can't get to it because I would cross this right here. But I could go around it, all right? And if I go around it though, then I have to cross right here. So I'm kind of stuck. So the thing is, I kind of need to go, you know, I can go around it this way, okay, and do that, or we can go on to the other layer. So again, these are all these just kind of decisions you can decide to make and do. It just depends how you want to do this. All right, so we can go inside of this thing. That doesn't hurt us, so we can do that. All right, and then we can go like this, and we can zoom in here, go like this, go like this, go like this, go like this, and go like this, and go like this. All right, report now. Okay, and then let's get out of this mode here. Let's drag this down a little bit. So you see, that's that's the process. And as you do this, you might say, "Oh, that's ugly. I don't really like that." And you can see why this stuff takes hours upon hours upon hours, right? Because you got to sit here and do this and get a feel for it. And again, it's real hard to see what's going on now when we back out. We look at this and we say to ourselves, how is this? Could it be done, a million different ways? Could it be done better? Yeah, sure, of course it can. Everything can always be done better. Like this right here, maybe I can just put this right there, give myself a little bit more room. I can probably bring this up. I don't need to have it that low. And maybe this, I can bring this up just a hair. Okay. All right. And so now we've kind of got this this routed here. So now what we can do, let's save that. Let that do its thing. Let it do its saving thing. And then I'm going to commit this. All right, and I'm looking at the time here, and I may have had to break this up into 2 videos already, another video, but I've already been spending about 20 minutes doing this little piece for you. And you can see it's a slow process. What happens is, as you get more and more routing done, then you become more and more constrained, and then you start to see patterns. You start to see, I've got to route these like this, I got to do this like that, and you can the constraints kind of help you as well. All right, so now that we have that done, now again, we can set up net classes for power, and then we can let the auto router do it and route them thicker, but just for now, we're just going to thicken these all up manually. All right, so what we're going to do right here is I'm just going to grab this, and then we're going to use Shift and continue to get pieces of it, just like this. And forgive me, I'm sure there's a clever way to do this, so we don't have to sit here. I bet we could probably select all of it and just select tracks. I bet we could do that and get all of this at once. There's always a bunch of different ways to do things, and but since we're doing this simple example, we'll just do it the old-fashioned way, and just select them all. There's not that many. If I had a lot more, I would probably say, hey, let me see, is there something else I can do here? All right, and then these guys here, Shift, Shift. All right, so do I have all of it selected? So that's my whole power system right there. All right, so now we see the width here is 10 width, so object kind is track. So let's go ahead and let's make that 20, see what that looks like. All right, we'll do a repour. All right, and we could even make that thicker if we wanted. We could say make it 30, why not? Sure, make it 30. Okay, repour now. Okay. Now, one thing you don't want to do, and that's violated one of our constraints, but I don't care. That's one of our design rules, but we don't care. That's okay. One thing you don't want to do is make these traces bigger than these pads. So none of these traces are bigger than these pads, and so be careful of that, all right? And here we've got a little kind of a little bottleneck right there. So what we can do is we could move these 2 guys here, or we could just move this thing up a little bit. So why don't we grab this, and I'll just move this just a little bit. Repour, there we go. And then, if you want, we can do this too. Repour, and then we can also grab this guy, and if I'm lucky, the tool will let me do it. And There we go. And then it's not doing a repour, which it should. And let me see, if I right click on this, there's probably a way to force a repour, but what we can do is if we just grab this, just grab something and then there we go. It'll do a repour. Okay, so that's it. So that's our power. We did it at 30 mils thick. All right, just always want those power rails really thick. And now we're going to let the system do the rest of the routing. So let's turn on the other layers here. So now we can see it. Everything looks good. So now we're going to use the auto router. All right, so let's get back into how we do this. Okay, so we go to Tools, right, and we see auto route right here. And that's gonna, if we go here and we say setup, all right, then we've got routing width, routing via styles, all this different stuff. So let's start with routing width here, all right, and then we've got the different kinds of strategies. Default two layer with edge connection. You can read about these things and all that, but what we care about here is these two things primarily: rule width and rule routing vias. Okay, so let's click on that. Okay, and then here it is right here. So it's saying we want to make it 10. 10 is the thickness of the traces. All right, so what we're going to do is we're going to say the minimum is 10. We're going to say the preferred, I just want to make it a little bit thicker. All right, and then we'll say the maximum is 12. All right, just make it a little bit fatter. Top and bottom, same thing. All right, and we'll say okay, and now we'll go to routing via style. Now this is horrid. So let's see here. Let's go to routing via style. And now the default was like, I think it was 50 was the via diameter and the via hole was 28 mils. So I changed it to 20 and 10. We talked about this already. So depending on your manufacturer, they'll have a minimum hole size. They'll let you go down to like, 5 mils or 8 mils. And then there's the annular ring, which is this thickness here and this thickness here. So in this case, the whole thing is 20, which means the annular ring is 5 mils here, 5 mils here. That gives us 10 mils. The hole is 10, which gives us a total of 20. All right, so that's a good small via, and that's more than enough to route everything here. We shouldn't have any trouble. So we'll click OK, and we can mess with all these different things, but we don't need to. We don't need to. All right, so we hit OK, and we go back to auto route, and we'll say all. And as a matter of fact, let me back this up. So there we go. All right, and we'll go auto route, and we'll say all. All right, and we'll say route all, and lock all pre-routes. So we've already routed these things, so we should hit this right here because I don't want to rip any of these up. We just want to leave those, and it has to work around it. I believe that's the correct checkbox to do that. Okay, ready? Here we go. All right, 100% done in 3 seconds. Well, that's no fun. That's just too good, huh? Too fast, huh? All right, repour now. We manually do that. All right, so now let's take a look and see, and and we can undo this. We can redo it if we wish. All right. So that's interesting. The way it did this, it didn't tee it. It just went right through it. So what I might do is, which these things do not like to be moved. These test points. Let me see here. Hold on a second. Let me see. Can I grab this stupid thing and drag it down? Yeah, I can. Repour now. So let me see. If I put it right here, repour now, and then let me see. Can I grab this? Can I grab this? Can I grab this also? And can I grab the whole thing? So you see what I don't like here, right? Obviously, I don't like. Okay, so let's hope that there's no errors there. So we'll run the error check in a second. Right now, I just want to look at this. Okay, so we can see that the routing here did its thing over here, and it's okay. It's not as clean as I would like it. Let's get rid of the text. Shift S. All right, so now that we can see what's going on here, just immediately your brain should focus in on anything that's, look at this board. It's like there's nothing here and it's bunched up all these traces, right? And now let's go to the other layer. This is not bad. I see some nonlinearity there, so that bugs me. All right, so let's start with the blue layer. It's a little bit easier. So the blue layer over here, this looks all good, all right? Then if we look at this line right here, okay, I'm happy with that. That looks good. But this is just messy. All right, this is just messy. So I don't know what is going on here. And let me see if we can straighten these things out. I'm not sure if we'll be able to easily. So repour. All right. So in this case, when you have these kinds of things going on, just delete it. And let's go back to route here, and then I'm just going to route right on this layer. Okay. All right, good. Let's turn this one, and good. Straighten that out a little bit. Just come on. Don't be just totally gross. Let's pull this up. All right. And that was our fault because I didn't align these resistors perfectly. So the router but this is uncalled for. All right, I don't know what this thing is thinking here. It made a curve basically. All right, and that's why you got to look at it. You got to look at what the router does, and then you got to manually reroute a few of these things. Okay, so that's not bad. And I see some weirdness. No weirdness there. What else? Let's go look up here. What don't you like up here? So let's look up here. All right, this V-subs, I don't know what's going on here. This is bizarre. So let's grab this little piece right here. Let me see if I can pull it out. I don't know what's going on there. Let's put it right there. All right, same thing here. This is uncalled for. Let's fix that. And then we're not hitting the pad straight on, but you know what? I'd rather have the straight trace than hit the pad straight on. All right, in that case, because it just looks too ugly. That's nice. That's good. We haven't looked at the widths in V sub CC, but for now we'll be okay. Okay, this right here, you're crowding my V sub CC, right? Let's just move this down like that. Okay, looks good. All right, let's back out. Anything else look funky? What's over here? What's going on here? Oh, it's another one of these crazy curve things, right? Don't know what you're doing there. Let me see. I might be able to drag this over here. Yeah. Okay. Looks good. Let's control save that. And let me go and do a quick commit. Okay. So the blue layer now looks pretty good, the back layer. So I'm happy with that. That's good enough. Now let's deal with the top layer. All right, which is definitely more ugly. All right. So first thing, bunching up over here, bunching up over here. Maybe can work with that. This is definitely ugly. I don't like this. I don't like this. All right, a lot of things I don't like here. All right, so let's just get to them. Let's pull this over here. Okay, let's take this down. Let's do that. Okay, we've got all this space. Okay, this right here. So this is, I don't like straight lines like this. So, what happens when you do the straight line? You have to maintain this angle. So what I like to do is I like to come down, go like that, and then go like that. So it just gives me just more flexibility. So I'm going to go like this, and then I definitely don't like this, right? Whatever this thing was trying to do here, all right? So what we're going to do is I'm going to go above, if I can grab it, and it's not cooperating with me. There we go. Go like that. All right, and we're just going to have to mess with this a little bit here until we can drag this. I could just kill it, and I may have to in a second, but we'll see if I can pull all this in here. There we go. Good. Okay. So there we go. So now that's a little bit nicer. Now let me grab this here. Let me do this. See that? Just cleaner. Just cleaner. Now, it gives us a little bit more room to think here. Okay. Okay. Now we'll zoom out. All right, so this is our V sub CC line, right, coming from here. So let's go ahead. We know we need to fatten this up. So let's fatten this up, shift. And now it decided to get it all the way from here. All right, fine, whatever. Do whatever you want to do. Okay, it's going to be fine in this design. Of course, that's the whole point of manually routing. If we manually route the entire thing, we can do it ourselves with our rules and everything that we like to do. But and we just lost all that selection, because the stupid other plane got selected. All right, so that happens. Let's go over here. And again, time-consuming process. And there's always ways to speed it up. Yep. And you can figure them out. All right, we come over here. So this is 12 mil. So let's bump this up to. Let's see what happens if we bump it up to 30 mil. All right, bump it up to 30 mil. And what I'm going to do is I'm going to zoom out, and I'm going to see if that's okay, because we're trying to get v sub cc over here, right? Over here, this is where it starts feeding everything. So we might as well make it thick if it'll fit. Hey, why not? Okay, so that's working. Now let's go to this layer. All right, this is v sub cc here, right? So hey, let's make that 30 mil. Why not? All right, repour now. Okay, that looks good. And then let's go back. Click here, invalid expression. Have no idea what you're talking about. Let's back out. Back out. Okay. And we're just getting those complaints. So you can see this is v sub cc here, right? That's v sub cc right there. So we'll mess with that in 1 second. But first, I want to bring your attention to this madness. So we could pull this out like this. Let's do that for a second. All right, we'll go like this. Okay. And then this one right here, we'll pull this out like this. All right, but what's going on down here? Why are these all bunched up in the first place? All right, so, and then we can take this one and go like that. Okay, that's looking a little bit better. And now what we could do is we could drag this right next to this. So we could do this. Let me go like this a little bit, like that. All right, and then what I want to do is I'm going to bring it like this. Okay, now what I'm going to do is I'm going to go like this. So, I want them sort of close, but I don't want them, this close, where they're on top of each other. All right, and we'll bring this one away a little bit. Okay, now, say that looks much nicer, except I don't like this 90-degree turn right here, so what I'm going to do is I'm going to go to route, and I'm just going to go bing, bing, close it off, and it'll do it automatically for me. And please don't crash. I'm not sure what it's doing right now, but it's probably has something to do with the cloud. All right, and I don't want to send a report. All right, it looks like it survived. I'm not going to believe that completely, but let me bring this back here. Yeah, report now. This is happening right now. So it looks like the software has become destabilized. All right, so what I'm going to do is I'm going to go ahead and I'm going to crush this and then reboot it, restart it, so that you guys don't have to deal with this. But anyway, this does happen, and this is the first time I think we've even seen this happen. And so that's why you want to save your software, save your design constantly with Control S and commit it every now and then. All right. So let me, I'll be right back in a second, and I'll just refresh this. Okay, so I rebooted the software. I'm probably going to have to reboot the whole computer. I think it's just starting to destabilize. Anyway, so we fixed that little problem right there. And so now we have this right here. So again, this is a little bit close. No need to put it on top of it like that. So let's do that. And most of the time we're just looking to create space. Just make things. You don't need to make things so tight. All right. This right here, this is fine. It's in the middle. All right. So each one of these is in the middle. Now you might be tempted to put it up here. You could, but you can just leave it in the middle. That's fine. All right. So let's zoom out. See if there's anything else we don't like. So this looks all good. This is not bad, not bad, not bad. Oh, right here. That should just stick out at you and just be like, what, why, oh, that we don't want that. Again, you got to be careful where you grab these things. There we go. All right, and then again, no need to have this thing sticking out this far. So we just go like that. Okay, and now I don't like that, so let's bring it out a little more. There we go. Okay. All right, so that's fine. Looks good. Looks good. And again, you got to do this. You got to kind of zoom in and zoom out to kind of see things, kind of get a bird's eye view, then kind of zoom in, all right, until you kind of feel comfortable. All right, there's a little problem up there. I don't like that. Again, I don't like this point-to-point stuff. So what I'd prefer is this gives me more room. Now I can work. Now I can snake something else through here, right? Now this right here, so this trace is all on top of here. So first I've got this double thing here. So let's do this and let's see if we can get this to line up. All right, it's not going to cooperate with me. So what we can do is we can delete this whole thing here. We can delete that, and we can try and drag this. Let's get rid of that. And now what I'm going to do is I'm going to literally drag this up here, and I am happy with that. I'm going to go over here. All right, we'll get it to repour in a second. All right, now this whole thing right here, don't like it. So let's see if we can grab this whole thing and pull it out here. All right, so that went. Now let's pull this one out. I think if we pull this one out and up, yep, that'll give us what we want there. And then this right here, we don't need this to come in at this angle. All right, now there's two pieces here. So let's leave that there. How about this? Can we grab this? All right, and maybe we can do that. And let's see, put this, can we do this with it? Will it let us do it? There we go. All right, and then this is V sub CC here, right? So this is our V sub CC line. We know we're going to fatten that up in a second. So let's back out. So there's that V sub CC that we were talking about. So now let's see what this situation is here, this craziness. So let's fix that. All right, now, again, this straight line, the system created this straight line right here. All right, and let's put our, all right, so this is like a pull-up resistor here. So we don't really care that this V sub CC from here to here is thick, but we want this one to be thick because this is what's feeding the rest here. It's actually a feeder. Now, again, I don't like these point-to-points because now I can't route anything through here. So what I'd rather do is come out, go down, and go like that, right? Now, typically when you're routing power, you know, you use a different kind of strategy. The power kind of looks like a tree. You kind of bring it up, you bring it across, you bring it down, or you put it on a plane. You don't really route it like you would a signal. The auto router kind of did that. It routed it like a signal. That's why it's looking like a signal trace. So no big deal. But let's go ahead and let's pull this. Okay, so that pulled all the way. Don't want to do that. Repour now. Let's undo. Okay, so what I want to do here is let's get to route, and we're just going to kind of manually do a little bit of work here. So let's go like this, and let's go like that. Okay, now that we've done that, now we should be able to grab this. There we go. That's what I want. And you can see what I've done with this right here. I've just kind of done that. Now I've got some room. You know, I could, if I wanted to, route something through here, through here, through here. I don't have this straight line taking up all the space. So that's what you want. All right, now let's back out here. Okay, so now we're okay, and let's fix this little guy right here. We got this kind of half straight line. Again, one of these things right here. You know, we could fix that. I'm going to leave that one this time. All right, so now what I'm going to do is I'm going to back away, and we are going to let's see what that component is. That's our capacitor, so we want a fat line right there. And again, you're always looking at what these things are too. So okay, so here we go. So we're going to shift, select all these. Oops, oh, sorry. Shift, shift, shift. Lots of keys, lots of keyboard controls, lots of dexterity, lots of places to get frustrated. But you know what? Don't get frustrated. Just take your time. You make mistakes, just be slow at it. Don't drink coffee. I guarantee you'll make a lot of mistakes. I don't drink any caffeine at all as a rule. Definitely not when I do this. Okay, and then we got this one coming through here, and let's turn this on. And what is this? This is, oh, this is the speaker, right? So we definitely want this one fat also. So I think if I switch layers, I can shift and I can select this line without deselecting all those. Okay, so that's good. Good to know, good to know. All right, so let me zoom out here and let me go back. All right, so now we've got all that V sub CC selected. So now let's go here and let's try 30 mil. Why not? All right, 30 mil, see what happens. And we'll say repour now. And as long as it doesn't get on top of another trace, I don't care. All right, so let's see here. So this looks good here. This is just going to this resistor, so I don't really care about that one. But you know what? I'm gonna select that, and I'm gonna make that 30 mil too. All right, why not? Okay. All right, and let's grab this. Okay, so this is okay. Did we create any issues in here? Nope, that's still okay. We got flood fill around that. We didn't do any problems, create any problems. All right, there's our capacitor. All right, so now what I'm gonna do is click out there. So that looks good. All right, and I'm happy with that. Let's get rid of this text layer. Okay, so there we go. Okay, so that looks good now. So now if we look here from the bird's eye view, this looks more or less very clean. I'm happy about this, nothing weird. We go in here, we zoom around. This all looks good. We got all our grounds. We got this guy. I'm not happy that this doesn't hit this perfectly. So what we could do here is we could drag this down. Okay, we could drag that down. Now this is let's see, can I drag this? Nope, still can't drag that. Don't know what I'm doing wrong. I'll grab it like this. Can I drag it like this now? Yeah. All right. And let me move this up here. So this tool is, it's not cooperating exactly the way I want it to, so I'm going to have to drop another trace. I'm going to go like this. I'm going to go like this. And not super happy about that. There we go. All right. Now I can grab this thing and center it with this. I got to be stupid and do it like this. All right. There we go. Okay, shut up. There we go. All right. Good, good, good. Okay, so looking at this, this looks good. This looks good. All right, happy with all that. Okay, we got all these grounds, our 4 grounds at our 4 holes. That looks good. That looks good. We go to our other layer. Okay, take another look at that. Those reds are just showing that we violated our design rules, our thickness, trace width, thickness. All right, so these traces all look good. So I'm happy with all this. All right, so let's get this back on this top layer. All right, so I'm happy with it all. Let's Control S and let's go and commit this thing. Where is commit? We right click, we'll say commit. Cross our fingers it doesn't crash again because I haven't rebooted the computer. I'm going to definitely reboot when we're done here. Now, so now this is done. So now let's go ahead and let's do a design rule check. So we'll go to design rule check. We'll say reset error markers, right? And we will say design rule check. And click it. All right. We'll do all these things. Let it do everything. Who cares? And create a report. Looks good. And we'll say run design rule check. Yes, let's rebuild. Okay. So total error 0. That's really all I care about. Total warning 0. Rule violation 75. All right, I'm a big violator. Power plane connect rule relief expansion 20 mil. Yep, this is okay. Again, this is just a setting, and since we made those traces so big, you know, excuse me, this width constraint, since we made those traces so big, the 30s, it said 10, 12, 12, but we made those 30s manually, so that's what happened there. All right, and let's see. This one, hole size constraint, same thing. We changed it. Solder mask, don't care if things are touching, don't care if things are touching, don't care if things are touching. Unpoured polygon, there must be an area. I'm not sure what that is. Let's go ahead now. Let's close this. All right, let's reset error markers again, and let's do it again. All right. And why am I not seeing it? Do it again. Run design rule check. Okay. Okay, same thing. All right, so that's good. So now I am happy, and let's save this. Give it a second, give it a second, give it a second. Save project. Give it a second, give it a second. Commit. Commit. So we don't now we could put a hole here, right, for the speaker, right? So we could do that, but right now we think we're done. So the only thing we're not totally sure of is like V sub CC. right? I want to make sure everywhere there's V sub CC, we've got these fat traces. So here's V sub CC, it goes here. Then where does it go? It goes here to this resistor here. Don't care too much. And then the amplifier, I really do care about. It goes here and goes here in the amplifier. And then let's see here. Okay, now this is a power path. So this is an amplifier, right? So this amplifier's got a lot of current. So now look here. So here's where power comes in, and then it goes through the speaker, which is a coil, ton of current, and then it's going through our transistor. Now, the base of the transistor, this should be the base of the transistor. This is low current, but the collector circuit is high current. So see this trace right here? This is like a V sub CC trace. We need, and I did whatever it is I did. I selected the plane, and now I'm in this mode, and I'm not sure what happens there. Okay, so that makes me mad. I'm not sure what I did. So I'm still going to select this, right? And then we're going to make this 30 mil. Okay, and nope, I didn't want to do that. Read-pour now. As a matter of fact, this sets, and these the resistors set the bias, but I did not want to do that. All right, I'm not. Okay, so now let's try it again. All right, let's try it again. So net D. So it's grabbing this whole net because I'm selecting it. So let me try this. Let me try this. Let me try this. Yeah, it's not cooperating. It's grabbing the whole thing, but that's okay. You know what? I'll make the whole thing 30. It's not going to hurt. All right. Okay, so we make the whole thing 30, and now we've got this one under here. So let me go to the top layer, and we're going to go to single layer mode, and let's see if we can get it. There we go. Go to single layer mode. Now grab it right there. Now we'll do it. And you know, this is what you got to do. You just got to, you know, sometimes you got to fight the tool and get it to cooperate with you. All right. All right, and again, I'm not sure why it's doing this, the dimming version of itself. All right, I'm not sure what's going on right there, but we'll see if we can reset it in a second. Okay, so let's continue here. So here's the base. That's the base circuit. So we really don't care about the base circuit because there's very little current. All right, and then let's turn on. So here's this. Here's our diode here. So oh, actually, we do want that. That's high current. And then the thing that sets the bias here is this R3, R2. We don't care about that. And then the current goes down and flows through the transistor to ground. So now the transistor circuit is all, it all has large traces, which you want. So that's also something that we want. We want that transistor to have all high current carrying traces. Now, the traces that are running to each one of these switches and all that, those are low current. Those are just being switched in the switching circuit of the timer circuit. So that doesn't matter. Okay? All right, so let's save that. Give that a second to do whatever it is that it does. We'll say commit. Say OK. All right. And again, something, I don't know what's going on and why it does this, but let's just go here. Let's say reset error markers. Let's do a design rule check. Let's say run all design rules. Yep, we're going to do that. And rule violation, we got one more rule violation, which is just a because we made those fat traces. All right, so now let's save that one more time. Let's commit it one more time. All right, and I don't like that it got funky. So let's try this. Let's try and close. Can we close the project? Close the project. Close the project. Good. Now let's reopen the design. And again, don't do what I'm doing and try and fight the tool. If it's getting weird, definitely close the tool, restart it. If it's still getting weird, turn the computer off and turn it on. Now, in all honesty, this is a Windows 7 computer, and Windows 7 and Windows 10 is very, very, very stable. This I literally reboot this computer every 6 months if I have to, whereas in Windows XP or Windows 98 or something, you know, you're rebooting constantly. But Windows 7, I never reboot it. Windows 10, I never reboot it. It just works. All right. All right, so there's our board. All right, so it looks good. So now let's go into 3D mode. All right, and now it's going to take it a moment to populate and bring in all the 3D models. So while it's doing that, I will kind of do this a little bit. So there we go. And I mean, that looks to me like we have a complete design. And let's look at the bottom here. Make an attempt to look at the bottom. Sometimes this little 3D handle here is just a little bit not the way I'd like it to be. There we go. And there we go. So that looks good. That looks good. And woo, try and get this the way I want it. There we go. And bring it down here. And zoom out, zoom out, zoom out. Okay. There we go. And zoom in. Okay. So again, everything looks good. And now we can kind of see some of the mechanical issues. Are there any mechanical issues? So our battery will go in there good. We got our on-off switch. We got our LED there. That looks good. The board edge is cool. We definitely can fit a screw in there. We can fit our screw in there. We can fit our screw in there. We'll plug our little battery in there and then pop our speaker right through there. We got all our switches and everything's labeled, hopefully correctly. And that's about it. That's about it. And then, of course, there's no models for C1, C2, C3, right? Those just didn't have a model. Same with C6. They're just monolithic capacitors. All right. So that is the design for the organ. So if you manufacture this and put it together, it should, I think, work. All right. So put that back there. All right. So that's it. And so we're done with this one. So that's cool. So that's another one down. So now what's next? So now we're going to do the, what are we going to do? We're going to do the Simonduino. So an Arduino built into a Simon color matching game, or a Simon color matching game built onto an Arduino, whatever you want to call it. So we'll stop here, and then we're going to go take a look at that, and that's our last project. And we're not going to go through that in this much detail of actually putting it together and all that. We're going to look at more of the design process, because now you've seen this, and the other one is fairly complicated. So we'll see how we want to do that. But anyway, stop the video, and I will meet you in the next one, and we'll talk about the Simonduino. All right, bye. Hey there. So I'm playing a Mattel Electronics football game. I think I've shown you this before in another video. If I haven't, then here it is. So this is a small electronics game. It was designed and manufactured in 1977, originally 1977. So it's a long time ago. 40 years ago, if I'm doing my math right? 40 years ago. How crazy is that? 40 years. Now, inside of this toy is a microprocessor and a little, this screen right here is an LED screen. It's not an LCD, but an LED screen. So it's got an LED screen, it's got a microprocessor, it's got a number of buttons. It's a very well-made toy. I mean, this is an original, it's 40 years old, it still works, and it's a lot of fun. And you know, toys like this used to be very common, and they didn't have complex, you know, Android systems in them and things like that. They had very simple electronics. Many of them didn't have microcontrollers or microprocessors. They just used discrete electronics. So now in the class, we're on our final kind of lecture here. And then, of course, we're going to have bonus lectures as the class progresses over the months and hopefully years. But this is the end of the formal part of the class. So we're going to do our last project, which is a Simon game. All right. And the Simon game, let me kind of tell you where the whole idea of this kind of came from. So, you know, I love things like this. I had this when I was a little boy, right? And I used to play this, and I still have it memorized how to play it and how to win it. So this is comes from a class of games, these handheld electronic games. And if you just Google for electronic games, handheld from the 70s, 80s, you can find many pages like this. I'll of course give you this link if you want it. But here's a Speak and Spell. I'm sure you've seen one of these before. all right, unless you've been hiding under a rock. Speak and Spell, Little Professor. Here's what we were just looking at right now, the football game, a little video of it. Shows, it has these special security screws on it and shows what's on the inside of it. We've got our circuit board there, we've got our battery, we have, these are called dimple switches, and basically they're little metal switches. You press it down and it pushes down, right? And then there's usually a transparent tape over it to hold it in place. There's the LED screen. And the LED screen is very simple. It basically has an LED in every possible position. All right, and then you can control the brightness. And then the side view here, you can see the microcontroller or microprocessor. All right, and there's the Speak and Spell. We don't really care too much about that. Another little web page. Let me see if I found. Yeah, so this is kind of nice. So this one's handheldmuseum.com/Mattel/FB.htm for football. And this kind of tells a little bit of the technology behind it. So it was invented by George Close and Richard Chang, according to the patent, programmed by Mark Lesser, 1977. There's a patent, so you can go on Google Patents and look this up if you like, the display technology and so forth. So this is really the beginning of handheld games, and this is one of the more complicated games. I mean, it had scoring, it had 2 players, very, very, very cool. Now, I would like to do something like this for our final project, and we can do something like this, but the display just adds one element, I think, a little bit too much. So, with the same kind of thinking, I want to do something still fun, still interesting. All right, so what I thought of doing was a Simon game. All right, now Simon, again, unless you've been living under a rock the last 20, 30 years, you've seen one of these. They still manufacture and develop. This is Simon. It's a simple color match game. There's a microcontroller, microprocessor inside of here, and you press start, and then the game lights up one of these panels, and then you press the panel, and then it lights up 2 panels. You do the 2 panels, and so on and so forth until you can't remember anymore. So there's a Wikipedia page. You can read through the page and check it out. But couple things. So this was invented by Ralph H. Baer, and Howard J. Morrison. I actually didn't know about the Howard J. Morrison part. Ralph was a friend of mine. Actually, I've spoken to him many, many times. He just passed away a couple of years ago. And Ralph, you may or may not know, is kind of the grandfather of video games. So before Nolan Bushnell, right, created Atari and created Pong, which Nolan didn't write Pong, but before Atari, there was Ralph Baer, and there was what was called the Magnavox Brown Box and Magnavox Television, Brown Box, and Ralph invented that. And it was a non-microcontroller, microprocessor game system, discrete electronics, but it had cartridges. And from there, the kind of video game industry evolved, and then the first Atari 2600 or VHS system and so forth, and everything kind of went from there. So Ralph really started it off, right? And so I'm going to do the Simon game because it's cool, it's a fun game, it's a fairly simple game to program. We don't need much hardware, but we are going to need a microcontroller, all right? So I'm going to talk about that in a minute, but I want to show you a couple other things while I'm here. And like I said, Ralph just passed away in 2015, I think. If we look up Ralph Baer, it was 2014, 2015. Yeah, he was 92 years old. And I'll tell you, Ralph and I would talk, now and then frequently because he liked electronic gaming, and I've been making game console kind of hardware. And to the day he died, seriously, Ralph was building electronics. That is workbench showing right here in Wikipedia. He was sitting there working on microcontrollers and this and that, and and he was an analog expert. And so digital stuff he thought was, was kind of he was kind of cheating, right? So he loved analog. But to the day he died, he was playing with electronics. So that was really his passion. He was just always trying to play with stuff and have fun with it. All right. So one thing I want to show you is, and it's no secret that I'm a retro gaming enthusiast. I'm a game developer, both software and hardware, and so I like retro gaming. And so I've read every book there is on it, everything from Masters of Doom, which is an awesome book about John Carmack and John Romero and the creation of Wolfenstein and Doom and their whole journey, all the way to this book, which is Video Games in the Beginning. If you can see that right there. And this is a book that Ralph did, and it's kind of goes over, just what's interesting about it, Ralph is a consummate engineer, right? So he was never purported to be a businessman, a CEO type. So he was an engineer, and this has literally got his engineering notes in it. It's got patent filings, things like that, things that you would never see, you know, in other books. Here's a patent filing and so forth. His engineering notes are in here, and he kind of describes his thought process. This is a good book. This is you're getting into the mind of someone who started the entire video game industry, the hardware industry. This is the guy, Ralph Baer. End of story. That's him right here. So I would read this book, Video Games in the Beginning, and by Ralph Baer, and just read through it and to see what he was thinking. All right. So and you can probably order it on Amazon. My copy he sent to me. Let's see. Can you see that? I don't know if you can. Little to Andre there, signed copy. Now, another book I want you to take a look at is this one. And this is a great book. And I got this also when I was younger because I was very interested. And I was very interested in hardware game design. This is in 1978. So I maybe got this in the early 80s. I can't remember. But anyway, this one is called How to Design and Build Your Own Custom TV Games. All right, so very similar to The Black Art of Video Game Console or Design Your Own Video Game Console, which I wrote, of course, in 2005, in the early 2000s. Now this book is by David Hesserman. You can actually find this on Amazon still. There are copies floating around. But I spoke to David many years ago, and I licensed it from David and told him I just wanted to put it out there. And so we electronically scanned this in, and page by page, painstakingly, and it's actually going to come with the class, and it comes with my book, my Black Art of Video Game Console Design / Design Your Own Video Game Console book. It actually comes on the CD, DVD, which is just in the zip file. So there's a copy of this, and I want you to read this also. And so now, this is all about making games with discrete electronics, with microcontrollers, but just the thought process. Imagine it's 30 years ago, 40 years ago. You didn't have all this technology. You didn't have Google. You didn't have internet. You didn't have someone like me teaching a class. You had to figure this stuff out. And so to see how these people had to think is important because it's extremely optimal way of thinking and using very little electronics. The Apple computer, the Apple II computer, Steve Wozniak was created from this kind of thought process, minimization. And that's what game development and gaming hardware is all about. And just electronics in general, just doing more with less. Of course, I like gaming stuff. It's a challenge and it's fun. You see things on the screen. All right. So with that said, we're going to do a Simon game. All right. So again, if you've been hiding under a rock, you can take a quick look here. I'll play this for a second. And as you can see, it just basically, the game comes up with random tones and random colors, and then you copy them. And if you make a mistake, then the game stops and it screams at you. And it goes, eh. All right? And this little video, you can just go to YouTube and type in Simon videos and you can find them. Okay? So now, the game itself, let's see if we can find, yeah. So you can Google for the instructions. This will explain the instructions of the game, the full game itself. So we're going to develop some hardware so that we could potentially write the software for this game. Okay, so that's kind of the first thought. So all right, what are we going to do? All right, so this is kind of what we're thinking we want to do here. All right, next we want to model this thing after this Simon game. All right, kind of it's inspired by. There's been thousands of Simon games created, derivative works, all that, licensed and unlicensed, sold and not sold, do-it-yourself, and so forth. You can find them anywhere. Just Google for them. But the majority of them, still kind of hold close to the original design. There's 4 different colors, and each one of these colors has a button associated with it, and a light associated with it, and a tone associated with it. And there's some controls. The original Simon game has game 1, 2, or 3. It has skill level 1, 2, 3, 4, and then this button hiding here says last, and this says longest. And I believe if you press last, it'll show you what the last move was. To help you in longest, it'll play the longest sequence that you got. And then start is start, on and off is on and off. So as hardware engineers, we're not copying this right here. We don't want to do an exact copy. We want to do something close, right? And then we can program whatever software we want. So we look at these buttons and we say, okay, there's a start button, there's a couple other buttons, longest and last. Maybe we'll make those longest and last. There's an on and off button. There's a skill level. There's a game. So there's some buttons that have on and off that are momentary, 3 of them. And then there's some buttons that have multiple selections. Those would be harder because we would need a slide switch that was, many, many throw, right? 4 throw, 2 throw, or 3 throw. And then we have the on and off switch. So we're just trying to keep the basic idea here. All right, now, so given that, so we need a microcontroller. We need to be able to make sound. We need to be able to make light. We need to be able to have inputs. All right, and then the whole thing is we could just use a very small microcontroller to do this and make it kind of proprietary, or we could make it open source-ish, right? So I said, well, let's make it open source-ish, and let's use an Arduino as the basis. Now, if you don't know what Arduino is, right? Again, you can Google it and read about it and so forth. But Arduino is it's a technology platform invented, I don't know, maybe 10 years ago, something like that, came out based on an Atmel small processor, 8-bit processor, an Atmel 328. It's a little 8-bit processor. And the Arduino is not really the processor. It's not really the board. It's really how you program it and how you perceive it, which is a tool, a very simple tool written in Java originally, which hides the compiler, the C compiler, the GNU compiler under there, and basically you plug this little board in, and I probably have one here someplace, no. But anyway, you plug the board into the computer, you can write very simple code, there's libraries and all kinds of stuff, and then you can download the code and get blinking LEDs or do whatever you want very, very easily. Now, Arduino is kind of a brand, and there's maybe 100 different boards you can buy that have the original processor all the way up to very complex ARM processors, right? And Intel processors, even all kinds of stuff. All right, we're going to look at that in a second. So we'll use an Arduino compatible processor and an Arduino compatible core design so that we could use the Arduino tool to program it, so that you can kind of program this as an Arduino. So we could think of it as if we were to take an Arduino and just connect up 4 switches for the buttons, and then connect up 4 LEDs, and then connect up some sound and a couple more switches for these other buttons. You would program it like an Arduino, then through the input-output, you could control all these buttons and lights. That's kind of the idea, so that'll be cool. All right, so let's see what else here we got here. And just looking through here. Okay, now, if we're going to deal with Arduino stuff, right, then again, if you know all about Arduino, then I'm just telling you stuff you already know. So, but if you don't, Arduino, it was a company that created this product many, many years ago. And then there was some infighting a couple of years ago between a couple of the founders, from what I understand. And so one founder, wanted to do one thing, he was hardware, and the other founder was software, and they got in a big fight. So this fight lasted for about a year or two, and then finally the court said, you know what, stop it, that's it. Here's what you're going to do. You're going to merge things back into this holdings company, yada, 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 and you're going to play nice with each other. So here's a little Google search. You can read about this. It was just all kind of resolved. So now, if you go to arduino.cc, I believe, and I always get this confused, and it's an Italian company to boot, so that just makes it even worse because it's hard to figure out what's what and who's who here. So I think Arduino CC is kind of more the software side, and then I think Arduino org is more the hardware version, which is now not coming up. And because I think I had a cached version of it. Let me see. There it goes. It's not HTTPS. So I think this one is the hardware-ish one, which I'm not sure why it's not been merged back into the CC. But in any event, what we're going to do is we are going to, as a matter of fact, let's see if we can find it on the arduino.cc. So what we needed was so here's the original Arduino. It looked like this. It was called the Arduino Uno. And let me go here. And again, this class isn't about Arduinos, but I'm doing one next about it. But this is just so that we can do something with a microcontroller. All right, so Arduino Uno Rev 3. So it's a third iteration on it. And here's what it looks like. So this looks very similar to what the original Arduino looked like. So here's the deal. It basically had a USB port which had nothing to do with USB. All it really had to do with was you could, I don't even think you can power it from the USB port in the original. I'm trying to remember, maybe you could. But the USB port basically gets intercepted by a USB to serial transceiver, so it turns it into a serial stream. So it doesn't even use USB, it's not a USB device, it's just a serial device as far as the PC is concerned, use it to program it. Then it's got power, and then here's our little Atmel 328P in this version for low power, 8-bit processor, and I believe it's got what, 16K of flash and 2K of RAM, 1K of RAM, 2K of RAM, I think. Really teeny tiny little processor, fairly slow. You can put it up to about 20, 25 megahertz if you push it. But the design is very simple. And the whole idea was, hey, I just want to do something with a microcontroller. All these little headers here are some analog headers, some power headers, and then just some general stuff, digital PWMs, pulse width modulation, some general GPIO. Here's TX and RX. Okay, so this is kind of the base Arduino. So we could have kind of copied this core if we wanted to, but there's other simpler ones, and like here is the Nano. All right, so take a look here. So the Nano is even simpler. It has very little on it. So the whole point is there's some firmware that can be loaded on this processor, which is still an AT328P processor, but this one's surface mount. And then it's just got a couple little LEDs on here. It's got the USB port. On the back of it, it's actually got the USB to serial chip. All right. And the design is just simpler. It's just got less bells and whistles. So all we want to do as hardware engineers is copy kind of the basic Arduino Nano core design so that when we plug our board in to the PC and use the Arduino tool, it will think it's an Arduino Nano. That's what we want. So we're going to trick it, right? So that's kind of cool. And then we'll add all our LEDs and our lights and our buttons to all these GPIOs. So basically, we're going to design this with a bunch of LEDs and sound and all that, and integrate it all together. But you could, if you wanted to, check this out. I just found this again, just Googling. You know, you can find anything on Google. I think we all know that. And where is it? Looking, and it disappeared. Let me see, did it disappear? Here. Oh, here it is right here. I was just looking right at it. So on Arduino.cc, there's a project. So what this is, it's a Simon game implemented on an Arduino. And so if you just take an Arduino and you get all these little parts, and then you can hook it up like this, right? And so there it is. So this would be a Simon. So there's your Arduino Uno, there's your, I don't know if this is a start button or whatever, and then there's your 4 LEDs, your 4 colors, your 4 buttons. Of course, there's no sound here. There's no other switches, right? There's not the other switches and all that. But this is basically kind of what we're doing. We're saying we're going to take an Arduino, bare bones. We're going to take all this stuff. We're going to add some sound. We're going to add some other cool stuff. We're going to put it all on one board. All right? That's what we're going to do. So that's what this design is all about. Okay? So when we get all done, and I've showed you this before, when we get all done, we're going to create this Simonduino. So if you go on to my page here, I want you to fork this Simonduino color match game. All right, and we can show it right here. Of course, we have to wait for the wonderful world of the cloud interfaced circuit maker. So here it is here. And so what you're going to do is just fork it, and then you can fork it into your work copy. Now, this is complicated enough where I don't think we're going to do what we've been doing, which is create a blank final design and then piece by piece create it. Looking at how long it took us to do the other lectures, they took a long time. So I think you are at the point where I don't need to sit and go through everything again like we did before. To do all the way through the PCB design and all that. So we're just going to work with the working copy and talk about it, but we're going to talk about higher level architecture. What's the thought process I'm going through as I'm doing this? That's what we're going to do, and that's what we're going to do right now, is we're going to look at all these things, all right? So go ahead and fork it into a work copy, all right? And then let's get these two things up. So here is the final design, all right? And we're going to go over how I got this piece by piece, every little element. But I just want to take a quick look here. I always, the way that I am, the way that I learn, and the way that I think that students learn the best is if first you show them where you're going, right? Here's where we're ending up, right? Then show them piece by piece how to get there, right? And then back away and say, do you get it? But if you just start showing pieces, it's like you can't see why I'm doing this, you know? And one of the questions that used to drive me crazy, and I'm probably repeating myself here, when I was in school, whether it was math or computer science, electrical engineering, students that raise their hand, why are we learning this? Well, you're learning this because you're supposed to be learning it because you're paying to get a degree and so and so. But you know, the teachers, they can never give an answer because there's 1,000 reasons why you're learning it, to do this and this and this and this. But it would be nice if there was a project or something could say, well, you're learning this because you need to be able to do this to do that. So what I like to do is show the whole thing and then kind of, you know, where we're going, especially something this complex. All right, so let's take a quick look here. So bird's eye view. So we've got our power system here. All right, we've got our interface here. This is our interface headers, like on the Arduino, right? The pins that interface things. This is our buttons here, our button bank here. Here are our LEDs. Here's our basically our Arduino. This is the Arduino, the 328P. This is the programming interface for the Arduino. So before we can program the thing and turn it into an Arduino, we've got to somehow program the firmware into it so it can be an Arduino. So that we have to do that through a direct programming port and a programmer, which I don't have here. Then once we're done with that, then we can use the USB port and we can use the serial USB to serial bridge, which is this section right here. That's that. And then finally, we could, if we wanted to, just take a couple of the GPIOs from the Arduino chip, a couple of the GPIOs from the 328P, the Atmel chip, and we could just put those out to a speaker, or we could just put them out through a single transistor like we did in the previous design, a simple amplifier. But what I wanted to do was allow you to generate a true audio signal and then filter it and then put it through an actual audio amplifier to bang out a couple watts of power. And this just gives you something else to add. That way, if you just want to put out a simple square wave, you can do it, but you could also use PWM pulse width modulation or PDM pulse density modulation, and you could play synthesized voice, music, whatever you want. You could hook up an SD card and then get the Arduino SD library, SD to audio library, and play audio clips out. So there's so many things you can do once you have the Arduino core. But I wanted to give you a real audio amplifier just to show you one, and then also so that we could have cooler sounds. Of course, there's no software. I'm not writing the software. All right. So maybe later I'll do that. But for now, when you get this, it's just a system, because the whole idea is PCB design and schematic design, not software. This is not a class about software. Don't even want to go there yet. But maybe later I'll write it for it. But I'm sure someone will take a weekend and bang this out. Not hard, not hard. Okay, so now let's zoom in a little bit. Okay, so, and again, we're going to go through this whole thing. I just want to do a zoom in now. So here comes our battery. So we're going to use a 9-volt battery. All right, we've got a little protection diode here. I'll talk more about that. We got an on-off switch. We've got one of our LDO regulators, low dropout. So this is going to give us our 5 volts for our whole system. We've got our bypass in. We've got our bypass out, looking good. We got our 5-volt power good indicator. Okay, we got our couple little test points here so we can see our power. All right. Then here we have Arduino Nano style I/O headers. Okay, so what does this mean? If I go look at the Arduino Nano, I can see it's got these headers and they go to specific pins. So I try to maintain that compatibility so it's like an Arduino Nano. So we're going to put these on 0.1 inch headers. All right, so and they're going to look just like this, which is a copy of the Arduino Nano, more or less. Okay, all right, we're going to go over here. This is the difficulty switch. So the difficulty switch is just going to be a toggle switch that goes, right and left. So basically, it's single pole dual throw. So we can have it in 2 different positions. So in one position, it'll be kind of on, and the other it'll be off. So in one position, it'll have this pull up, and the other position, it'll have this pull down to ground. And so you get a 1 or a 0, and that'll switch, so you have 2 modes, right? Do whatever you want with them. Now, this is a little bit more interesting here, and this is something fun. So the whole idea was we have all these buttons. We got, what do we have? We've got the red, the green, the yellow, the blue, which are on the colored buttons. Then I have start, I went last, I went longest, and then 1 extra button for auxiliary. Don't know what you're going to do with it. If we were just to take all these buttons and use GPIOs, we would have to use 1, 2, 3, 4, 5, 6, 7, 8 GPIOs. All right, to encode these buttons, 8 GPIOs. But instead what we're doing is, because we only can press one of the buttons at one time, we're using this chip right here, all right, so which is a demultiplexer. So this is a 148. So instead of a 138, which goes 3 to 8, this goes 8 to 3. So whenever you press one of these buttons, you get a code out, which is 3-bit. Now, there's another way to do this. We could serialize the data. So we could take an 8-bit shift register, right? Could take an 8-bit shift register, and with that shift register, we could parallel latch these 8 bits in, all right? Then we could serial stream it to the processor. But we still need 3 pins, and here's why. We need a latch pin, we need a clock pin or a shift pin, and we need the data pin. So it's still 3. But that way becomes more efficient after 8. So if we wanted 16 or more switches, we would serialize it. But since there's 8, we're going to do it like this since it's just as simple. A little easier to understand than a serial stream. Okay, the display bank, very simple. We're just taking the outputs directly from the GPIOs and putting them through LEDs. Now, if you look at the ATmega's data sheet and you look at the current capability of the IOs, I believe it's 20 milliamperes. I could be wrong. We'll take a look at it at some point. So they should light these LEDs just fine. If not, then what are we going to have to do? We're going to have to put a FET or a transistor, but they'll be fine just with the GPIOs, all right? But if not, then we would put that transistor or FET in there so we could really jam some current in there if we wanted to, or if you want big lights, okay? Now, another thing you're seeing, these 200 ohm, these are just placeholders. You could make them 0 ohm or 10 ohm. They're just current limiters, so probably in reality when I get done, I'll make them probably 10 ohm or 33. You want to make them small, but they're just there now for safety so you don't burn out anything. Okay, manual reset. So here is the rough Arduino design, all right, Arduino Nano. So now it's not copied exactly. What's copied exactly is anything that goes to anything Arduino-ish, we want to use the same thing. For example, on the Arduino, it uses pin 30 and 31, RxD and TxD. This is the UART. This particular UART is what goes to the UART on the PC, right? The firmware that's going to get loaded in here that makes it into an Arduino thinks that these are the pins. So we got to use those same pins. So in other words, you got to copy everything to maintain compatibility. And that's another key thing. So it's like we're porting hardware. All right, but we want to still do things ourselves. All right, so we'll get to this in detail also. There's the programming port. All right, okay, let's see. Here's an amplifier. So we use this amplifier right here. So here comes our audio signal. We've got a low pass filter. Remember this, low pass filter, right? And then we've got a coupling capacitor here, and then we've got this Rin, and then the ratio of RF to Rin creates the gain. So right now it's 10 and 10K. Gain will be 1. So the voltage gain will be 1, which we don't really care about the voltage gain because we're pumping 5-volt signals into here. So we're going to have a big enough voltage. We care about the current gain, and that's what this bad boy is going to give us. It's 1.1 watt. So this is a good amplifier. We'll look at it also and see why I picked it, and then it just goes right to the speaker. And this is a bridge tied load. Notice here's the plus and here's the minus. The one side of the speaker does not go to ground. So what this means is it can flip the entire signal. So you get a really wide range of amplitude. It's not referenced to ground. So this is an awesome little amplifier, very low cost. Very simple too. Just one capacitor here, a couple resistors, and you're off. That's it. All right. Okay. Let's see here. Then this little nastiness is the USB to serial UART using our famous FT231 XSR USB serial UART from FTDI. And this is different than the Nano uses, and I'm going to tell you why it's different and why it's better and why it's cheaper when we get to that. All right, but this is a cheaper version of the chip. And then some of this is from the reference design from FTDI. They say, hey, do this way, like use 27 ohm here, and these resistors are for reflections because these can become transmission lines when you're doing the D plus and the D minus in a USB signal. So we keep that little design, and then some bypass capacitors here on the power and so forth. And then here's what's interesting is this is the actual USB connector. And on the connector itself, there's ground, there's data. We're not using the ID here. And then VBus is the 5 volts coming from the USB port. Now, kind of a issue. USB ports are not guaranteed to be 5 volts at all. They're anywhere from 4.75 to 5.25. If you're lucky, they might be more, they might be less if the company has maintained the spec. Normally, I would never ever, if I was going to make a consumer device, I would not take this V-Bus and put it directly into anything. I would regulate it, buck boost it, do something to it so I know exactly what it is rather than assuming that it's going to be correct. If you plug your computer, a laptop, your Xbox, your charger into this thing and measure the voltage, you'll get everything. You get voltages all over the place. Now, it's not going to hurt it. This thing is robust enough where it'll be okay. We're going to talk about that a little bit more later. But anyway, anything you hook up to a USB power, we want to have a little fuse. We got a little ferrite bead here for noise. We don't want noise to be injected into our system. We also don't want to inject noise back into the USB. Couple capacitors here, bypassing to get a nice clean. This is a VCC USB, just a label I put on here. And then finally, another protection diode so current can't come in this direction. It only can flow in this direction, so another Schottky diode here. And then we have our VCC 5 volt, which is going to get connected to the other VCC 5 volt from our power supply. We'll talk about all this, all right? And that's it in a nutshell. So you've got basically an Arduino. Then you've got, this is the Arduino and this is the Arduino. That's basically the Arduino. Here's the I/O for the Arduino, which are just headers. The power supply, which is the Arduino Nano has a different, it doesn't even have one. I think it just uses the USB. We've got our own power supply because we want to have it battery powered. Then we've got this switch mux here so we can have a bunch of switches for free. Then we've got our little display LEDs. We've got our programming port. We've got an audio amplifier. So we have all this hardware added in. We're going to put it all on the same board called Simonduino, right? That is the plan. Okay, so what is it going to look like? Again, I've showed you this before, but if you're skipping around and don't know what I'm talking about. So here is the Simonduino. Okay, so here is the finished PCB, 3D view, obviously. So rotate it around a little bit. And again, I've shown you this, but now that we know what things are, we can kind of take a look. So here are our 4 LEDs. And now one thing you'll notice about the board is obviously it's mostly mostly surface mount. So this is a surface mount board, and so we'll be using surface mount parts. And these size parts are 0805. If you recall, there's like 1210s, there's 805, 603, 402, 201, 101, super teeny tiny. 805 is small enough where it's small, but it's big enough where you can get your hands on it. And as an introduction to surface mount, this is a great size to start with, 805s, 0805. All right, so that's what I recommend. Even if you've got bad eyes, you can still, with your glasses or whatever, be able to solder things and not have a problem. But you have to go to surface mount. All right, the through hole stuff is, when you're starting off, do a couple of boards like that. Then it's time to get big boy technology going and use surface mount because it just makes things easier. It makes routing much easier, and then you don't have these giant components taking up all your space, and it's cheaper in manufacturing, obviously. All right, so the majority of the board is surface mount. Now, what I did leave as through hole, just to be easy, was all the mechanicals, right? The majority of mechanicals are all through hole. Now, you can find surface mount mechanicals as well. For example, the USB is a surface mount mechanical. And I can show it to you right here. You can see if I rotate it around, let me see here, and take my life in my hands with this tool. All right, let me zoom in here a little bit. So you can see this is actually just on the surface, just surface mount. Okay, but obviously all of the other things, and there we go. Okay. Obviously, all of the other parts are through hole. Like this is through hole, all right? The buttons are through hole, and the LEDs are through hole also, just to make them big. And that way, because if you want to make a plastic enclosure, print something 3D print, they can stick through very easily. The programming port is through hole. This crystal this is the processor right here. Right, the crystal is through hole, the switches are through hole, this one and this one, right, and then here's all our other momentary switches, right, and then let's see here is our, I believe this is my, here's the amplifier right here, here is, what's this right here, this is the power supply right here, all right, and then of course the USB hardware is over there. Here's our little multiplexer, our 148 that multiplexes all the buttons, all right, and then of course here's the Arduino. This basically is the Arduino up here, all right? or maybe this is what's multiplexing all. Let me see, this is U5. What's this guy up here? U5, let's see, what's U5? U5, U5, U4 is our amplifier, and U5, yeah, U5 is our multiplexer IC. So this is U5 right here. Okay, now let's see what else we have here. Okay, so you see there's these 4 holes here. This might be reminiscent of something. Let me turn this board upside down. Aha, there is our battery holder, right? So there's our battery holder. And let me see if I can spin this around. And I am really sorry, but this does not work like a normal 3D. You kind of grab it and spin it, and it just doesn't do what you want it to do. It's very annoying, and I'm not able to do it. I'm not going to waste any more of your time sitting there trying to do that. But anyway, so that's our battery, our 9-volt battery. Now, all these things you see sticking out here, these just represent the posts which we're going to solder and then cut. Okay, but one thing that's important here is the speaker. Here's the speaker connector right here. So again, we're going to take a little speaker and we're going to place it on the back, and then it's going to face through the front. So there's the little connector, right angle, so that we could have the speaker hidden in the back as well. Let me turn this thing over and pray. There we go. So we've got a bunch of holes for the speaker, so the sound can get through. All right, so that's kind of cool. And so that's about it. So that's everything and what it looks like. Again, it's designed in blocks. Every little section is its own section, and that way you can work on things separately and then kind of make sure that you think that they're working before you work on the next section. And then routing from each is a little bit easier. So that's the entire design. Okay, that's the entire design. And let's take a quick look at the layer. So that's the top copper layer, obviously, and there's the bottom copper layer, all right? Top copper and bottom copper, so they're both fairly simple, all right? And if we go back into 2D mode, let's get rid of, we'll go into single layer mode. There's the top, let me zoom in. All right, so now I did not route this manually. I routed it with the auto router. All right, and it's not bad for the auto router. So if I were to route this manually completely, it might have looked a little bit better, but it's not bad at all. Of course, I cleaned it up. All right, cleaned it up definitely, and just looking at it, I could keep on cleaning it up. We'll talk about that when we get to that. All right, and then here's the back, the bottom copper. Again, not bad, for the auto router. Some of the things, I can look at and I don't like the way it did it, but again, I didn't have to sit here for 20 hours doing this. All right, so anyway, we're going to use the auto router. Now, one thing also is this has a circular shape, a circular cutout. So we have the board here, and by the time I'm done talking about this, I'll make sure that this is correct, but we just want to make sure that the mechanical outline for the board edge is this circle, which I believe it is, but I could be wrong. I think it is the way that I've done it, and I'm not exactly sure, but by the time we get done talking about this, I'll make sure of this and show you how to do this. This is a little bit of a pain to make this shape a circle and make sure that it's doing what it's supposed to do. All right, so that is it. Of the preliminary. So, just a lot just talking about this. So again, this is what you do as an engineer. You kind of decide, what is it I want to make? And then you kind of do your research. You say, hey, I want to make it Arduino compatible. Maybe I want to make it Raspberry Pi compatible. Maybe I want to make it microchip PIC compatible. Maybe I want to make it Parallax Propeller compatible, or ARM compatible, or Intel compatible. I don't know. So we pick something in Arduino because we like programming Arduinos maybe. Then we say, okay, cool, we'll use the Arduino so it's compatible. Let's find a little one. We found the Nano, and we're going to talk about more of this stuff in detail and dig down. And then we say, okay, we want to add these features to it. We'll put it all on a board. It's battery operated. We want USB. We want this, and kind of come up with all these things. And then, here is the end result of everything. Now, this to me is a very, very, very simple board, right? But to someone that's just starting out, this is a fairly complex piece of technology. It represents an entire computer. It's got input, output. It's got lights. It's got all this stuff. And then what's cool about it is right here on these interfaces, and you could make these male or female. Right? They could be a female or male. It doesn't matter. The headers are the same pitch. You could hook up an LCD screen to it or anything you want. So you can actually hook an LCD and make this little thing an entire little game system if you wanted to. So it's the beginnings of a lot of different projects, but it kind of shows you a fun one where it's just one application all in a box based on an Arduino, which if you don't know how to program microcontrollers and all that, this is going to be fairly meaningless to you, but from an engineering and electronics point of view, we don't really care. And here's also a great irony. Many kind of old school electrical engineers, embedded engineers can't even program really. Many of them haven't programmed in so long because they just design hardware. There's a firmware guy or girl sitting over there that does all their firmware. So they design all the electronics, they hook everything up correctly, and then that poor person has to sit there and read the data sheets, write the drivers, get it all working, boot it up. Not fair. So anyway, we are hardware and firmware and software because we're going to do everything. But if you don't know how to do that, don't worry, because many times you would just be designing the electronics. All right, so that's okay if you don't know microcontrollers and all that, and that's something you want to learn next, which is great. But for now, don't worry about it. And we're just going to do it from a hardware point of view, and I'll make sure to talk you along any software stuff because I don't want to make assumptions you know a lot about it. Okay, so why don't we stop here? And then when we come back, we will start going into each of the subsections, starting with the Arduino Nano design and kind of going over that and how I ported it. And then we'll just go through everything piece by piece in the schematic, and then kind of see how this layout was done also. Okay, so I'll see you in the next video. Bye. All right, welcome back. And where did we leave off? We were just talking about the Simonduino and kind of going over the high-level design and looking at all the subsystems. And now what we're going to do is we're going to start drilling in, and we're going to start looking at the actual design of things and the IC selection that we're going to use. All right, so so one thing, let's come back here. So what I've done was we have the work copy that we created, which is just a copy, a forked copy of my original, right? So we've got this work copy, and the work copy is complete. And this is kind of what you want to do. You want to create a fork of the original, the color match game, and call it work copy or whatever you want. That way you can mess with the final complete project, right? But also I decided, I can't remember if I said I was going to or not, but we're going to create a final version, and we're just going to do a lot of copying and pasting. So we've got a final version here, and the final version is just blank. So this is going to allow us just to copy and paste pieces of the working copy as we look at the ICs. All right, so so let's just get right into this. All right, let's get back to the design here. So here's the Arduino Nano. So this document